Morning,
Morning.
ready.
Morning, Professor Madhya, Professor many others, of course.
Good morning.
Good morning, everybody.
Hello, Sudrak sir. Namaskar.
Namaskar, sir. The grand start of the IGC.
Yeah.
Hope that it goes off in a great
Speak.
manner.
It will
Your mic
go in a
is-
good manner.
Because Professor Reddy has made so much effort, I'm
Yeah.
sure it will all come good.
He told there are 600 registration for this workshop. That's great.
Oh, I see.
Yeah. Am I true, Professor Reddy?
Yes, sir. Yes, sir. Exact number is 596.
Yeah, that's
596.
very interesting.
And how many have registered for the conference?
920 plus 1. 920. Still, the people are joining.
I have yet to register, so
Yeah,
one
yeah.
more you can
I
add.
think it will touch 1000. Sir.
That's, I think, a record for IGS conferences.
Yeah,
That is a record. Yes.
that's a record. Maximum was somewhere 550 or something like that. Professor Samadhi, remember how much?
No.
Ah.
It was 673 in our
673. Yeah.
2003.
I think Surat was even more.
2011, Kochi had the maximum.
How much?
600 plus, I don't remember.
600
how much.
plus.
Less than 700.
Okay.
Good morning, sir.
Morning, Samadhya. How are you? Good. Welcome. Be ready to take over in another 3 days.
Yes,
Yeah.
Yes, sir. We need your blessings.
They're always there. I think, I've been with IGS full. Whenever IGS wants, I'm there.
Yes. Thank you, sir. Thank you.
You can always count on me.
Sir.
It's more than 25 years now since I'm with Babu has set a good standard. You have to now match it or go higher in terms of activities and everything.
Even if I am able to maintain that standard, that will be good enough for me.
Keep the ball rolling.
Yeah.
No, it will go.
Good morning, Professor Madhav, sir.
Morning. I'm good. Oh,
Good
Nice to see
morning,
you
Professor
after
Rao.
long time. Good morning, sir.
morning, Professor. Good
Morning.
morning.
So by now, 74 people have joined. 74. Good morning, Professor Sahu.
Good morning.
Nice to see you. It
Nice
looks
to see you too.
it's very cold there in Delhi.
Yeah. Where are you? You are not in Delhi?
I'm in Roorkee.
Okay. Equally cold.
Equally cold.
Yeah.
So,
Hi, sir.
Sir, good morning, Professor Prasad Reddy, sir, Vice Chancellor of Andhra University. He has joined.
Professor Prasad Reddy, good morning.
Morning, Professor Reddy.
Good morning, sir.
Good morning, Professor Reddy.
You have the senior most alumnus in front of you, Professor Reddy. I passed out 6 years ago from the university. So,
Sir, sir, your audio is not coming.
your audio, Professor Reddy.
Oh,
Is it okay now?
Yeah,
Okay.
it's okay. Yeah.
Right, right. We are really honored to have you, sir, because you said that, you passed out from this institution 60 years back.
Yes.
Yeah.
I was allowed to be there today, but the corona COVID has kept me away.
Oh, okay, right.
Good morning, Professor Reddy, sir.
Good morning, sir. Satyan Reddy, shall we start? Because
sir.
it's 9 o'clock.
Okay, sir.
Are you okay? Waiting for some guests to join?
Some more participants, all guests have joined, sir. Professor of TC213, Chairman of TC213, Professor Issmge Sassai has joined. And Professor
Okay.
Jihan from Kansas University is here.
Uh-huh.
And our IGS President, Professor Babu, and Secretary, Professor Shahu, they are all here, sir, to grace the occasion. And our EC members and our incoming President of IGS, Professor Samaria. So all are
Okay.
Available, sir, now. They have already joined.
Okay, that's very nice. You can go ahead with the inaugural activity.
Okay, sir. We will start, sir.
So that,
Slowly
we will not be
Okay, sir.
losing time, okay, for
Okay,
this
sir.
real sessions.
Sir, Chairman, sir, Professor Sassa.
Yes.
Professor Sassa.
Yeah. Can I speak?
Yeah. Can I start the inaugural session, sir?
Yeah. Yes. Please.
Okay, sir. Okay, sir. Thank you. So, good morning to all of you. On behalf of International Society for Soil Mechanics and Geotechnical Engineering, Indian Geotechnical Society, and Andhra University, Visakhapatnam, I extend a very warm welcome to you all to the inaugural function of this Issmge TC213 workshop on scour and erosion. This event is being organized as the pre-conference workshop of the prestigious Indian Geotechnical Conference 2020, scheduled to be organized from tomorrow, that is 17th to 19th of December. I am very thankful to the chairman of TC213, Professor Issmge Sassa, for his guidance right from the moment of initiating to organizing this event. He has provided excellent guidance in planning each and every activity of the workshop. Thank you, sir. And I would like to thank Professor E.C. Shin, Vice President Asia, Issmge, for accepting to deliver the lecture and for extending his support. I would like to also thank Professor Jihan of Kansas University for readily accepting to deliver a lecture here. He is giving one more lecture in IGC. I thank our backbone, I can say, Professor M.R. Madhav sir, for his continuous support, encouragement and guidance in organizing all these events, right? He is here to deliver an important lecture here today. And the other speakers we have are Professor Sundar from IIT Madras, Washington Department. And we have two professionals, one from McAfee and McAfee, that is McAfee, Mr. Paulo, and from 10K, Mr. Albert. They are here to present case studies, and from Andhra University side, I will be giving a lecture. So in all, 8 lectures are there in this workshop. So I hope we'll be addressing the important aspects of scour and erosion with case studies, so that the deliberations of the workshops will be useful for the participants. So with this introduction, I request Ms. Aparna to offer a prayer before we go into the remaining program of the negotiation. Aparna?
Good morning, sir.
Okay.
A very good morning to all. Thank you, Satyanarayan Reddy, sir, for this opportunity. Gananayakaya Ganadevataya Ganadhyakshaya Dhimahi Gunashariraya Gunamanditaya Gunechanaya Dhimahi Gunadhishaya Gunapraveshtaya Dhimahi Ekadantaya Vakratundaya Gauritanayaya Dhimahi Gajeshanaya Palachandra Shri Ganeshaya Dhimahi Ekadantaya Vakratundaya Gauritanayaya Dhimahi Gajeshanaya Palachandraya Shri Ganeshaya Dhimahi Ganachaturaya Ganapranaya Ganantaratmane Ganotsukaya Ganamattaya Ganotsukhamanase Guru Pujitaya Guru Devataya Guru Kulasthayine Guru Vikramaya Guya Pravaraya Gurave Guna Gurave Guru Daitya Kala Kshetre Guru Sharma Shararadhyaya Guru Putra Paritratre Guru Pakhanda Khandakaya Gita Saraya Gita Tattvaya Gita Gotraya Dhimahi Gudha Gulfaya Gandhamattaya Gojaya Pradaya Dhimahi Gunaditaya Gunadishaya Gunapravishtaya Dhimahi Ekadantaya Vakratundaya Gauritanayaya Dhimahi Gajeshanaya Palachandraya Shri Ganeshaya Dhimahi Ekadantaya Vakratundaya Gauritanayaya Dhimahi Gajeshanaya Palachandraya Shri Ganeshaya Dhimahi. Thank you so much all. And it's a privilege for me to join this meeting. A very good. Thank you.
Thank you, Aparna. She was our former MTech student of Soil Mechanics and Foundation Engineering, and she is presently working with RV Associates in Hyderabad. Thank you, Aparna, for your offering the prayer.
Thank you, sir. Thank you for this opportunity.
Starting this workshop. Thank you. Now I request Professor Issmge Sasa, Chairman of TC213 of International Society for Soil Mechanics and Geotechnical Engineering, and the President of this inaugural function, to give his opening remarks. Before that, I have a word to say, sir. So for this workshop, I would like to inform you that 596 have registered with participants from 18 different countries, right? People from abroad are also attending. So with this, I request Chairman Professor Sasa to give his opening remarks.
Thank you, Professor Reddy, for your kind introduction. I'm Issmge Sasa, Research Director of Port and Airport Research Institute at National Institute of Maritime Information Technology. And I am the chairman of the International Society for Soil Mechanics and Geotechnical Engineering, Technical Committee 213 on Score and Erosion. We have held a series of international Society of Soil Mechanics and Geotechnical Engineering, Issmge, international conferences on score and erosion in every 2 years, as participated by both geotechnical and hydraulic engineers, reflecting the interdisciplinary nature of the theme, score and erosion. This year, the 10th International Conference on Score and Erosion was supposed to be held in Washington, D.C., United States. But as you may know, due to the spread of COVID-19, the 10th ICSE has been postponed to 2021 next year. Amid the situation, we have decided to hold an international workshop on score and erosion that is hosted and coordinated by Professor Reddy, a member of the Technical Committee 213 on Score and Erosion of the Issmge. So I wish to sincerely thank Professor Reddy and Professor Babu, President of the Indian Geotechnical Society, and Professor Madhabu, and Professor Reddy and their colleagues for hosting this international workshop on score and erosion at Andhra University, India. I sincerely hope that this workshop will provide the audience the latest knowledge and development to understand and mitigate the risk on score and erosion. And that's for all for my brief opening remarks, and thank you.
Thank you, sir, for your opening remarks. So next item is a report on workshop by me. So I have already given report and details of speakers and participants. So we have participants from academic institutions, profession, research scholars, and PG students. So the ratio between practicing engineers and professionals taken together with respect to students is about 60-40. So out of 596 registrations we have received till yesterday, and many more will be joining in course of the program, because we have given the access to as many members as possible so that they will be benefited. Official registered number is 596. So with this, without losing much time, I request Professor J.T. Shahu, Honorary Secretary of IGS, to address the participants.
So, respected Professor Prasada Raju sir, Vice Chancellor, Andhra University, Professor Issmge Sasa.
Professor Sahu sir. Professor PV.
No, it's okay. It's okay.
Professor
Right.
PV Prasad Reddy.
No. It's all right.
Okay.
It's all right, Professor Sahu. Just please
Okay.
continue, right?
Okay.
Right.
Professor Issmge Sasa, Chairman TC 213, all dignitaries present, speakers, and participants. Thank you for giving me this opportunity. First of all, let me congratulate Professor Reddy for selecting such a great topic for the workshop. If I recall, in last EC meeting, we had decided that we must select the most relevant and the local aspect for our Indian Geotechnical Society conferences and the workshop. So I feel that this topic is the most relevant as far as the Vizag and the local area is concerned, because scour and erosion I know is a it being very close to the seashore is one of the major problem around the Vizag. Hence, this is the most relevant theme on which he is conducting this workshop. As far as Professor Reddy, can I make some little projection? I don't know.
Sir, you can present, sir. You can present your. You can share your screen and make your presentation.
Sure. Okay, I will just quickly do that. Just excuse me, 1 minute. Sure. Okay, can you just see my screen?
Yeah, it is visible, sir.
Okay, thank you. So IGS and ISSMG has a long and fruitful association since last 70 years or so. So IGS is an affiliated member society of ISSMG. ISSMG is a federation of 90 member societies and IGS is one of those. And ISSMG has around 20,000 individual members. ISSMG membership, individual membership is always subscribed through the member society like IGS. So those who are little unfamiliar with this, so IGS has about 242 members who have also taken the ISSMG membership. The membership fee is around rupees 6,000 only for a block period of 4 years. And ISSMG has several technical committees. There are 35 technical committees of ISSMG. We just have 91 representatives, 35 technical committees. So, IGS has been very active, ISSMG activity. So the topmost conference of ISSMG, which is ICSMFE, 13th International Conference on Soil Mechanics and Foundation Engineering, was held in New Delhi in 1994. Besides that, we have also hosted 3 Asian regional conferences in 1960, 1975, and 2007. Then 6th International Congress on Environmental Geotechnics was held in New Delhi in 2010. Then 16th Asian Young Geotechnical Engineering Conference was held in Bangalore. 3 of our honorable members, Professor K.L. Rao, Professor Dinesh Mohan, and Professor M.R. Madhav. Professor M.R. Madhav is also present in the audience, served as Vice President Asia of ISSMG. IGS members regularly present papers in international conferences. They also serve as chairman, co-chairman, general reporters, panelists, etc. in these conferences. IGS has signed agreement of cooperation with several major societies like USA Society, Japan, JGS, and Korean Geotechnical Society. Joint workshops with all these societies are regularly organized. In 2017, we had KGS with Korean Geotechnical Society in Korea, Seoul. Then in 2017 with Japanese Society in Guwahati, 2019 with Korean Geotechnical Society at Surat. Beside this, we have been now for last 2 years, we have been regularly organizing major TC supported international symposium, conferences, and workshop. Before COVID period, face to face, you can see these are the conferences which were organized with the major support from the TC committee. Beside that, during the COVID period also, we have arranged several webinars jointly with TC and other international geotechnical societies have been held during this COVID period. So with that, I thank Professor Reddy for giving me this opportunity and wish all the best for all the participants and look forward to great interaction during the conference. Thank you.
Thank you very much, sir, for exposing the participants to IGS and ISSMGE interaction and the details of both the professional bodies. Thank you, sir.
My pleasure. My pleasure.
Now I invite Professor G.L. Shivkumar Babu, President of Indian Geotechnical Society, to address the participants.
Professor Babu, you are mute.
Professor, yeah, hello, am I audible?
Yes, sir.
Yeah. Professor Prasad Reddy, Professor Issmge Sasa, Professor Satan Reddy, Professor Sahu, and other distinguished colleagues. And it's a pleasure to be a part of this important event, TC 213, on this current erosion. At IGS, we have been working quite hard to interact with some of the TCs, which are the activities of which are quite relevant to Indian conditions. And I'm delighted to see that Professor Sasa has kindly agreed to be a part of this event. As pointed out by Professor Sahu, we have a long coastal line and there are a lot of erosion problems everywhere. And maybe the knowledge that we get from this particular program would be valuable inputs to how do you address this problem, and maybe look at codal provisions that we have and do a lot of research in this area. That was a prime motivation. I should also say that the support of the international community has been very, very fantastic in this regard. And I'm delighted that we have a lot of experts participating in this particular event. I'm sure that we'll have good outputs from this particular program. So I welcome you all again for this important event of the IGS, and the special welcome to the the Professor Sasa, Professor Jihan, and other speakers who would be giving lectures. And thank you very much.
Thank you, sir. Thank you for your excellent support and guidance for organizing this workshop and the coming IGC 2020 activity from tomorrow. Thank you very much, sir. Now I invite Professor PVGD Prasad Reddy, Vice Chancellor of Andhra University, Chief Guest of the inaugural function, to address the participants. Before he addresses, I would like to inform you all that Professor Prasad Reddy is a senior professor in Department of Computer Science. He served the university in many positions. Earlier, he has served as registrar, rector, and now as the vice chancellor. He is instrumental in many development activities of the university and is striving hard to take university forward, and hopefully under his able guidance, right, we'll see our Andhra University best placed among universities of the world. At least in top 100, we hope we can reach to that. With this introduction, I invite Professor PVGD Prasad Reddy to deliver his address.
Thank you, Satyanarayana Reddy, for your very nice introduction about me. Is my voice audible there?
Yes, sir.
Yeah, okay. So good morning, one and all. It really makes me very happy to be present in the midst of all of you virtually this morning during the inaugural activity of this workshop. And from the university, let me extend a very warm welcome to all the dignitaries, and in particular, Professor Issmge Sasa and Professor M.R. Madhavji and Professor Hung and Professor Sundar, Professor Babu, and Professor Shivakumar, and all the other members. And I understand, from the talk of the convener Satyanarayana Reddy, that about 540 participants or delegates, they have registered from 18 different countries. And I'm quite happy about it. And the International Society for Soil Mechanics and Geotechnical Engineering, and its member, I understand, Indian Geotechnical Society. They're organizing this pre-conference workshop on a very important topic called scour and erosion, in association with the Department of Civil Engineering of Andhra University. And it's really a welcome initiative. Because the university is located in a place called Visakhapatnam, and which is going to become, in fact, the executive capital of the newly formed state of Andhra Pradesh. And as such, if you look at the Visakhapatnam, or maybe I think Andhra Pradesh as a whole, we have a very long coastline with varied topography. And as such, we are suffering from problems of beach erosion caused by sea waves, or maybe I think subsoil erosion, especially during cyclone period. Because recently also the city was affected with many number of cyclones, and a couple of years back Hudhud also. And there is a heavy rainfall also these days, and so because of this, the post, in fact, Visakhapatnam, which is a port city on the east, which is plagued with several problems of erosion. And not only the erosion at Visakhapatnam, as such in Andhra Pradesh, we have got good rivers like Godavari, Krishna rivers, and very frequently we hear that there are floods, flash floods during the cyclone period, and they're resulting in scouring of river beds. And there are many instances of that damage happening at the foundation of bridges. For example, there is a huge project being constructed at Polavaram, and the Polavaram works are also getting affected because of the sand erosion especially during floods time. And I have a technical document, in fact, given by Satyanarayana Reddy. Let me just present a few points from there. The present international workshop on scour and erosion, planned with expert lectures by eminent academicians and practicing engineers from India and abroad, to address the various issues related to sea erosion, river erosion, and subsoil erosion caused by surface and subsurface flow of water, is very apt for countries like India. This is what is given to me by, in fact, the expert Satyanarayana Reddy, who is in fact the convener of today's workshop. And I hope and believe that the deliberations of the workshop will be really useful for civil engineers as a whole, because I understand not only the students and scholars, even some practicing engineers have also registered for this workshop, and along with geotechnical engineers. And the outcome of the workshop definitely would be really useful, and to tackle the problems of the so-called scour and erosion. Let me once again thank Professor Issmge and the chairman of TC213 of International Society for Soil Mechanics and Geotechnical Engineering, and Professor Shivakumar Babu, the president Indian Geotechnical Society, for taking up this initiative to allow Andhra University to offer this kind of a workshop. And let me also thank Professor Shin, Vice President Asia, Professor Madhav, the Emeritus Professor from IIT Hyderabad, for whom we have also extended an invitation to be on the board of Andhra University, and Professor V. Sundar, IIT Madras, who are going to deliver the keynote addresses. And the university, Andhra University, in fact, which is a 94-year university, and the Department of Civil Engineering, we always look forward for really a continued support and association with the Issmge, as well as its member IGS, in organizing several such important technical events in future. Thank you so much, and I wish you all the best.
Thank you, sir. Thank you for sparing your valuable time and addressing the delegates of the workshop. And I thank you very much for your continuous support and encouraging us to organize events of this nature, sir. Thank you very much, sir. Next, I request Professor Shinji Sasa, President of the function, to offer his presidential remarks.
Yes, the time seems to be running short, but we are happy to hold this international workshop. And once again, I wish to sincerely thank Professor Reddy and Professor Babu and Professor Shafu and Professor Madabu and Professor Prasad Reddy and the colleagues for hosting this international workshop on score and erosion at Andhra University, India. I hope that this workshop will be fruitful to all the participants of this workshop, and thank you.
Thank you, sir. Thank you. Thank you for all the support for the workshop and your wonderful guidance, sir. Next, I request Dr. Jimmy Thomas, co-coordinator of this workshop and member TC213, to propose a formal vote of thanks for this inaugural session.
Yeah, good morning, everybody. It is my pleasure and privilege to express our gratitude to all those people who have contributed to making this workshop a reality. First of all, I thank Professor Prasad Reddy, the chief guest of today's function, and is the Vice Chancellor of Andhra University. Thank you very much, sir, for your inspiring presence. I thank Professor Shinji Sasa, the guest of honor, and who is the chair of TC 213 on scour and erosion. Thank you very much, Professor Sasa, for all your support and guidance. I thank Professor Shivkumar Babu, the president of our Indian Geotechnical Society, for his guidance and motivation. I thank Professor M.R. Madhav, who has been a source of great inspiration for organizing this workshop. And I thank all our IGS colleagues, including Professor J.T. Sahu and all others executive members. I express our deep sense of gratitude to all our speakers who have accepted our invitation and agreed to share their knowledge and expertise. I thank all the delegates who have registered in large number, showing their interest in this very important topic. Once again, I thank each and every person who have contributed to making this workshop a reality. Thank you. Thank you, one and all.
Thank you, Dr. Jimmy Thomas, for presenting the vote of thanks for this important event's inaugural session. Now we'll go into technical sessions of the workshop. So in the technical session 1, there will be 2 lectures delivered by Professor Shinji Sasa. The topic of lecture being mechanics and countermeasures of scour and internal erosion, tsunami or wave seabed structure interaction. And the second lecture will be by Professor Jihan, Glenn Parker, Professor of Geotechnical Engineering, Department of Civil Environment and Architecture Engineering, University of Kansas, USA. So for this technical session, I request Professor G.R. Shivkumar Babu, President of Indian Geotechnical Society, to act as the chairman and conduct the sessions. Before he takes over, I'll give you a brief introduction as a formality, though many of you are aware of Professor G.L. Shivkumar Babu. Professor G.L. Shivkumar Babu completed his PhD in Geotechnical Engineering in the year 1991 from Indian Institute of Science, Bangalore. After his master's degree from soil mechanics, master degree in soil mechanics and foundation engineering in the year 1987 from Anna University. He is graduated from Sri Venkateswara University, Tirupati in the year 1983. He worked as a Humboldt Fellow in Germany during June 1999 to July 2000, and he served as he worked as a visiting scholar in Purdue University, USA during February 95 to February 96. He is presently the President of Indian Geotechnical Society, Chairman of International Technical Committee TC 302 on Forensic Geotechnical Engineering, of Issmge. He is a fellow of American Society of Civil Engineering, and he is
Thank you. Yeah.
And he is serving as governor ASCE. He is serving a governor of ASCE Region 10. He has guided 17 PhDs and 5 MS research degrees, and he has authored a popular book on soil enforcement and geophysics. He has edited 8 books, proceedings, and he has several publications in reputed international national journals of about 180 in number, and in conferences he has more than 150 papers. Total publications about 300. He received several awards such as
Thank you, Professor Reddy.
Just one line. He received several awards such as John Booker Award from IAC-MAG, Humboldt Fellowship from Germany, DST Boys Cast Fellowship, and few awards for best papers from various professional bodies like IGS and AAC. With this introduction, I request Professor G.L. Shivakumar Babu to chair the session and conduct the proceedings. Please.
Thank you. Yeah, thank you, Professor Reddy. First of all, I would like to thank you for giving me this opportunity to chair this session. I would like to invite the speaker of the session, first speaker, Professor Issmge Sassa. He is TC chair, TC 213 chair. He is head of the Soil Dynamics Group and Research Director of International Research Center for Coastal Disasters, Port and Airport Research Institute, National Institute of Marine, Port and Aviation Technology, and National Research and Development Agency in Japan. He obtained his doctorate from Kyoto University. He is best known for his seminal works on wave-induced seabed liquefaction that have been cited worldwide. His main research areas are soil dynamics, geodynamics, coastal and offshore geotechnics, subaqueous sediment and gravity flows, and ecological geotechnics. He was an invited panelist twice at the 15th and as well as the 17th ICSMG events, served as a panelist leader for the UNESCO conference. He's a recipient of numerous awards, including commendations by the Prime Minister for the Disaster Prevention Merit and by the Minister of Land Infrastructure, Transport and Tourism as a representative of Technical Emergency Control Force. He has Best Paper Awards from Soils and Foundation Journal, and he has got many awards from the Japanese Geotechnical Society, and he has been outstanding, I should say, in a simple word. And I would like to invite him to deliver his lecture. Professor Sassa, would like to have a lot of interactions with you because we need your support to work together in this important area of cost erosion. Thank you. Please welcome. I welcome you. Welcome you for this.
Thank you very much for Professor Babu for your kind introduction. And now I'd like to share my slide.
Yes.
Can you see this slide?
Yes, sir. It is visible.
Okay. So I'll start. I'm Issmge Sassa, Research Director at National Institute of Maritime, Port and Aviation Technology. And here I report some recent advances in the mechanics and countermeasures of score and internal erosion. In particular, I present a concise review of the structure interactions from geotechnical and hydrodynamic perspectives. The content is divided into 4 parts. First, I describe the background and the importance of the theme. And I then present tsunami seabed structure interaction by focusing on seepage erosion, effect of overflow and seepage coupling of score of caisson breakwaters with its countermeasure. Next, I would like to highlight wave seabed structure interaction. Here I will show that wave-induced liquefaction and score protection around a monopile are closely interrelated, and that will be followed by the mechanics and processes of internal erosion, cavity formation, and collapse behind seawalls and clay walls with its effective countermeasure. Finally, I would like to summarize the key contents. As introduction, tsunami and wave seabed structural interactions have received increasing attention in recent years following the devastating impact of the 2011 off the Pacific coast of Tohoku earthquake tsunami, ongoing development of oceanic infrastructures such as offshore wind turbine foundations, and the need for coastal disaster risk management. The mechanics and countermeasures of score and internal erosion plays a pivotal role in such tsunami and wave seabed structure interactions. The theme is multidisciplinary in nature and hence requires both geotechnical and seabed structure interactions. I first present tsunami seabed structure interactions by focusing on seepage erosion and the effect of overflow and seepage coupling on the score of caisson breakwaters with its countermeasure. I then present wave seabed structure interaction by highlighting wave-induced liquefaction and score protection around the monopile, and the mechanics and countermeasure of internal erosion, cavity formation, and collapse behind seawalls and clay walls. I first present tsunami seabed structure interaction. Tsunami seabed structure interactions are schematically shown in this slide. In fact, the upper figure shows tsunami-induced forces on caisson breakwaters, which mainly comprise of tsunami wave force and tsunami-induced overflows and seepage flows and other related forces. The lower figure shows the corresponding failure modes of the foundation that consist of scoring, erosion, piping, boiling, and shear failure. These failure modes and processes are closely interrelated. I will show some key mechanisms of the concurrent processes of the instability of foundation and the tsunami. It is essential to reproduce a prototype scale stress field in clarifying the instability of structure foundation. Geocentrifuge makes it possible and has proven effective in studying fluid soil interaction problems such as wave-induced instability of seabed soils. Indeed, the role and importance of centrifuge testing in fluid soil structure interactions has recently been emphasized. Here I report the novel use of geocentrifuge for studying tsunami seabed structure interactions involving the role of tsunami-induced overflow and seepage on score and erosion. The seepage flow in the rubble mound becomes turbulent due to the high permeability of the mound as crushed rocks. The similitudes for such turbulent seepage flow as well as overflow have been satisfied together with the mechanical similarity between the model and the prototype. I first present the progress of seepage erosion. Tsunami-induced seepage can induce erosion in the sandy ground beneath the rubble mound of caisson breakwaters. Actual breakwater was targeted and the experiments were performed under conditions where no sliding and overturning were allowed to occur in order to focus on the erosion process of the ground. The results show that seepage erosion progressed with time at the vicinity of rubble-sand interface. The eroded mass deposited in the onshore side of the mound in accordance with the onshore direction of the seepage flow. Accordingly, caisson settled owing to the tsunami-induced seepage erosion. Now the effect of overflow and seepage coupling on score of caisson breakwaters. The coupled tsunami overflow and seepage actions can promote the development of mound score significantly, causing bearing capacity failure of the mound, resulting in the total failure of caisson breakwaters, which otherwise remained stable without the coupling effect. Indeed, the figure on the top right indicates that without seepage, the score front stopped far from the caisson toe. By contrast, the coupled overflow and seepage promoted the mound score substantially, resulting in the total failure of the breakwater. The velocity vectors obtained from the high-resolution image analysis, as shown on the figure left, indicate the series of such concurrent processes of the instability involving score of the mound and seabed, bearing capacity failure as indicated by the upward direction of the arrow, and flow of the foundation, leading to the instability of the caisson breakwater and the coupled overflow and seepage. The influence of placing an embankment that is elevated mound as a countermeasure was examined by employing different bank thickness. The embankment significantly suppressed the effect of such coupled overflow and seepage in accordance with the decreasing hydraulic gradient that manifested underneath the caissons, thus preventing bearing capacity failure, resulting in the stabilization of the caisson breakwater. Without the countermeasure, the scar front reached caisson toe, yielding the phenomenon of significant washout that was boiling, giving rise to the formation of a cavity underneath the remaining caisson. Such cavity formation underneath remaining caissons was found to be consistent with what was observed following the 2011 off the Pacific coast of Tohoku earthquake tsunami. Tsunami-resistant breakwaters has been developed based on the outcome of recent research that I mentioned. Here I am showing the sketch of such uniform breakwater. The embankment reinforces the caisson against the tsunami wave force and suppresses the effect of the coupled overflow and seepage on score, as I mentioned. Such new form of breakwater with embankment has been brought into practice with a rational design, and it prepares, as shown in the lower figure of this slide, and this prepares for the mega thrust earthquake tsunamis that are expected to occur in the near future. So in summary for this part, the piping, boiling, seepage erosion, bearing capacity failure, and overflow score are closely interrelated and interacted, which all affect the stability of coastal structures. These highlight the crucial role of overflow and seepage coupling in tsunami seabed structure interaction from both geotechnical and hydrodynamic perspectives, which warrants an enhanced disaster resilience. I now like to talk about the wave seabed structure interaction. Wave-induced seabed instability considerably affects the stability of coastal and offshore structures resting on in the seabed. Representative forms and processes of the instability involve score and seabed liquefaction. Here I show that score and wave-induced liquefaction are physically interconnected, affecting the stability of structures. Here I am showing some factors affecting stability of breakwaters on sandy seabed. The upper figure shows the case for caisson breakwaters. Here, the sandy ground around the toe of the rubble mound may undergo liquefaction under scouring and severe wave conditions, which may lead to significant sediment transport. Owing to these phenomena, caisson may settle into the foundation ground. Once caisson settles, it may lose or reduce its preventive function against severe ocean waves, traveling toward coast and land. The lower figure shows the case for detached breakwater in a similar way. Indeed, under severe wave conditions, liquefaction or score may occur around the detached breakwater, which leads to substantial particle transport. Accordingly, rocks may settle into the foundation ground. All these processes are important design consideration of coastal infrastructures. Before going into the linkage between liquefaction and score, I may need to remark the basic yet important understanding of ocean wave-induced liquefaction. Here I'm showing a sketch or a close-up of sandy seabed saturated with water. Solid particles are surrounding pore water, and the granular soil, a seabed ground, is subjected to severe ocean waves, which consist mainly of wave-induced pressure fluctuation, as well as oscillatory flow. The essence here is unstable granular structures can easily fail under dynamic environmental loadings, such as ocean waves. The physical state of given seabed soil can be expressed by a form shown in the lower figure of this slide. The void state of seabed soil exists below the maximum possible void ratio, yet above the minimum possible void ratio, which may indicate that when seabed soils are subjected to cyclic shearing arising from severe ocean wave conditions, it may exhibit some tendency for contraction, namely cyclic plasticity, at given effective confining pressure, which may lead to buildup of residual pore water pressures and may undergo liquefaction under sufficiently severe wave conditions. Here I need to remark the basic difference between the ocean wave-induced liquefaction and earthquake-induced liquefaction. In contrast to the earthquake-induced liquefaction, the period of ocean waves is more than an order of magnitude longer than that in earthquakes. However, the number of cycles experienced under ocean waves is far greater than the case experienced in earthquakes, and accordingly, when seabed soils, particularly fine sands and silts with relatively low permeability, are subjected to severe ocean wave conditions, they may undergo the buildup of residual pore water pressures. Here I'm showing such excess pore water pressure generations in sand beds under severe wave conditions, schematically shown in this slide. The wave-induced excess pore water pressure may consist of two parts. First is fluctuating component, and the other one is the residual component, which stem from the contractive nature of sand. When this residual pore water pressure reaches its initial vertical effective confining pressure at given soil depth, liquefaction may occur. What is distinct in the ocean wave-induced liquefaction is a stress path-induced seabed under the action of ocean waves. In particular, liquefaction susceptibility or resistance varies substantially depending on the types of ocean waves, namely the ocean wave forms. Under progressive wave, both normal stress variations as well as horizontal shear stress variations act on the soil element of seabed soil, leading to the stress axis rotations in the seabed ground. By contrast, under standing wave that may occur in front of the impermeable vertical wall, such as seawalls or playwalls or caisson, in particular under the antinode, only axial stress differences on the horizontal plane of a given soil element of the seabed soil, leading to the stress path shown in symbol E of this slide. By contrast, under the node of standing wave, only horizontal shear stress variation acts on a given horizontal plane of a soil element of seabed soil, leading to the stress variation shown in the symbol C of this slide. These distinct forms of stress paths affect substantially the liquefaction susceptibility of seabed soil. I'm showing here the comparison of liquefaction resistance to progressive and standing waves. The horizontal axis shows the cyclic source ratio, which represents the index of severity of wave loading in a similar way of earthquake-induced loading. The vertical axis shows the residual pore pressure ratio, and when it reaches unity, liquefaction will occur. There exists a critical cyclic source ratio below which liquefaction does not occur, which indicates the liquefaction resistance. What is important here is that the seabed soil is most susceptible to liquefaction under progressive wave due to owing principally to the effects of the rotations of principal stress, namely the wave-induced stress axis rotations, which has been shown to substantially promote the buildup of residual pore water pressures. Such wind-induced stress axis rotation become pronounced in the course of wave loading. By contrast, the seabed soil is least susceptible to liquefaction under the antinode of standing wave. The node of standing wave, the corresponding liquefaction resistance is between that under progressive wave and under the antinode of standing waves. With this basic yet important understanding of the ocean wave-induced liquefaction in mind, I would now like to talk about the wave-seabed structure interaction by focusing on monopile, namely the stability of offshore wind turbine foundation. In the usual score protection around the pier or monopile, the diameter of the score protection area is 3 to 4 times the diameter of the monopile. And I show that such score protection is closely linked to the ocean wave-induced liquefaction. Wave-seabed monopile interaction was studied by advanced centrifuge wave testing, where the relevant scaling laws for wave-induced seabed liquefaction, namely time scaling laws for fluid wave propagation and soil consolidation, as well as for mount score, was satisfied. I'm showing here the results in form of the horizontal axis denotes the number n, that means the extent of stone layer score protection, and times the monopile diameter, and the vertical axis shows the ratio of increasing liquefaction resistance to ocean waves. The results show that score protection increased the liquefaction resistance. For instance, in the usual range of score protection, namely 4 times monopile diameter, liquefaction resistance increased by 20%. And when we use double usual range, namely 8 times monopile diameter, the ocean wave-induced liquefaction resistance can increase by 40%. Hence, score protection increased the liquefaction resistance depending on the diameter ratios of the score protection in the pile. However, what is important here is that it could not prevent the collapse of the monopile once liquefaction occurred. This basically means the importance of source certification on the wave seabed structure interaction in light of wave-induced liquefaction and score protection. And further, the results highlight the fact that the wave-induced seabed liquefaction may need to be considered in the rational design of monopile foundations for offshore structures, such as offshore wind turbine foundations. Now present the mechanics and processes of internal erosion, cavity formation, and collapse behind seawalls and clay walls. These are the photographs indicating typical cavity collapses behind seawalls. As you can see, there are large cavity collapses which may pose substantial risks on humans as well as on infrastructures. In fact, the photograph on the left shows the site of a fatal accident where a cavity formed in the backfill behind the caisson joint suddenly collapsed without giving any alarming signs to the soil surface. Investigations into the cause of such accident confirmed some key issues in internal erosion, cavity formation, and collapse behind seawalls and clay walls. Namely, first, defects in sand covers allowed sand particles to be washed out through the caisson joint. The progress of internal erosion resulted in the occurrence and evolution of cavities. Eventually, the cavities collapsed. Lessons here is that the stability of cavities in unsaturated granular backhills is of an essentially unsteady nature, owing to ocean waves, tides, groundwater table fluctuations, and precipitations. The key factors and processes involved are propagation of fluctuating water pressure, washout of sand particles, arch effect, and role of suction. Role of suction, that is negative pore water pressure relative to atmospheric air pressure, is of particular importance since no cavities would be formed in dry or saturated or submerged states of sand, since sand has inherently no cohesion. This means that suction may control the lifetime of cavities in unsaturated granular backhills above groundwater levels that accompany flows of power fluids, both of air and water, and complex hydro-environmental loading, as I mentioned in the above. Mitigation measures are hence important against internal erosion and cavity formation. In particular, maintenance-free operations are crucial for ensuring the safety of sustainable infrastructure development. Bilayered filter is effective in preventing such internal erosion, cavity formation, and collapse behind seawalls and clay walls. This is a sort of dual protection concept such that washout, cavity formation, and collapse are prevented from occurring, even if sand covers seas fail. Diverse options are possible. Diverse measures are possible as options, such as asphalt mat or cemented soil. However, these solidified materials are susceptible to defects and cracks when they are subject to severe dynamic forcing such as earthquakes and uneven differential settlement. By contrast, filters have been shown to be stable under various dynamic forcing such as waves, tides, and earthquakes if they are properly designed. International standards on filters have generally been developed for use in dams and seabeds. However, the use of filters in backfill materials, such as behind seawalls and clay walls, needs three key issues to be considered and satisfied. They are a clogging and trapping function, and stability against rubble stones, and performance under various dynamic forcing, such as waves, tides, and earthquakes. Before going into the filter designs, I would like to remark the basic yet important physics behind the internal erosion, cavity formation, and cracks, particularly the role of suction, how it may affect the process and forms of internal erosion, cavity formation, and collapse. I'm showing here two different types of sands, in which in the relatively coarse sands with low suction profiles, the contrast in fine sands with relatively high suction profiles above groundwater levels. These two different types of sands with different suctions substantially affect the process and forms of internal erosion, cavity formation, collapse. For illustrative purposes, I am showing here a video of the model experiment. At the center of the model ground, there exists a slit through which washout occurred. And how this is the case for fine sands with relatively high suction profiles. With continuing washout, the cavity starts to be formed and continues to grow. Because higher suction supports larger cavity, the top of the cavity tends to be flattened because of the high holding capacity. And what is important here that even if the large cavity develops below the ground surface and the top of the cavity approaches the ground surface, they barely leave any alarming signs on the soil surface. Yet large cavities eventually lead to collapse, as shown in this video. Now no alarming signs, yet suddenly and abruptly collapse. By contrast, this is the case for coarse sands with relatively low suction profile and setup is the same. The form of and the process or speed of cavity development is distinctly different in the case of coarse sands. A cone-shaped cavity, because the lower suction has lower holding capacity of the cavity, and they leave no alarming signs on the soil surface. Yet they eventually lead to collapse, relatively more rapidly than the case for fine sands with high suction profile. When, in case of using filter that is appropriately designed for the targeted sand, even if severe hydrodynamic forcing, no significant washout, no cavities, and no collapse will occur throughout the entire period of hydrodynamic forcing. So different types of sands with different suctions, the physical states of sand, affect substantially the processes of collapse and cavity formation. In coarse sands with relatively low suction leads to cone-shaped cavity due to the lower holding capacity of the cavity, and the cavity reaches the ground surface more rapidly than the case with fine sands with relatively high suction, which leads to a large cavity. For both types of sand, even if the cavity develops to a moderate size, such as 1 meter diameter, below the 50 centimeter beneath the ground surface, they barely leave any alarming signs on the soil surface. This means that the cavities abruptly collapse. Hence, preventive measures are crucially important. Filters that are appropriately designed work properly and prevent such internal erosion, cavity formation, and collapse and the various dynamic forcing involving waves, tides, and earthquakes. Recent research has shown that the grading of filters, in particular, uniformity coefficient, is a key for satisfying all the three functions that I mentioned and keeping the preventive function against internal erosion, cavity formation, and collapse throughout the service period of the infrastructure and has been shown to be stable under various dynamic forcing. Consistent with technical standards of filters for dams and seabed, rational criteria has been developed for use in backfill materials behind seawalls and firewalls. An example shown here. It is for practical use. It is formulated with regard to uniformity coefficient and the grain size ratio in terms of D50 for filters and sands. Such criterion applies to the upper filter layer, while the lower filter with grading larger than and adjacent to that of first upper filter layer. For other relevant information, please refer to the paper of the workshop of the Springer volume. Such bi-layered filter has been applied to an important infrastructure such as airport. The mitigation measure was taken to prevent internal erosion and cavity formation collapse around box culverts subject to wave propagation and has proven necessary for safe and maintenance-free operation of the important waterfront infrastructure. Now I'd like to summarize the key content. I have presented some recent advances in the mechanics and countermeasures of score and internal erosion through the tsunami wave seabed structure interactions. Progress of seepage erosion beneath rubble mounds leads to the settlement of caisson breakwaters. Tsunami overflow and seepage coupling promotes the development of score with mound and seabed ground, resulting in the total failure of caisson breakwaters. Tsunami-resistant design of breakwaters has been developed and brought into practice so as to prepare for the future megathrust earthquake tsunamis. Wave-induced liquefaction and score protection around the monopile are physically interconnected, affecting the performance of offshore wind turbine foundations. Then highlighted some key issues in the mechanics and countermeasures of internal erosion, cavity formation and collapse behind seawalls and firewalls. I sincerely hope that these may facilitate a better understanding of the physics involved pertaining to geohazard mitigation. And that's all for my content, and thank you very much for your attention.
Thank you very much, Professor Issmge Sasa, for a brilliant presentation. We have a couple of questions. We invite the audience to pose questions either in the chat box or they can talk over directly as well. We'll just see if there are questions. I don't see. I have questions from my side itself that I think you have proposed a revised filter criteria. What is your comment on the Terzaghi filter criteria based on all your expertise?
Comment on
Terzaghi's filter criteria. Yeah.
Comment on what? You mean filter design?
Yeah, exactly.
Yeah, filter design. This criteria is very consistent with the criteria used for dams and seabed, but the difference is that stems from the basic difference in the expected hydraulic gradient that would occur in the case of dams and in the case of backfill materials. For instance, in the case of dams, the highest hydraulic gradient would be around 10, but in the case of seawalls or firewalls, it will be around two at most. Hence, we can achieve an efficient and cost-effective design of filters. And another important point is that often the filters subjected to dynamic such as earthquakes. So the filters need to be stable and not just hydrodynamic forcing, but also the other types of dynamic forcing. And the design developed is ensure achieve the safety against such dynamic loading, and that is a noble issue of this design.
Yeah, there is one question by Professor Bina. How the tsunami affects the beach sand deposit and whether the liquefaction happens due to tsunami in seashore?
Oh, tsunami and liquefaction, yes. Tsunami and liquefaction also interrelated, but I did not mention that part. That the basic difference between tsunami and waves, the tsunami is long waves, long period waves, and the waves, the period is distinctly shorter than the case of tsunamis. But in the case of tsunamis as well, the liquefaction has been shown to occur, yet the types of liquefaction is different. The wave-induced liquefaction mostly residual pressure build-up, but the tsunami-induced liquefaction is closely related to the oscillatory liquefaction. That is closely linked to this oscillatory fluctuating component. That means under the receding tsunami from land, the cyclic boiling, this is one form of liquefaction, may occur under tsunamis. So the types of liquefaction that may occur under tsunamis and waves are different, yet of course the under tsunami liquefaction may occur under more severe conditions.
Thank you very much, Professor. Yeah. Thank you very much. I think it's a very interesting, brilliant lecture. I request all the speakers, they can post their questions in the chat box. We'll compile all of them and give it to the speaker later. And thank you, Professor Cindy Sissa. And now I request the second speaker, Professor Jihan, to be available. And before he commences his lecture, I would like to introduce Professor Jihan. Professor Jihan is a Glenn L. Parker Professor of Geotechnical Engineering in Civil Environment and Architecture Engineering Department of University of Kansas. He received his PhD degree in civil engineering from Georgia Tech in 1997. He is an author of the book Principles and the Practice of Ground Improvement and has published more than 400 journal and conference papers. He is a ASC Geo Institute Board Governor, Council Member of the International Geosynthetic Society, the current chair of ASC Geo Institute Soil Improvement Committee, the current chair of TRB Transportation Networks Committee. He serves as an associate editor for the ASC Journal of Geotechnical and Geomechanical Engineering and ASC Journal of Materials and editor for TRR Transportation Research Record. He has given more than 200 keynote invited lectures, short courses around the world, and he gave a lecture in the 21st annual George F. Sowers Symposium in Atlanta in 2018, and 18th UK IGS lecture in London in 2018, a keynote lecture at the Geoamericas in 18th, in the Geoamericas Conference in 2020. He received numerous awards, and I think some of them are Sankshar Prakash Prize for Excellence in Practice of Geotechnical Engineering, 2004 International Geosynthetics Award, and AC Award, Martin Clapp Foundation Engineering Award, and the ASC Kansas City Section Engineer of the Year Award. So, Professor Jihan, it's yours.
Okay, thank you, Professor Babu, for your kind introduction. And I also like to thank Professor Randy for the invitation to this interesting and important workshop. So my topic will be focused on the behavior of lateral load piles and the scour condition at the bridge. So my presentation condition will be very different from the previous presentation. My application basically is bridge foundations. Our study mostly focus on before and after scour. I will not talk about the process of scour, In this presentation, I will start with the introduction, give you very brief introduction about the problems we are facing, and then I will focus on the lateral behavior of single piles under scour conditions. Then I'll talk about three different issues here. One is effects of the scour hole dimensions. Second one is the effects of the stress history changes, how that affect the load behavior of single piles. And then how do we address then after I finish this, then we'll talk about the lateral behavior of pile groups. After finish this, then basically address one real problem. How do we analyze the lateral behavior of pile support bridges? At the end, there are a few concluding remarks. But let's start with introduction. And regarding the bridge scour, basically is the process of the erosion or removal of a stripped bed or bent materials from bridge foundation due to flowing water. There are basically three different kinds of scours. And in the bridge, the first one basically the general scour. I don't know what's going on. There's something going on with this pen here. Okay, it went away. Okay, the second situation basically is a general scour. Also, the federal highway also defined as a long-term degradation. Basically, the average removal of the material. The second type of scour, basically contraction scour, due to there's an object in the middle of the river that created the flow rate change and the flow direction change that will basically increase the scour capacity, remove the soil around the piers, high cap piles. The last basically is a local scour, mostly happen around the pile foundations. But that's will be the one I will be talking about today, mostly regarding the bridge foundation scour. But in terms of terminology, and we have three different situations. One basically called global scour. Let's say if we remove the soil uniformly around the piles. This is kind of ideal situation. You completely remove the soil, and then how they affect the pile capacity, the deflection of pile, subject the vertical, the lateral load. Now, my presentation will focus on lateral load only, not dealing with the vertical load. But this is also conservative approach when people design to consider scour effect. The second one basically the local around the single piles. Here we're dealing with different situations. We're dealing with scour depth, and then scour width at the bottom, scour width on the top, and also scour slope. Those kind of things I will talk about today. We did some research. Each factor. We have a pile groups, and then the situation will become a little bit complicated. There's really no unified definition about how do we dealing with different kind of scour. I give the name, this scour, the big scour I call the group local scour. And then you may have some small scour around the pile that I call the pile local scour. Now, for most cases, when the pile spacing getting closer, then you may not see the pile scour. Only if the pile spacing getting larger, then you may see the local scour basically similar to the single pile. Then here basically show you some picture of the real scour caused the bridge foundation explosion, complete exposed, and the kind of failure. And here I also want to point out debris sometimes will cause a problem because that will generate, reduce the water flow and generate horizontal load, basically to push the bridge fail. Now there are also the situation due to the scour and the cause the vertical sediment situation. Will be my focus. My focus will be on the lateral behavior. But we investigate the collect 36 bridges failures. We investigate what the most common failure mode. We found the lateral failure is the most common. It's about 40% over 100% the failures. That was the justification why we want to focus on lateral behavior of pile under skull condition. But in terms of pi foundation subject lateral load, this is a pi group situation. As you can see, we may have a skull original ground line here. We scale down and you will lose the support and also subject the lateral load. The lateral load will cause the pile to deform. How do we analyze this? Typically, we use this kind of model. This is a simple model. Basically, this is a pile and soil model as a soil spring. But if the pile start to deform, then basically there's deformation Y, and then the soil will start to react. That is a P. We can plot the PY curve as what we show here at the different elevations. As you can see, typically at the lower elevation, the PY curve is softer. At the deep elevation, the PY curve will be stiffer because of the overburden stress, the soil stiffer spot. This is the way how do we basically describe or model the soil and the pile interaction. There are two famous theories of methods available to analyze this kind of situation. For clay is the Matlock method, for sand, the Reese method. Okay, those two methods I will talk a little bit later on when we talk about how do we consider skull hole effect. So now let's move on to the lateral behavior of a single pile under skull condition. We have done a few things here. I list the stuff here. One, to investigate the effect of skull hole dimensions, use the physical model test, basically the reduced scale model, and then use numerical analysis method to expand the physical model test, and then develop a simplified method for people to use. Okay, but this is the one thing we try to consider what the effect of skull hole dimension. Another thing we also find very important is the effect of stress history change, because the removal of the soil, just like an unloading situation, the soil may change from normally concentrated soil to over concentrated soil. But that also affects the behavior of the soil response. For most cases, really you have both together. How do we consider the combined effect in the real design? We start with the physical model test. This is a physical model. We started to investigate the global scale. Basically, said all the soil removed uniformly, and this is the initial result skull depth, and then a little bit 0.1, 0.2, 0.3, and until 0.5. Then we measure the load deflection. From there, we can determine the lateral capacity. I define the lateral capacity ratio as the capacity with skull depth divided by the one without skull. Okay, I got the measure data. Then we compare with the Bloom's solution. Okay, there's a design chart, and the Bloom's solution basically consider eccentricity. Okay, you basically change eccentricity to simulate the skull depth, and they basically match very well. Okay, match very well. In other words, if we just design for global scale, we can use the current method developed by Bloom's to calculate the capacity of the pile subject to lateral load. Now we also put the strain gauge around the piles to measure the bending moment. Here basically show you the bending moment, and from here, as you can see, this is the increase the skull depth, and when you increase the skull depth, actually the bending on the pile getting smaller. The reason because the soil will not resist the pile movement. Okay, and the maximum moment go from the top to down, of course, because if you excavate to this point, there's no resistance. All the things will be resisted at the bottom. This is the way how that change. Okay, but from the physical model test, even though it's a reduced scale, we can observe some phenomenon and useful for us to do more research in the future. But we also investigate the other facts. basically skull slope. Like this one, this is a flat 15 degree, this is 30 degree. Here basically show you some model, as you can see here. That's the way how we generate the skull hole, okay? But we also have the bottom width. This is the bottom width equal to 0. But we also have a bottom width, and you keep increase. And then if everything removed, that becomes the global skull, okay? That we can investigate the skull width. At the same time, we of course investigate the skull depth as well. But all those things, basically, we are investigating regarding skull hole dimensions. Then we show you some results here. Okay, this is the one. How do we apply load? Actually, we just use a pulley and put the weight there, and then we measure displacement of the pile. Okay, so from here, first thing, we fix the skull depth, but change the slope of the skull, and we find out this is a 0 skull. What that means is 0 degree. 0 degree basically the global skull, completely remove of soil. Then if I 15 degree, 30 degree, actually that's not much different. But by increase the degree, you increase the response of soil. The reason, because you increase the slope, but basically you add some kind of surcharge on around the edge of the pile. This is why I increase the capacity. As you can see from here, of course, if you increase the skull depth, will reduce the capacity. But at the same time, if you increase the slope angle, and the capacity actually will be increased. Okay, so that is a situation when we have a bottom width equal to 0. Okay, now let's take a look at other phenomenon, basically skull width. So we start with the skull width equal to 0, and they keep increase and increase. Then we fix the slope angle. Okay, but at the same time now, for this case, we only we keep the also skull depth the same, only change the width. From here, as you can see, if the width, increase from 0, just like this situation. If 667 millimeters is a complete remove of the material. Okay, as you can see here, when you increase the width, basically reduce the capacity or increase the deformation. Okay, then also from here you can see that as well. Okay, and basically increase the width, the capacity will be decreased because you basically remove the surcharge around the pile. But we also did the cyclic loading as well. Basically, we just pour the pile in this way and pour the pile another way. I tried to see how the pile will respond. We fix the bottom skull width, fix the top skull, and but we changed the two slope. But this one is a small slope, basically flat. But this is a 30-degree slope. Now, one thing I need to point out, the repeated load capacity is equal to optimal load capacity divided by 2. But for the one, as I point out, that with 30-degree slope, actually the capacity will be larger. If larger divided by 2, of course, applied load will be larger. This is why for the degree one, the deformation larger than the 0 degree, the force applied for this was higher. But one phenomenon is very interesting. As you can see at the beginning, this deformation is larger, getting smaller, smaller, smaller. And in other words, really the soil is densified during this repeat loading process. Okay. Now, the things we are dealing with here is dry sand. Okay. Now, as the previous presentation showed, that if we have a cyclic loading, you may have a liquefaction. But that was not investigated in our study. Okay. Now let's move on to talk about numerical analysis. We use the FLAC 3D finite difference software, and this is the basic cone shape scour. And then we basically investigate all the factors as I mentioned early on. Mentioned the bottom width scour, the scour depth, the scour slope. But this time now we change the soil from sand to clay, and then investigate all those factors. Okay, but I will show you some results. Because of time, I cannot show you all the results, but I try to make some comparison. Now, unfortunately, we use two different dimensions of the of the pile diameter. For clay is 0.3 and this is 0.6. I haven't really changed this to dimensionless. They make it a little bit difficult to compare, but I already scaled that. Okay, I scaled. You see, this is 300, this is 150. But from here, as you can see, the sand, okay, actually has a more effect by the skull depth than the clay in terms of the variation. Okay, as you can see, skull depth 0 to 8Ds, you have a wide range of change. This have a little bit less change. Okay, you will see this kind of trend later on for other factors as well, and then I will conclude why is this the case. Okay, the pile in the sand is more sensitive to skull depth effect. Now let's take a look at the PY curve as I mentioned earlier on. Okay, from here, PY curve basically P is the soil resistant, Y is the basic deformation or displacement. We fix at the same depth, okay, from the soil, from the bottom of scour. That you see the same variation because the scour much more than the clay. Okay. Again, pi in sand is more sensitive to scour depth effects. Then now we change it to the bending moment. Okay. For the bending moment, we find out it's a little bit different situation. Actually, this depth limitation, now I haven't scaled again, actually is a little bit smaller depth in sand, but larger depth in the clay. Again, the reason because for sand, when you increase depth, the stiffness will increase. For clay, the modules increase is not much as the sand. Okay. But that is the reason why if you remove the soil, you release the stress, and then you basically reduce the modules of soil to resist the pile ladder deformation. But if we look the slope, okay, this is the width, skull width. Again, we see the more effect in terms of the skull width, because if you increase the skull width, basically you kind of remove the surcharge. Okay, for sand is more sensitive to overburden stress. As we know, for the more current theory, we have a cohesion plus normal stress, then tangent the phi. If you change the normal stress for friction angle soil like sand, will be very significant. But for clay, it's not very significant because friction angle almost goes to 0. Okay, but this is the reason why for sand is more sensitive to scour, but clay is less sensitive to scour. Now, but here basically shows the slope angle change, which shows a similar situation here. As you can see, from 0 to 40 degrees, we see some difference. But if for clay, change from 0 to 40 degrees to even 60 degrees, and the change is not much. Now, we didn't do 60 degrees because that will exceed the friction angle of soil that you will not be able to do for sand, but you can do for clay because of the cohesion. But again, show the pi in sand is more sensitive to scour slope effect. Okay. But after we understand that, now we try to see whether we can develop some kind of simplified method to consider scour hole effect. But this is the basic model we proposed several years ago. Basically, for a PY curve, there's 2 different failure modes. One is called near surface failure. One is below surface failure. You need to check both failure to make sure which one is a lower capacity. Okay. But this is the one basically include the scour hole. Okay. But we don't have any solution for PY curve with scour hole. But we try to use a conventional PY curve, look like it's on the right side. Okay. Basically, we solve the equation based on the force equilibrium. See how much capacity, how much force you need to fail this wedge, and how much equivalent this. That basically you can determine what the equivalent depth of the one without scour hole. But if we know that, then we can use the current conventional method, like a Reese for sand, to determine the PY curve. Okay. One thing I will point out for sand, as you can see, there's an angle here. Okay. If we move to clay, you don't have the angle here because this is depend on the friction angle. Okay, that is the key, basically the equivalent force to determine the equivalent depth. Here basically shows the force derived from this equation. And then from there, if we know the equivalent depth, we plug in those formula. Those formula came from the Reese formula. Then we can calculate what is the pressure. And then from that to determine what is the minimum pressure for the depth. And then we can calculate the PY curve modified, consider skull hole. Okay. Okay. It sounds like a very simple, but that's only simple if your K is constant. But in reality, the PY curve is K basically is not a constant, it's non-linear. How do we do that? It's very difficult to do hand calculation. This is why we need to develop a software module to do that. Basically, the basic concept now, this is like a PY curve. Then we divide this into different segments. For each segment, you have a K. Okay, that K is kind of constant with this segment and the constant with this segment. Of course, if you divide to more segment, basically you will fit the curve perfectly. Okay, but that only can be done through the software. This is why we develop a software, and to do this, the software basically to do the non-linear conversion of that. Okay. But if we calculate the stiffness, then we can use other software like structure software to structure analysis. I will show you this later on about this software, but at least we can show how they compare with our numerical results. Here, basically, we make a comparison. I already show you some results from Flex 3D, and then the compare with the SSM. Basically, this is a simplified soil model. And for different kinds of situation, basically very well. Okay, to verify the simplified method is pretty good one. Okay, now move on the clay. As I mentioned, for clay, because the friction angle equal to 0, then you don't have that angle here. Okay, just like this. Then we can use the same approach. Now the formula will be different. Okay, now we use the Matlock method, but the concept is the same. We use the same force to equivalent what is the depth, then use this one to original Matlock solution to determine the PY curve. Okay, but all those things are already published in the paper. I show some of those here. But we also make a comparison between the numerical analysis results and the simplified soil module, and they match pretty well with that. Okay, but there is one issue. That all the things that we have done so far without consider cause stress history effect. Okay, as we know, the soil has a memory. If the soil originally at this location, this point already subject stress gamma z initial. Okay, if this soil is removed, basically the yield stress or pre-consolidation stress still is this one, but now current stress is lower. Basically we change from the normal consolidated soil to over-consolidated soil. That will change the behavior of the soil and also change the property. But that's what we try to consider for two different kinds of soils. For sand, that may change the friction angle, change the unit weight. As we know, if you remove the soil will start to rebound, will reduce the unit weight a little bit, may also affect the modular subgrade reaction. Okay, that is the K value. We talk about spring stiffness. For clay, we're dealing with Andre shear strength, and it may change the unit weight, or may also change the modular subgrade reaction. Okay, so let's take a look. The concept basically we use similar like a chem clay concept. You have the stress initially here, and if you remove the soil, you have a rebound line, and you come to here, right? And then we try to see how that affect the friction angle. So this is one formula, okay? It's a very famous formula, and Bowden proposed the formula. Basically depend on the relative density, and also depend on the mean stress, okay? But here now, if you remove the soil, you will change the mean stress, and you also will change the relative density. You will change your friction angle. okay? And another thing, this is dealing with the unit weight. If you change your radial density, then you change your unit weight. Let's see how do we do that. Here first, it's very simple. You have an initial stress, subtract how much you remove. They plug in here. You will change that, and also we change the OCR as we talk about, right? And the density also will plug in here too. Now, this formula, as you can see, this can reduce. So angle will get reduced, but you minus the small one, and the angle will getting larger. Okay, that really depends on which one has more effect on the friction angle. It's difficult to see from here, but I will give you an example later on to show you how they affect. Okay, for unit weight, it's very simple. If you do not remove soil, the unit weight will getting smaller. Okay, then how they affect the PY curve, those formula I present earlier on. Basically now you change the friction angle, change the unit weight. Of course, you will change the P ultimate and it will change PY curve. Another thing, we change the K value because now you have an OCR. If we assume initially is the OCR equal to 1, now you have a high OCR. Okay? Those are all the theories. It's sometimes very confusing with theories. So let's take one simple example and see how they affect. Okay, so we pick up one example actually used by Rees, but we added the scour there. In the Rees study, there was no scour, but the soil property from his study. Let's assume like a 3 meter scour. Then how they change the property of the soil. So here basically show you, and this is the initial friction angle. Okay, and then this is after scour, the friction is getting larger. Okay, and when you get it deeper, the friction angle increase getting smaller, and the unit weight, of course, there's a change as well. Okay, therefore you have an OCR here. Okay, increase that. So basically, after scour, the soil friction angle getting increased. So how that affect the PY curve? Let's take a look here. If say this is the one before scour. Okay, those two lines are basically after scour. The one say unmodified means without consider stress history. The modified ones consider stress history. I take the diffraction like a 10 millimeter going up here, and I can determine what is the resistance. For the case, this is basically unmodified without the stress history. After this one, basically you almost double the resistance. Okay, how that change the deformation and the load curve. This is the load applied on the top. This is the deformation on the top, and those are the basic ones without scour. Those are with scour. As you can see, after you consider stress history, okay, and this curve become more stiffer. Basically, becomes stronger and also stiffer than the one without consider stress history. But in other words, if we ignore the stress history effect, it is conservative. Okay. But consider stress history resulting in high lateral soil resistance, those reduce lateral displacement. Now let's take a look at the clay, how that will happen. But we use a similar kind of concept, but now we have a CCC response, and we have a point here, and then start to rebound to here. But this formula very similar things, but the important things are dealing with this one. Okay, the Andreas stress strength is correlated to normal stress and also correlate to OCR. Okay, based on the ladder solution for the Andreas stress strength. And then we use the Matlock's theory we talked before to different failure near the surface, failure below surface, and we still can generate the optimum capacity. Plug in here, we can get it called PY curve. Okay, those are the theories. It's difficult to tell what kind of effect. Okay, this is the cohesion here. This is the normal stress change, right? Because if you remove the soil, okay, cohesion here. Take the case from Matlock. Okay, we use Matlock's soil properties, high properties, but we excavate down for 3.2 meters. See how that affects soil properties. Here you can see this initial unit weight that's effective like 10. basically you get a reduced a little bit, okay? And this is the cohesion initially. And then you surprised to find out actually the cohesion get reduced, okay? So you can see decrease the unit weight, decrease the cohesion after remove, even though the OCR getting larger, but the actual cohesion getting smaller, okay? So how that affect the behavior? Let's come back to PY curve, okay? So I take the same deformation. This time I take a 50 millimeter, and this one is unmodified without consider stress history, okay? And I got this resistance. Then how about this one? This consider stress history, and I got the less resistant, okay? So if we come to the pi load deflection, this on the pi head, we found a similar situation here now. And basically, the soil getting weaker, and at the same load, this is considered stress history. This without consider stress history, okay? But basically say consider stress history result in smaller lead soil resistance, those increase the lateral displacement, right? But now if we ignore the stress history, it's not the same. For two different soil, the behavior is complete opposite, okay? Okay, I basically present those two separate, right? We consider one skull hole effect without consider stress history. When we talk about stress history, basically consider global skull is a horizontal removal of soil. But in reality, actually you have the removal of soil, and also you have the skull hole effect. But this is a kind of new study. Dr. Lin, he was my former student, and after he went to Victoria University, become faculty in Canada, and he continued his study with his student. That came out a new idea. I thought this very clever idea. I want to share with you. That if we have a point that just use this middle point as example, that we suppose it can calculate the overwhelm stress without the consider surcharge, okay? That basically is effective unit weight soil times the depth, right? That we know that overwhelm stress. Then we treat this soil as a surcharge. And then of course you have additional load come from both sides. You come to here. Now this is a cone shape, and I only show you the cross section. That if you derive it, then you come to this formula, okay? That you have the overburn stress from the one after scour, and then you have a surcharge from the soil remaining, right? That we add it together, that will be the stress here, okay? That stress you can use for the stress history analysis, right? Because you have the original stress, also gamma z from here. But this is a new stress that you can do analysis, and also you can come out the equivalent. This is total stress divided by effective unit weight. That is the equivalent depth, okay? This depth can be used for PY curve. So now we combine both effects in the same analysis, okay? So you can use for stress history analysis, you can use for basically PY curve analysis, consider skull hole effect. Okay, so basically idea is like this. You equivalent eventually to horizontal, but now the Z is different. That Z is different from that Z, okay? Or from original Z. But that is the case, basically you do analysis, okay? But this analysis considers stress history and the skull hole effect together. Okay, how that really affect the results? I use the results from Professor Liang from Tongji University in China, and he did some kind of comparison. And say one case only consider stress history. Okay, this is the skull depth increase. As you know, skull depth increase, the pi head diffraction increase. We already talked about this for clay. Okay, if you consider stress history, and as we talked about before for clay, if you consider stress history, it becomes softer. In other words, you have a more diffraction, okay? And then this one, the solid one here, is consider stress history and the skull hole effect. Now the blue one basically only consider skull hole dimension, okay? But from here, studies show the stress history actually is very important for clay, but the skull hole effect is not that important as as we talked about earlier on. Okay, but this is really consistent with what I discussed earlier on. Basically, for clay, the overburden stress effect, the scaffold effect is not that important, but stress history effect is important, and also will increase the deflection because of the reduction of the Andre shear strength. Okay, now let's move on to talk about the pi group effect, lateral behavior of pi group. But also I got some results from Dr. Ling and with his student. But now we have like 3x3 piles, and then we have the basic pi group. You need to get the equivalency. That's a little bit complicated procedure, depending on the flow rate. I will not get into detail about this. Then this is a group, pi group, and you have the basically the group local scour, and you have the width, you have slope, you have the depth, and this is like a single one. And they adopt a similar kind of approach, basically use the middle one as the calculation. Okay, now this is a kind of assumption, of a major assumption or approximation. And I discussed with Dr. Ling, they probably will keep improving it, but basically concept is very similar. Then they derive the equation based on that. And this is the overburden stress, the addition stress from this one. And then you basically equivalent the depth again with the PY curve. But for group effect, there's more than that. Now for stress history is very similar, like a single pile situation. But for the group effect, there's more than that. Okay, now let's talk about those things. Here basically show you the PY curve. I have 3 different situations here. Let me show you. First, we started with a single pile. We got the first curve here. That is a single pile without scour. Okay. Then if we have the second one, single pile with scour, and then we need to modify a factor to reduce the resistance. That is basically a single pile with scour. Okay. But that's not enough for pi group, because if you have a pi group, there's also stress overlap between each other. When you push this one, you have a leading pile, you have a trade pile, you have a middle pile, and there's another reduction, basically FM. That's a reduction of a group effect. Okay, you reduce to that point. That will be the one eventually used in the analysis. That will be the pi group under scour condition. Okay, but they did some numeric analysis, try to see how the way they propose will match with the numerical results. This is the model use finite element. Okay, without scour, this is with scour. As you can see, here's a cone shape, and there is a 0 scour width from the edge, and then the scour depth, and then this is scour slope. And this is the one when they push laterally, try to see what the horizontal displacement. As you can see here, there's a change of the horizontal displacement. And this is after scour, and there's a stress or deformation contour here. Okay, but they were able to basically predict the lateral load and the displacement in the pi head. And as you can see, this is a pre-scour. The resistance is high, but when you increase the scour depth, and then of course the load resistance gets smaller and smaller. And then the solid one is a numerical analysis. The dashed one basically proposed the method. As you can see, I mean, generally basically match with the results, but I talked with Dr. Rain, and they tried to continue improve it, and I didn't use all the results, but actually overall I think I matched the results with the numerical analysis with their simplified method. Now let me move on to the last segment. I think I'm also kind of running out of time. There was a lateral behavior of pi support bridges. This is the real situation. All the things I talk about, individual pi group, the people say, how do I use it for real project? Okay, but we did some study, also published a paper back in 2012. And this is basically show you how do we combine the soil model with the structure software model. Okay, But on this left side, basically this is a before scout. Here we now have a bridge girders. Then also we have the abutment support at two sides, and also we have a pier, and then all those like things basically spring. Okay, those are spring basically to simulate piles. Then after scout, what happened? We just remove the spring, and that's how we model in the structure software. But here, as you can see, there's a skull depth. Okay. Now let's see. Here, basically, the model I just showed you. As I described to you before, we have the soil model, and we input the information about the soil and the profile, and then we do the analysis. Okay. Eventually, I showed you this before. That we can generate the K value, basically stiffness value, okay, and then we apply back to this structure software, and then they can run analysis for the whole structure, include the pile, pier, bridge deck, and abutment. Okay, but this is a close view. As you see, each one basically is the steel, basically is a spring. Okay, let's take again. We want to take a real project as example. It's easy to illustrate. This is a project in Kansas. We have the pile, and for this case, then the pier is not a uniform cross section. That we basically divide into the segment, and those are the H piles we convert. And basically, what we analyze here is to simulate the skull depth. Okay, we assume there's a skull depth, how much, and also we consider stress history change by remove the soil, as we talk about. Now, in this analysis, we use the global scale. We didn't use the local scale for analysis. And another thing we didn't consider here, the pi group effect. Okay, now we could consider that, but in that analysis at that time we didn't consider. Okay, just make that clear. But for the loading condition, we consider self weight of a bridge, and consider the wind pressure, and consider water pressure, also with the breast. Okay, we use the AASHTO standard, and also we have the upstream and the downstream, because the flow we have two piers. Okay, that also affects the performance of the piles. Here basically show you we did the analysis for two different kinds of soil. One's for sand, one's for clay. And here basically show you again, if you increase the skull depth, of course the pi cap deflection will increase. And then here now we also consider, as I mentioned, consider soil history effect. U means unmodified without stress history, and with stress history. Okay, but this is dealing with the clay situation. As you see, if for clay situation, if we consider stress history, the deflection will get you more because it's getting weaker. Okay, but we also have the pier deck deformation, and we also to analyze abutment. That we find out the abutment actually carry a lot of load. Okay, basically the load eventually will transfer to the end support. Okay, but also we calculate the bending moment. But this is for sand, as we talked about before. Now for sand, actually deflection getting smaller because sand will increase friction angle getting smaller. Okay, now even though it look like the magnitude is very small, but because the bridge support is much stiffer, basically carrying a lot of load to help the pile to support the load. But that reach to the concluding remark for my lecture. That I show you the experimental and the 3D numerical method were used to investigate the effect of skull holes on the response of the pile in sand and or clay. The skull depth is the most important influence factor. Okay, skull hole dimension have a more effect on pile response in sand than in clay, as I explained to you. The stress history has an effect on the response of lateral load piles by increased OCR and reduce the undulation strength of clay, basically reduce resistance, or increase friction of sand, basically increase resistance. Okay? The simplified method consider effect of skull hole and stress history were developed and their results were well compact with numerical results. Now, design of pi group under skull condition should consider 3 facts: skull hole dimension, stress history, and the group effects. Okay. Then lastly, integrate analysis program for lateral behavior of pi support bridges under skull condition were developed. The analysis results shows the skull reduced bridge lateral resistance. Okay, and also the soil stress history effect was limited because of the interactive effect of bridge structures. Okay, but I'd like to thank my former students, as I mentioned, Dr. Lin and another master student, Omar, and most of my presentation based on their work. And I also corroborate with my colleague, Dr. Burnett, Dr. Parson, Dr. Paul, and Professor Liang from Tongji University, and Dr. Li from Wuhan University of Technology. And most of the work was sponsored by the Kansas Department of Transportation. With that, thank you very much.
Thank you, Professor, for a brilliant presentation. You're known for your brilliant presentations. I met you so many times. Amazing. And your work on geosynthetics is fantastic. So I just will go for some questions here. One is from Mr. Maurya. The angle of internal friction is shown to be increasing for top layers of sand post-score due to Hosier effect. Whether the stress relief due to score would not have any effect. The effect of stress relief is asking.
Can you say again? I couldn't hear very clear.
Yeah, okay. The angle of internal friction is shown to be increasing for top layers of sand after post-score. Will it not, the stress release effect, will it not have any effect? That's
okay, I think I got that. The friction angle effect is more important at the shallow depths. Okay, when you're getting deeper, the overburden stress getting larger, the friction angle effect getting less and less. That's right. Yeah, that's also what we show in our example.
Okay, so the other issue you're trying to clearly bring out that the the integrated effects in the integrated effect are completely slightly different from what is considered for individual cases. Why is it so? Of course, is it a compensating or something? Because
yeah, I think the reason because the bridge itself in that model is very stiff, very strong. The pile effect in the overall for the lateral load. Basically, if you think about it, the top is fixed, bottom is fixed, and even though you remove the soil, the deformation will not change much. You see what I'm saying? But the top of you fix into the bridge deck, the bridge abutment. The bottom you fix in the we have a rock in the bottom, and then if you even remove the soil, kind of between. The effect is not as significant as what we see for the single pile or group pile without the bridge structures.
Yeah, one last question. Actually, all your findings are all codified or in a consolidated form, because in India we have a lot of issues on pile design and score. We have a lot of agencies. There's a lot of contradictions in codes, and a lot of consistency is required. Maybe your codes work best on your codes, maybe of some use to us. Is it codified or somewhere in years or something?
You talk about the software we develop?
No, not the software. The findings that you did. Is it in the form of a consolidated report or something for bridge score, or so that it can be used by regular practicing engineers?
Yeah, I mean, we publish quite a few papers, and I provided in the presentation. And also we try to help the engineers. This way, develop a simplified method. Okay? And the simplified method, of course, is verified by numerical method. But we don't suggest you use numerical method. Actually, simplified method would be good for practical applications. Yeah. Okay.
Thank you, Professor, for a brilliant presentation as usual. And I just now hand it over to the organizers. Thank you, Professor Reddy.
Sir,
back to you.
Sir, thank you very much, sir. for effectively organizing the sessions. I thank Professor Jihan for giving a very interesting lecture on behavior of piles and pile groups, supporting bridges subjected to erosion and scour effects. So this is very apt for Indian conditions, because in many locations we are facing the problem of scouring. So you have addressed the issues related to response of pile and pile groups in clay and sand. Thank you very much, sir.
Thank you.
Now we'll move on to technical session 2. So this session will be chaired by Professor G.V. Ramana, Head of Civil Engineering, IIT Delhi. In this session, we have 2 lectures. The first one to be given by Professor Issmge, Vice President Asia, Issmge, from Incheon National University, Incheon, South Korea. He will be delivering his lecture on the topic of construction design of geotextile tube for shore protection. And the second lecture is by Professor M.R. Madhav, Emeritus Professor of IIT Hyderabad and AICTE INA Distinguished Professor at JNTU Hyderabad. The topic of his lecture is cover mitigation, predictions and limitations. I request all the participants to mute their audio. Okay, thank you. So, with this introduction, I invite Professor G.V. Ramana to chair the session. As a formality, I'll briefly introduce him. Professor G.V. Ramana.
I think we are behind schedule.
But
So
it is very short, in short only.
Okay.
Professor G.V. Ramana is graduated from Nagarjuna University and then obtained his MTech from IIT Madras, and later obtained his PhD from Rensselaer Polytechnic Institute, New York. And he has been working with the Department of Civil Engineering of IIT Delhi, and presently serving as head of the Department of Civil Engineering at IIT Delhi. He is specialized mainly in geoenvironmental engineering, geotechnical earthquake engineering, waste mechanics, and ground improvement. Throughout his career, he has worked as a consultant and expert on various geo disasters, their mitigation and remediation. With this introduction, I invite Professor G.V. Ramana to chair the session and conduct the proceedings. Please, sir.
Thank you, Professor Reddy, for a long introduction. And Professor Issmge is going to speak about the first lecture on construction and design of geotextile tube for shore protection. Professor Issmge is very well known in India. He is is currently the Vice President Issmge for Asia. After graduation from Korea, he went to United States for his master's and PhD. He has several laurels to his credit. He has been teaching, and he has, for the last 26 years, published several papers. And he was honored by Incheon National University with several accolades. So to keep the time, let us invite Professor Shin. Go ahead, sir. Professor Shin, we are able to see you.
Hello?
Hello?
Yeah, you should release. You should release.
I released, sir. Go ahead.
Can you see? Can you see me?
Yes, sir. Yes.
Okay,
no,
no problem.
I'm able to see your screen.
Oh, but I tried to connect to the video, but your central control is rejected.
Professor Reddy, I think he is having trouble.
We are able to see his presentation.
No, he would like to turn on his video as well.
Okay.
Sir, it's not possible, sir. Only we can see the presentation, sir. When you're sharing the screen, only we can see the presentation.
Sharing. So can you see me?
No, not
No?
yet.
No, sir. Your presentation is visible, sir.
Okay. Yeah. My presentation is there, right?
Yes.
Okay.
You
Shall
can
I
start,
start?
sir.
Okay.
Yes, please go ahead.
Yeah. Thank you very much for inviting me to the ISSMB TC 213 scarring and also erosion. And the topic of my presentation today, construction and design of geotextile tube for shore protection work. The content is the background of my presentation today, and I'll go to the some preliminary background of the erosion problem in the various country and the various situation, and also the steps of the the design of a geotextile tube, and from the shape analysis and the stability analysis and the functional analysis. And I'll present several case history of the utilizing the geotextile tube for shore protection and the construction of the platform for the bridge pier foundation work. See, this is a map of Seoul and South Korea and North Korea. So I'll talk about shore erosion problem. Somewhere Busan is right here around southeastern part of the Korea, second largest city. And I'll talk about another project in the somewhere here, Jumunjin Harbor rehabilitation work, and somewhere the Woolchin, and some erosion problem somewhere in the west coast, and some project in the this part, the Semangam area. As you see here, 1970s, we have a pretty good, the seashore line and with the beach area, but now we found out there are of erosion problem here, and this is a.
Sir Shin, sir,
Yes?
it is Reddy. Sir, you kindly turn on your video so that you will be visible to all of us. Your video is not on. And then you can continue.
Okay. Good.
Yeah, now we are able to see you, sir. Okay.
Yeah. Thank you.
Okay,
So this is another, the same area in the Busan area. We had a lot of problem, and we normally constructed jetty and the FAP for the ship embarking like this. But we have a series of the erosion problem. I see that around here beach area, there used to be maybe here maybe around the sand around there, but some erosion happening, and also our country in the east coast, we have a heavy sea wave attack, and after the monsoon, and we have a lot of coastal erosion problem, and I think this is the west coast. We rehabilitate this beach area by using the geocell here. And this is all the photographs. And in 1971, we have a shoreline, pretty good shoreline, but compared with the 1991, there's a lot of, some particular this area, we have some series of erosion problem, and the Gangneung city, east coast, because east coast has a very deep sea and also has a heavy wave attack, and the sand particles migration right by the arrow direction, and see here a lot of scarring problem around here, and sometimes scarring problem happened due to some people they dredging the soil and they obtain the sand, for the construction purpose. Particularly in the west coast of Incheon, we have a serious problem of that. Because of that, we have sand migrate to the deeper area, so that another problem happening. And this is another origin, east coast, and we had some right here. We used to have a coastal line, red black dot, but so now is coastal line is retreated, so it's this much of area as eroded in the past 15 years. And this is a view of Japan, and you see the coastal line as this much of the sand beach is eroded, and this Ibaraki area, I think this is the west coast, and this is maybe Pacific region, and we have a series of the erosion problem. And I think it's Mr. Albert Lim Kong will maybe talk about this phenomenon in the Malaysia, and there's a heavy attack, the coastline, and with the installation of the geotube, they can rehabilitate all the beach area and extend it pretty much. I think I reviewed this paper for the Journal of Korea Civil Engineering, the Society Journal for this. I think Mr. Lim will talk about it. See, the problem is conventional method of the construction of the embankment along the rivers and the creek that has a hard imposing structure. So sometimes some country like Incheon we have in the Singapore, and some countries, they don't have much of the stone or rocks around towns. So there's scarcity of local raw material, and also lack of aesthetics, so and time consuming for construction. This, what's the alternative, new solution? So, and which is a much cheaper way to this, and maybe quickly we can construct this method. Maybe geotextile would be good solution for this alternative, the method, so that many of you know maybe geotextile tube. This is like a sandwich, not sandwich, sausage type, of the tube that made of that polypropylene, PP or PT, but we prefer to use the PP mat, and we dredging the soil and fill in the this geotube inside, and we have inlet, from time to from place to place. And normally we utilize dredging the soil, and so that this geotextile tube can be designed to any form of any size for required, and it can quickly fill the this very lengthy, normally 50 meters of this, the tube, and the width maybe diameter maybe 3 to 5 meters. And also this tube material can fabricate in the factory, so we can have a good quality and the consistency of the textile. And I think it has been used a lot in the last 40 years. First initiated in the Holland, I think, flood control, and also they use in the U.S. Army Corps of Engineers. They use this method for rehabilitation of the Mississippi River, flood problem, and some New Orleans somewhere, and also it can replace and repair the expensive conventional, maritime structure like TTP, and also contain isolation on unacceptable soil, the spoiled soil, and maybe like a polluted soil. Maybe there would be good methodology, the discharge of this with this container system. This is a France, and if you visit maybe Nice and somewhere, you will see the lot of coastal erosion problem, and also the Spain has also a lot of problem. I think Korea we had a project to investigate why is the region of the coastal erosion that's very severe, I think the past few years. I think I took these photographs here. This is a view of the Padang, West Sumatra. I think they have a serious tsunami somewhere, here a long time back. My friend has a house, the building has a higher than, 10 meters. So whenever tsunami, something warning coming, and they climb up to the third floor of their flat. This is groins and along the coastal, all the way here, you can see. And here, all the groins here. And I enjoy, visiting there. So this is schematic diagram of the groins, and the bottom part, mostly that medium sand size. And also because they did some experimental work to find out the bearing capacity of this mound, and there's a bedding stone as a rock armored around here, all these the groins. And here the Barhead Island in North Carolina. I know this is a very nice beach, and I call the playing golf. But unfortunately here, a shark, they're appearing and beating, 8 years old every they have here, but they, to protection of the shoreline and the beach area, they use the groins. And I collected all the data, so far 2000 year to the 2011, and the number of research and also real project implemented by utilizing the geotextile tube. So we have a pretty good result. And here we have the rehabilitation work of the Yongjin Bay I'm going to talk about, and also some this also I'll show you that discharge of the hot water from the new nuclear power plant. And also we had some Grand Bridge, the project for the temporary working platform, and also Incheon Grand Bridge near to our university. And we have also the Semangam sea dike. We have about 35 kilometer long, sea dike, and we use a geotextile tube. And here also Busan, Newport, we have 3.3 kilometer. And we have a Busan, another port, we have a couple of, and the last one, we had some, the project, so I think the waste, like lime sludge, the big amount of waste in the South Coast area, and the leachate is migrate out to the sea. So we want to prevent like a barrier system, and we constructed the twin, the geotextile tube to prevent for that problem. So when you do that, research work of the geotextile tube technology, so we should do first shape analysis, and 2D and 3D, models, and we can formulate and the shape which we want to design, and also we check the field model test and the monitoring, and also that we should consider very seriously about filling soil. Maybe clay is some problem, of the consolidation, also a sedimentation problem, but the soil sand would be very good, So we got to do, preliminary soil lab test for settling, and also self-weight and consolidation test, because we want to shortening time, and we want to have the higher ratio of the filling of the material inside of the tube. And we wish we could do some hydraulic model test. I know the Corps of Engineers, they have a very big hydraulic model vaccine, so they can simulate, which is the real situation in the coastal area. And we can have an empirical equation and also stability analysis for the overturning and the sliding and also bearing capacity. And also we should consider that functional analysis and the show protection and erosion control and the seabed soil migration. I think so we basically we first of all we should the check over the mechanical performance and tensile strength and also elongation. They all these one yes, and also hydraulic performance like permeability and the dynamic loading resistance and so on. I think this is one of example of this, and this is a view of the tensile strength test with the wide stripes, and this we have in our laboratory. Have a machine. We can feel the the sample of the geotextile tube and put it inside in the box, and we feed in the soil which you want to use in the field, and then we plunge it up and down and fluctuate. We obtain the water and see the suspended solid. We don't want to have a lot of suspended solid around here. They may be polluted in the seawater, and check the clogging problem of the geotextile. And this is a small the shape, and this is a tube and the schematic diagram. And so we usually use the first stage of the design and to use the Rejinsky, Professor Rejinsky, he developed the GeoCorps program. So 2D, we can find out the tube shape with according to the hydraulic pumping pressure, and also the dimension we did using the abacus and to the shape, and this is more similar to the real situation, and we see analysis like low the Young's modulus and the higher Young's modulus. We checked it with the hydraulic pressure, and we this result we compare with the field model condition, and I think there's a good agreement with that. And this we use the flag, and we see the vertical settlement or displacement, and because this is important when you have 3 layers of geotextile tube, we have a planned the ground level, but after you constructed the geotextile tube, there may be sometimes that too much settled, so we cannot reach to the required that height of the embankment. Then we have a big problem, too. And also we need that global stability. When you have this is, let's say, geotextile tube, and then there may be you need to find out factor of safety for against sliding. So this is sometimes serious. I think we have a very high value of the global stability. And first of all, we obtain the sample for the filling material and check the consolidation test and sedimentation. It takes about 2 hours, 3 hours, to reach to the primary consolidation. But this one is more likely silty sand, but this one is a more silty clay that takes 4 days. So this material maybe has a problem using as a filling material. Let's see the stability analysis of geotextile tube. And first of all, we need check the sliding with the wave attack, and also the overturning problem and the bearing capacity problem also. I think some I think Professor Chu, Jin Chu in the National University of Singapore, the Nanyang Institute of Technology, he reviewed, one time he researched on the bearing capacity problem. And now National University of Singapore, Professor Chu, he does some research work on the relatively small size of the geo bag. for using the embankment of the Singapore that port area, and we checked the hydraulic model test, and also we did some the numerical analysis for calculation of the sliding. So as you see here, we have two different module. One is a single tube, the other one is a double tube. Okay, and also filling material. As you see here, 85% of filling soil, 90 and 95. So that tube, the less filling and a little bit flat bottom, so which has a higher friction compared with the full filling the tube. Full filling tube is more rolling, when the wave attack. That's why here all the tube and 85% of the filling material of geotube, which gives the higher, factor of safety for the sliding and overturning and also bearing capacity. And also we see the tensile strength. Sometimes if you put it, too much high pressure of the injection, there may be rupture, inlet, particularly inlet, they ruptured, we experienced that. So we should control it for that. And also the permeability, So we did use that PET, the geotextile for the geotube. We had a problem for the drainage, but the PP has a very good result. And also we have some two types of the geocops, analysis. And let's say we have maybe 2 stacks of the geotextile tube. Of course, we should check that the sliding for the top part and also overturning and the overall part, that 5 meter height, and we check the that factor of safety for each analysis for that. And I'll move to the real case history of the geotextile tube application. In here, Korea located here, and India is far here. And we're talking about here east coast of the Korean peninsula. And so we have here the blue color, and which indicates of the cold water, cold current from the here Kamchatka or northern part of the peninsula, and also warm current coming from south to the to the north, and they connected together here. So that's why we have a lot of the erosion problem, and the storm comes and so has a problem like here. Maybe you carefully observation of the top of this wall. What is this? Barbed wire. That means this location near to the demilitarized zone boundary between North Korea and South Korea. So we want to protect our land coastal line for infiltrators. So we have, barbed wire on the top, So this is a situation, but we have like this, big, serious, scarring problem. So we want to rehabilitate, this beach area. So one proposal we propose in a growing system here. I think this is one of alternative. And another alternative we use, like this submerged breakwater system with the parallel against the coastal line. And we want to check with the TTP in a breakwater system. So finally we analyzed by several reasons, and we adopted parallel the geotextile tube installation. And we had several benchmarks, and we have twin tube from our experimental work and hydraulic model test. We found that twin tube is a much better performance against sliding and also, and we find out, so depths of water which would be suitable for this against our analysis. So I think it's from their coastal line about 100 to 150 meters, and we want to compare with this. And depth of water 4 meters, length of the geotextile tube is about 50 meters, and the diameter 3 meters, and so on. Then these are the, I think these are the ASTM they required, all the specification for the material, and we checked it, and we meet the requirement. And also we using the sand, I think it's a pretty good sand for the backfill material, and in terms of the grain size distribution, and also the permeability. And we have a dredging ship. Ship is like this size, and the crane 50 ton. And now we placement of the the bedding, the geotextile, and normally we do use about 20 ton per meter, the tensile strength of geotube, and we're using the sandbag, and we fix it, and this we filling the soil, and we instrument it, and put the pressure, and also the vertical the earth pressure cell, and also we checked it benchmark from the coastal line. So we want to see the the change of the coastal line, and we checking it as compared with before and after. As we see comparison left hand side or right hand side, the sand migrate very much toward the extended toward the coast, the sea area. And we checked all the level of the sand ground, and we have a little bit we increase. That means the sand is accumulate behind the geotube. As you see the observation, I think this is very important to see the that seaweed and the marine creature growing on the surface of the geotextile tube, because that the maritime or the fishermen, they're not happy with the installation of this geotube in front of their coastal area. So we, from our observation, this is a very environmentally sound and good method for the fish and also agriculture purpose. And this is another project. We had the nuclear power plant. They discharge the warm water to the sea. When discharge the water, then the coastal area is eroded very much. So they want to prevent the erosion. So we use the geotextile tube for here, and the diameter 3 meters, and again 50 meters, the length, and you see that all utility, barge ship and dredging pump, and the apron mat, and this is a sandbag. We want to fix that apron at the bottom of the sea, and you see they're filling the geotextile tube, place it, and filling it. And this is a schematic diagram about the diameter 5 meters, and the second strategy. This is for the platform for the bridge pier construction work. And I'll quickly move to this, and we're spreading apron mat and the geotextile tube, and we pumping it, fill it, and make a double deck. As you see that, yeah. So this is a much cheaper way to construct a platform for the bridge pier. Maybe normally we use when the sheet pile. So in this case, instead of a sheet pile, we use the geotextile tube, which is much economical and stable. And finally, we remove this part. And this is another project, similar project in the Issmge. Our university located here. And this Grand Bridge, that this area, so we use that geotextile tube, and this is a, I think 3 layers of a stacked of a geotextile tube and diameter 5 meters, and this is one, I think about 1.5 kilometer. So we have 3 decks, so back and forth, and here and here, and the great length of the geotextile tube used here, and we did some management of the assistance of the technical problem of the stability for this particular project, and also design for this. And we check the sliding and the overturning bearing capacity as a user, and which satisfy the requirement. And also this is the view of the installation of the apron mat, and setting the geotextile tube, and we pumping the sand slowly into the tube. And here, I think after we installed in the first layer of the geotube, we want to place this second stage of the geotube, and we felt maybe some next layer of the geotube maybe rolling, and falling down, maybe sliding, maybe we worry about. So we adopted, like a mattress form and geoform, and we fill the cement milk inside, and just naturally that stabilize, and then we stack up the next layer of the geotubes, which increase the stability very much. I think as a conclusion, see that the prediction of geotextile tube shape we can do 2-dimensional strain, 3-dimensional, final element analysis by using the abacus, and also we should check when you selecting the filling material, we got to do drainage condition and the consolidation, phenomenon, so that we found out is good agreement with the field model test, and we check it, and also stability, sliding, overturning, and the bearing capacity, particularly in the marine area. And also when you have some under the water, we need to have some hydraulic model test to simulate the field situation. So we should find out the reasonable factor of safety. And also
Professor Shin,
yes?
you have to wind up in the next 5 minutes or so, sir.
No, this is the last slide.
Thank you, sir.
Also, with the geotube, when you wave attack, because the geotube is a twin tube normally we use, and the diameter 5 meters, after putting the sand, drainage of the water from the sand, that make a very hard and a big structure. So they can, break the, wave attack. And also then we can minimize also a migration of the sand seabed, because that the sand coming in, and when it comes out in the down direction, so that sand is accumulated, behind the geotextile tube. And also submerged geotextile tube would be good solution because of the inhabited seaweed and around the geotube, and also the habitat of the sailfish. So this environmentally sustainable technology for shore protection. Thank you very much for your pay attention. All right.
Thank you, Professor Shin, for a very interesting practical applications you have highlighted. And we'll be happy to take quickly 1 or 2 questions. Professor Reddy, am I missing anyone from the group chat? Any questions?
No questions are there.
Yeah, so, currently none.
On behalf of all the participants, just I'll pose a question to Professor Shin. So in many,
go ahead, sir.
In many countries, geotubes are being used for mitigating beach erosion, and still in some countries, people are opting for groins. So in which conditions do you suggest that compared to grow in geotubes or else?
Yeah, that's a good question. You see that when the groin, you see that groin is more exposed, expose the ground surface. So sometimes if you build the groin by the geotextile tube, because of that, people, they put on their foot on there, and also a lot of activity on the top of the groin. So that's why the geotextile tube also, I would say they damage it, So it kind of needs some protection by the geotextile and some other, methodology. And also it's not very environmentally friendly. So my suggestion is maybe depth of water is not very deep. Like Malaysia, they has a very successfully, they implemented the shore protection, the mangrove growing area. But depth of water is not 4 meters, maybe 2 meters or something. Then geotextile tube is like a parallel with the coastal line. That would be good, and very easy to construct it for that and for stability and otherwise. Because you see, when you go to the coastal area, if you towards the sea, the level is not the same, because geotextile tube is very important. When you have a level at the bottom of the tube in the ground, because sometimes we have a rocky area, the seabed, there is a problem, make a leveling it, the real situation. Experimentally is okay, but so I prefer to have a same level of the ground, and where the foundation is there, of the textile tube. Hi, Daniel. So I parallel is with the coastal line would be the better situation and the construction wise and also stability wise.
Okay, sir. Thank you. Thank you for the clarification.
Thank you very much, Professor Shane, for a very interesting lecture.
Sure.
And Professor, thank you, sir. Now I invite Professor Yamar Madhav for the next lecture. Before that, let me introduce Professor Madhav. Professor Madhav is a distinguished visiting professor of AICTE INAE, visiting professor IIT Hyderabad, and most importantly is an alumnus of Andhra University who is hosted the conference. He graduated from Andhra University in 1960. And Professor Madhav's research interests span the whole gamut of geotechnical engineering. He has guided more than 45 doctoral and several master's theses. He is a fellow of Indian National Academy of Engineering. He was awarded with several awards of IGS and Distinguished Alumni Award from IISc Bangalore, Doctor of Science Award from IISc Bangalore. He is a very well-known teacher and a researcher who traveled extensively all over the world, delivering lectures, keynote lectures, invited lectures, and the list can go on. But to keep with the time, I request Professor Madhav to share his knowledge on mitigation, prediction, and limitations of scour. Welcome, sir.
Thank you, Ramana. Can everybody hear me?
I'm able to hear you. Yes, sir. Yes, sir. And your video is on, sir?
It's on? Can you see?
Yeah, we are able to see you, sir.
Okay.
Okay, sir. Yep. Go ahead, sir.
I'd like to thank Professor Reddy for inviting me for this very important workshop. To me, it's one of those most timely ones for the simple reason. In India, very few seem to have been working on this cover. We left it to the hydraulic engineers to decide, and we are not able to modify the predictions or in terms of limitations of the present method. As we go along, I would like to highlight where the lacuna are, and I would like my young researchers to take this topic for future work for the simple reason it's the most challenging one. Just as we have foundation, soil foundation interaction or soil structure interaction, we have an interaction problem between the water or the hydraulic part and the ground. And we somehow seem to be a little scary of getting into this area. And I haven't seen much work to quote in terms of prediction of scour. And while we are trying to solve the effect of scour, like what G100 in terms of design, etc. So what I'd like to now go into would be initially, I had a very interesting experience of dealing with a coastal scour. And for the last 10, 15 years, I've been trying to deal with alluvial scour, wherein the practice is very, very conservative, and that way leads to enormous expenses, time, etc., which is something not very good. My first project I would like to talk about is the Gulf of Cambay on the west coast, slightly north of Mumbai. You know, we in India, we have tidal effects, but on the east coast, I believe the tide isn't too much, about a meter, meter and a half, whereas in the west coast, it could be like slightly more, 2.5. But in Gulf of Cambay or Kambat, as they say, I believe the tide could be as high as 5 meters or so. So somewhere in this region where there is enormous erosion that's taking place. You know, this has been going on for quite some time in the recent past. I believe the coast was moving at the rate of something like 5 to 10 meters per year. And on the right side, you will see that there is a oil field, which is ONGC is buried. And you can see the coastal erosion because of the high tide. Apparently, the tide velocity could be as high as something like 4 to 5 meters per second. So it could be very, very significant. And this problem they were trying to deal with various aspects of it. You can see how the erosion takes place over a period of time. And they were trying initially to do various kinds of sheet piles, piling, trying to stop the erosion. And all of them seem to be collapsing within a matter of months. And the erosion has reached such a stage, as you can see on the right, there is a small shipbuilding yard. This is what they call as the small ships, which are 1,500 to 2,000 ton capacity, they call them DHO in the area there. And this has been used for the last maybe 2,000 years for trade between India and the Middle East and the Arab countries, Gulf countries, and that is getting eroded too. You can see very close to the shipbuilding yard, erosion has reached. And this is another closer view. In a matter of probably few months, a year, even the building that you see here would be gone if we don't do something else. And you can see the piles which are already installed completely eroded, even the reinforcement, probably because of the cost, what is it? Seawater effect has eroded and is being visible there too. Another closer view of the same shipbuilding yard. And this is where we were asked to look into it. And then it's such a challenge. We hardly had any information about the soils at the site. They hardly could get us any soil sample. All we could find out was it's predominantly a silty sand, and the tide effects are very, very significant. So we had to make a guess what can be the possibility. So after a few iterations, we came with this solution. We said the only slope that will be possible would be 2 horizontal to 1 vertical, but that we protected significantly. So we provided a geotextile as a separator and for erosion protection. Then we provided a series of sandbags, on top of which we provided gabions. The height of the slope was fairly high, so something like 10 to 12 meters. So we had to provide berm at a height of 7 meters. And then on top of it, we put the gabions and tied them too. But the most significant one we thought was, it is not so much the slope erosion alone that bothers. We need to worry about the base too. So we had to provide an apron, which goes something like 12 meters into the bottom of the bay or the gulf, and then we had to tie them. So the solution provided was combination of both gabions and geosynthetic with sandbag particles, geobags put in. When we are trying to look at the gabions, it turned out that normal ones will not be more valid because of the salt water and erosion of the ordinary galvanized gabion. So we had to choose for pre-coated ones. And the other interesting thing is you will not get any dry surface to put in. So everything has to be constructed in water, so through barges, etc. When the course, they gave us about 850-meter long coast to treat, and other places the height was a little less, so we didn't use the berm at all. But the base 12-meter apron was necessary. The reason we were insisting on the apron was if there is any initiation of the scour near the slope, the apron would automatically sink, go and seal the erosion. And this is how the design was approved, and then we installed it using barges. And I would like to say that originally when we started, it was sometime in December 2006, April, this work started and the gabions were put in. And this is how in May it looks like. The tide was coming, but the gabions were holding more or less. And then we went on observing it over a period of time at different times of the tide, up and below. And in spite of the tide being active, it has been working. And you can see even after 3 months, we are able to protect it. And the idea is that this will last for about 5 to 10 years. That's what they wanted. It's not a permanent solution. But what we found interesting after 3 months was, instead of erosion, there is some accretion that is taking place. When the tide goes down, you can see the soil getting deposited and giving additional protection for this too. This is after about 4 months of this, and you can see the same coast continues to be. And the people came to check. This is being chased from ONGC, and apparently they were trying to extend the same treatment for rest of the bay over which their oil field was being extended. Their oil wells were getting affected very good. And this is another view you can see. And then what happened was that whole thing seemed to be working well. I couldn't go this year, but apparently till last year, it is still working very good. And this is the extent of our area they gave for treatment. And here you can see the depth of height of the embankment is not that high, so we didn't do with the berms at all. But you can see the geobags that were put in there partly, then the geocell, the gabions, etc. And you can see the accretion even here when the tide goes down. So this seems to be a kind of solution which worked here in this particular case with limited geotechnical data. We had to base it basically on some intuitive angle of shearing resistance. We took maximum maybe about 25 to 30 degrees, and the gabions seem to have prevented further erosion. So this is one of the most satisfying jobs we are called upon to deal with limited information. I would like to now come to more challenging jobs which I've been dealing with for the last 10, 15 years. A lot of bridges in India are being designed, and the scour is a major problem, as being highlighted by several people, including Jihan. The problem here is that our IRC code is very, very conservative and is probably, in my opinion, very outdated. So I wanted to impress upon our young engineers what is that which controls scour. I will first look at the substrata. You need to have a series of borings done and get the boring data, stratification. Then we need to know the bed material, the side gradation, distribution, etc. Then these stream and plane cross sections are very important. And what will be the shape of the platform that you're taking? And then again, the watershed characteristics. In India, we have the alluvial rivers in the north, which have very high flood level, whereas in the peninsular India, we have a couple of or few major rivers, but a lot of others are minor ones, and there are even small streams where there could be a flash flood. Then we need to have scour history, which unfortunately is very, very limited in our country. I haven't seen much of data over a period of time. then we don't even look at the energy gradient in the sense that how is the bed slope? If I have a obstruction, what will be the gradient upstream and how is the gradient downstream of the bridge, etc. Then history of flooding. What is kind of, is it one day? Is it over a period of a month, or is it a flash flood, etc.? Then location of the bridge. I believe now there are several bridges parallel to each other being constructed in several rivers. For example, if I look at Godavari, there are 3 next to each other. What would be the effect of one on the other? Are we taking that into consideration? Then the stream. This is where I found very interesting thing. Some could be perennial, which means the water is there all the time, flashy or intermittent, or there could be a gradual increase in peak. That's a different one. Then geomorphology, in the sense that you have the Himalayan fed rivers, which are geomorphology is very, very different. Our geomorphology is different because what we have here is a different kind of soil, mostly weathered soil from the granite, basaltic, or sometimes if you look at the Western Ghats, you will get some kind of lateritic soil. And those are the ones which are controlling this cover. Then erosion history. We have hardly any idea, no experimental data, no published one. Maybe the hydraulic engineers have some information, but as far as I'm aware, geotechnical engineers are not aware of any of these. Now the complication now is sand and gravel binding. I think somebody is using his, I think it's better. Can we request the participants not switch off their mobile?
Using that touchpad.
Then off late, we are having a major problem in terms of mining of sand and of course gravel, and everybody knows this makes a big difference in terms of score.
Sir, you can deactivate the annotation, sir. You will have more options.
I think, okay, basically I wanted to show that it takes different types of soils. You have scouring. In case of granular soils, it can be hours. Clays, it could be day. And depends also what kind of water. Is the water clear water, which means there's no bed load, or if there is some live bed, then you have a different kind of thing. Are we aware of these effects in calculating the flow? Then it depends on the depth of flow. You can see if I have an axisymmetric pier, the kind of effect of water depth and the kind of vortices and the flow field changes and the turbulence that takes place. So it makes a big difference in terms of the depth of flow around the pier. This is for a simple circular pier. The same mode, if it's a narrow one, you can see at the bottom what can happen in terms of formation of a scour hole. And then because of that, the kind of vortices that form and further propagation of the scour bed. And you can see, I would like you to also see the velocity profile, which increases from the bottom of the river to the top, and near the bed, obviously, there is some very low velocity that leads to some shear stress too. This is how you can see flow field around a wide width pier. And it's very different from what you have seen for a axisymmetric narrow pier. Now, do we use the same scour equation for both of them? Or should we say we need to consider the size of the and shape of the pier? This is what bothers me in all our design analysis for the scour. Then this local scour, which I think Jihan also mentioned several ones, but I would like to know what kind of mechanisms hold good. If it's an accelerated flow, which means the flood is increasing, or is it a secondary flow, which means because of all these horseshoe vortex where you have a horseshoe kind of thing, or a surface one, or a wave, or a pressure gradient, all of these make a difference in terms of the scour. Basically, what I would like to know would be, if I have a flow occurring, what would be the shear stress that is going to cause the scour, which means I need to find out the bed shear stress. And we had to ensure if this bed shear stress is less than the shear resistance of the granular material. If not, the scour will take place. So this is how what can happen if the bed shear stress is greater than the shear resistance of the soil at the base. And we haven't been able to use any of these in our prediction of this cover depth. So these are again flow fields around locus cover problem. And I would like this to be analyzed in terms of geomechanics. And these are again the processes you can see with the kind of vortices, the rollers at the surface, and you can see the horseshoe vortex at the base, which I mentioned a bit earlier. And this again, I think Jihan mentioned it already, the kind of shape at the bottom, you can see the scour is biased, but the slope below before that gives you the kind of scour getting initiated, and everything depends on what you can call as the median grain size for the soil there. The point I'd like to mention is from hydraulics and geomechanics, you can say the scour is a function of several parameters, including the unit weight, the particle size, effective stresses, specific rate of soil field, the water depth, the width of the pier, the height of the pier, the velocity. We can even analyze using dimensional analysis. This I'm presenting for the simple reason I want to know how many variables are available for us to analyze and use in terms of predicting the scour. Unfortunately, we don't do that. This is what I got from the Federal Highway Authority, wherein they use what's called Shepard's equation, and then the scour, which is normalized with respect to effective diameter of the structure, which is equivalent to a circular one. It depends on the water depth, a function of it. It depends on the velocity with respect to the critical velocity, and it also depends on the relative size of the pier with respect to the particle size too. And these are all functions which are fairly involved in terms of various parameters. You can see that in case of clear water, when the velocity is less than the critical velocity, or if you have more than, you will have another set, you will find that these equations are all given so that I can calculate the scour depth based on these parameters. And this is how the subject has evolved in terms of hydraulics, but in terms of our prediction in India, it is rather sad. This is for the live bed scour, wherein the velocity could be higher, in which case the scour takes place along the base, and you find that the equations are more different from what we have seen earlier. So this I find is a more challenging job, and we need to do that. And then how do we take care of the prediction and protection? So once you get the scour, in terms of the equivalent diameter, what could be the maximum? And I want you to see here, the maximum scour in clear water is taken as twice the equivalent diameter of the pier in case of clear water, and basically D is the effective width, you can say. And then in live bed, which is the big erosion taking place, it's about 2.2. This is how Federal Highway gives you. And the bed shear estimate is given in terms of the velocity and Ks, which is a bed roughness coefficient, which is a function of the particle size. If the particle D50 is more than 0.8 mm, or if it is in the range of 0 to 0.8 mm, we have different values for the bed roughness. So you do get a bed shear stress available for us. And then based on that, we can also calculate the design shear stress, which is a function of, here again, I want you to see there is a parameter called KB, which is a bed coefficient. So is the river straight or is there a bed at that time? And then of course, it depends on the hydraulic radius, area divided by wetting parameter, unit weight of water is the gamma standard. The other important thing I would like to do is the slope of the energy gradient, which means at the bridge, what will be the gradient before and after the pier. They find out the gradient, and then you can estimate the bed shear stress. And then we compare that with record critical shear stress as a function of grain size. And here I'd like to see this is a very, very important parameter. When you look at the mean grain size, the lowest critical shear stress which the soil can offer is with respect to a granular material, probably 0.4, 0.5 millimeters in diameter as D50. And as the particle size increases, the shear resistance increases, obviously. But on the lower side, as far as sands are concerned, I mean, below 0.1, 0.05, etc., you have the V-shaped curve. But when you come to the silt fraction, or even part of the clay fraction, it's not all that simple. The variation in terms of critical stress, which will cause erosion, in case of silt and clay, is very uncertain. It can vary from as low as 0.5 into D60 to the power of 0.4 to 206 into D60 to the power of -2. So this is what you have from the Federal Highway Authority. And I would like you to realize that the shear stress which causes scour is different, I mean, in the sense that resistance is very different for silt and clay, and you cannot use a simple equation at all. And that is where it matters. Obviously, in case of intact rock, etc., it's very high, we are not worried. And as you can see on the right, if you put riprap, there is no worry about in terms of the shear stress kind of thing. So then I wanted also looked at the CERIA, that is the British Construction Industry Research Association. They also said that if the bed is ratified, each layer should be considered step by step, and it's likely to terminate or progress to the next. Why I'm insisting is that I have many places where the surface may be fine sand, but if I have sand or gravel, I know that scour will stop. But unfortunately, the code doesn't have that kind of thing. And I have problem with many practicing engineers. The British engineers say, no matter what it is, you have to use the scour depth predicted by the sample near the bottom of the river bed. This is another parameter that seems to be affecting is the pier nose and shape configuration. Suppose you have a flat one, like square nose. Round is very common for us. That is, if you have a double D, you have the round nose, a cylindrical circular pier. Some of the old piers had this wedge shape or bevel shape, which you can see as D. And then, of course, you have piers which are multiple, that you have two individual ones on which the deck is cast and we built it. This pier nose also makes a configuration in terms of scour. Then I think Jihan talked about piles, and when we have these piles, we have the group effect, then we have the pile cap effect. Pile cap also is affecting the flow, and below that is the group of piles, and the pier is above the pile cap. So all these three have to be considered, the piles, the pile cap, and the pier in terms of the rotor. Because of them, you may have three different aspects of scour. We look at the scour due to pier, scour due to the stem, or due to the pile group. And when we have pile group, sometimes, we haven't been using too many of them, but off late we are getting into using piles. Otherwise, till now, in India, we have been using most of the time well foundations. And which are, in my opinion, very conservative and then very time consuming. We should go away from well foundations to the pile groups, which we have enough technology to install and then to analyze too. I think, G about when do I consider if the spacing is close enough, can I use a kind of block failure or block of flow and then do the scour for the pile group? That depends on the spacing and you can design accordingly. Then this also gives you kind of erosion rate, but as you can see, the fine, poorly graded sands and silty sand are the most highly erodible. And erodibility rate decreases as you increase the kind of soil becomes sand or low porosity, silt, jointed, etc. And this is very important in the sense have a degraded sand or silty sand. But I don't think it's necessarily true for all other kinds. So have we taken that into consideration? And then here again, I would like you to look at effect of the flow depth with respect to pier width and what is being observed over various results that we have, and discover in terms of pier width again. And as the ratio increases, there seems to be a tapering off of limits. Cover depth is limited to maximum 2.5 to 3 times the pier width. Whereas if you look at the Chitale one, it shows linear, which is very, very highly over predicting this cover depth with respect to flow depth, which to me again is a very serious limitation in our design. And this is the profile.
Scoring and
I
errors.
request all the participants to mute themselves. Thank you.
Then I found that very interestingly, in our IRC, we are assuming a profile which is given at the top, wherein the riverbed is more or less constant over significant part, and then of course the towards about 22. Whereas I find that many of the channels where the flow is occurring in the peninsular India, you have a channel which is relatively narrow, and then you have a right and left overbank. If that is true, if N2, which is the channel width, is relatively small with respect to the total width of the river, then how do we design in this case? Should I use the same cover for all the reaches or from left abutment to right abutment? That is another problem we have. Then you can see the effect of the flow velocity, and you can see the difference between the two. When I look at the velocity contour, they're very different depending on the shape of the river channel. We haven't included any of these parameters in our design. This is a typical bridge profile, and I can show you that this is not very uncommon. Many of the sites where we have seen the fine sand or the erodible material is at the center, but we don't necessarily have the same thing. Now coming to IRC 78, which is what we are using in all our design and where I find many challenging jobs of trying to get to reality. They have only 4 categories of catchment area. 0 to 300 square kilometer, 3,000 to 10,000, 10 to 40,000, above 40. And then they say increase the discharge. The cover depth is predicted based on simply the particle size and the shear KSF factor, which is a shear Worth-Silt factor, which is a function of the mean diameter of the particle. That's all the information that's being included. And unfortunately, this is a 1940 based equation, which is being used in our present day design. We have changed since then. And these are the silt factors as a function of particle size. Is that enough to predict it? What I'm surprised is, why should I only look at the particle size that near the top, not at the bottom? We have to be very whole. And this is the present state of design in terms of based on IRC. This is Federal Highway, where they try to predict, as I mentioned earlier, on several factors. The cover depth, the function of flow depth, factors for pier node shape, angle of attack of flow, for bed condition, pier width, length of the pier, shroud number, mean velocity, etc. Where is this state compared to our IRC? So we did a project where there was a bridge in one of the North Indian states. They were putting the pile foundations, and they were saying the piles had to go deep because of the prediction of cover. And this is a fairly long bridge, as you can see. There are about 12 to 13 spans, and the pile groups were varying from a 3x3 to something like 4x4 and 6x6. I wanted to look at the ground profile they had here, and I want to see here, when I look at it at a depth of 12 meters, I got a intermediate geomaterial, which means it's a kind of bonded, what should I say, cemented sand, which is not plastic, and the N values are more than 200. I mean, which means actually recovery, refusal. N values are increasing from 10 to 30, 40. And I want you to also look at the fines fraction. At the top, I have 46% fines. Then at a depth of something like 2 meters, the fines content comes down to 22, 10, etc. And as you go deeper, the fines content is maybe 10 to 14. But I want you to look at the intermediate geomaterial, which is a very strong, stiff material. And this is the bridge side. Another profile with the same, very similar. And I get again the intermediate geomaterial at a depth of 13 meters. And the fines content, except at one particular place, it's all very low in this case. And here is the grain stress distribution. As you can see that most of the soils are on the, what you can say, the sand, fine sand medium. There are few samples which are on the fine side of it. And based on that, they are trying to calculate in terms of discharge and the scour. And the hydraulic engineer gave this calculation. And he gave a scour depth of something like 13.75 meters. This is the prediction, which means normal scour depth. And then we had to provide for twice that. So which will become 27 meter is the depth for which we had to assume. No lateral resistance, no pile capacity, etc. This is the sad state of affairs that we have. The prediction is 13.76. I want you to look at the intermediate material, which is available at 13 meters. Do you think the scour will progress from the top to below the intermediate material? I have also found that there are sites where even if the hard rock was made, that was in somewhere in Orissa, they were insisting, no, you had to take the piles much deeper as per the prediction based on whatever is available at the top. So we had a lot of arguments trying to convince the scour in a non-homogeneous media, you had to analyze separately for each layer. Nobody does it. This is how they have been saying that you had to increase the maximum depth of pier, depth for scour for pier is twice the predicted scour, which is 13.76. And for the abutment, they said 1.27. This is what our IRC says. And we had to convince the people not to go for such deep piles. And then we don't need to provide such deep piles for abutments because the north scour strata is available at a very shallow depth. I mean, very close to the abutment level. So we had to talk to them saying that we need to revise the whole thing. And look at this. Because of this, the piles had to be taken much deeper and the pile capacity is high, I mean, very long. And then the socket length has to be increased to take care of both axial and lateral loads too. I want to finally give you a thought for remembering. If I do a hydrometer analysis, and if the flood comes and recedes, where do you think fine particles will be? Will they be at the bottom or do you think will be at the top of the sediment? So this is the point on which I want you to think and then see how much can we modify our design in terms of predicting the scour depth as per the based on geotechnical consideration. The flood is coming. It is bringing a lot of bed load and the soil is getting churned completely and the flood recedes. And once the flood recedes, the coarse particles will settle down first and the fine particles settle later, as you have seen in the borehole data. If that is so, and if I determine the D50 for the fine, for the particles at the top, should I use the same D50 for all layers? Or should I say I need to work better in terms of stratification and recalculate for each grade, each depth of the river bed? This is my thought for everybody to look into, and I encourage all the youngsters to work on this kind of problem. Let's work with the hydraulic engineers and bring in some geotechniques in scour depth prediction. And of course, we know enough to design once you know the scour depth. But my main concern is how to predict cover depth. I would like to thank all of you for your patient listening. And I would like to end my presentation with usual signature. I find that geotechnical engineering is a science, but when I'm practicing, it's an art. I cannot use any of these equations when I'm practicing my geotechnical ones. And I hope I have illustrated the challenges we have. Thank you, all of you. Have a good day.
Thank you, Professor Madhav. As usual, very thought-provoking and leaving some research directions for the young researchers. I think that is along with the practice. That's what is your hallmark of your presentations I had attended. And there are a couple of queries here. I'm going to read out for them, sir. How, these days we are getting cover depth as high as 20 plus meters. How do we mitigate? We prefer well foundations. However, right now it has been mentioned to avoid well foundation and go for piles, which becomes very costly.
I would like to say that well foundations have been traditional in India. We have been using them from the time of Taj Mahal, which was built on well foundations. But let me tell you, does anybody know how conservative is well foundation? We design according to IRC code, but the process of sinking itself changes the properties of the soil. So we hardly know anything. And we had used them because the technology was not available. We knew how to sink a well for our drinking water, but it doesn't mean that it's good for structural ones. We did it. But since around 20 years, maybe last 15, 20 years, we have very good equipment for pile foundations. Let me tell you, pile foundations are very quick to install. The quality is much higher and much cheaper. You can save a lot of time in construction if you go for pile foundations. Every project which has well foundations will drag on to 5 to 7 years. And I don't know how many of you are aware that sometimes because of the intermediate floods which happened in the second or third Ganga bridge near Patna, even the well got washed away. So I had to reinstall it. I had done another project where the wells got tilted and shifted. And if the well gets shifted or tilted, its capacity is lost. How much can you expect it to take care? The limit is something like 5 to 8 degrees maybe, but even then the capacity is reduced. So to me, just as there's no one who doesn't use a smartphone in these present times, you should go for pile foundations and not go for old the well foundations, which are like our earlier for mobile phones, which are very primitive. That is the best analogy I can give you. And high time we go, because the equipment for pile foundations is fantastic. In the Deep Foundation Institute meeting, if you remember, they even used the continuous auger piles, which are very fast to install and very reliable too. So that is my advice. Don't go for wells at all.
Okay, sir, one more question. How can we arrive on the silt factor for intermediate geomaterial?
There is no need, actually. Honestly, I want to, for my whole presentation is, you can see, this cover depth somebody mentioned is 20 meters. It's because at the top, we have more fines. Basically, if the soil below is, once it covers 1 meter, 2 meters, it meets with a much stronger or much coarser material. Will this cover progress? Where is the prediction of 26 meters? How did it come? Is it because the grain size at the top, or is it grain size right at the bottom? That is where I mentioned, according to Syria also, you initially predict, but once you go 1, 2, 3 meters, you will find the grain size distribution is different. So it can cover up to 2 meters, 3 meters. It meets with a coarser material, a stronger material. It will not progress further at all. We have been asking, even I was at IIT Kanpur, I asked the RDSO, can you give me a cover of all the bridges you have? But they have not been able to share it with us. So the biggest problem is we are still following the same old Lacy's equation, which he if you go to the history of it, he worked in Punjab in 1920s and 30s. And the oldest reference, which CBIP manual also gives is dated 1941 for scout prediction, and which is used in our IRC. Please revise it. I want my young people to work on, suppose I have a bed which is stratified. I have fine sand, coarse sand, and coarser sand below. Run a scour analysis or scour experiment. Will the scour progress from the top to the bottom if the increasing particle size is increasing? For intermediate materials, for rock, etc., scour is, as I gave you the shear resistance is so high it will not scour at all. So you calculate what is the bed shear and what is the shear resistance of the bed material. And if you find that the bed material is stronger than the bed shear, no scour. So basically, people had to realize, don't depend on one D50 for the soil at the top of the riverbed. Go for a stratification analysis and make sure. And then we save a lot of money for our country. If only we go for a stratification analysis and improve our scout prediction. And I find this is the biggest problem. I had a project in Andhra Pradesh for the national highway. The rock was met at 5 meters or 6 meters. The scour depth was 10 meters, based on the soil at the top. Can the scour occur through granitic rock? That's it. Point I want you to, all of you, think. Please don't go by, I would request IRC to revise it, but we had to put pressure with scientific study, which is what I want our geotechnical engineers to get into. I wish I was back in a college, then I could have started all of this, but I realize now when I'm practicing that scout prediction is one of the most conservative, outdated ones in our country. Thank you.
Thank you, sir. Some of your old students are enjoying your class today, who were students of you at IIT
Good morning,
Kanpur.
Sir, good morning, sir.
Good
I am
morning.
Go ahead, madam.
Sriram Lingeswar Sarma. I studied at IIT Kanpur in 94-96 batch, sir.
Oh, good.
But today I am very fortunate enough to listen to your class again after 25 years.
Oh, thank you. All of you made my day, and I'm what I am because of the kind of students I had all these years. No, that.
And
so it was
very excellent class, sir. Thank you, sir.
Thank you. And now I hand over to Professor Satyanarayan Reddy.
Thank you, Professor Ramana, for effectively conducting the session. So we had a very interesting and informative lectures by the eminent experts in the field of geotechnical engineering in general and scour and erosion in particular. So we are fortunate to have the lectures of Professor Issmge Sassa, Chairman TC213 of International Society for Soil Mechanics and Geotechnical Engineering, followed by the lecture of Professor Jihan from University of Kansas. And then we had the lecture by Professor Issmge, Vice President Asia, Issmge. And then we have a very interesting lecture by Professor M.R. Madhav. So he has critically appraised and analyzed the existing methods available for predicting scour, mitigation measures, and he has pointed out some important points which can be taken up by the researchers for their research studies. So your lecture is very much useful to you, sir. I thank all the keynote lecturers of the forenoon session for sparing their valuable time and for being with us, for sharing their knowledge to the participants of the workshop. So on behalf of the organizing committee, I thank you all for joining the session. So once again, I thank all the keynote speakers for spending their time preparing the papers and making very interesting and informative presentations. I thank the session chairmen for effectively organizing the sessions. So I hope all of you might have enjoyed all the lectures and gained considerable knowledge what you are expecting by looking at the brochure of the workshop. So we'll have 4 more lectures in the afternoon session. Most of them will be having case studies. So I request you all to join back at 1:50 p.m. For remaining technical sessions of the workshop.
Thank you, Professor Reddy. Bye-bye.
Thank you, sir.
Thank you, Professor Reddy. Bye.
Thank you, sir. Thank you, Mahendra Singh, sir.
Okay, thank you. So we will be busy in NEC meeting in the afternoon.
Yeah, sure, sir. Sure.
Okay, okay.
Thank you, sir. I'll be there for some time because I have my lecture.
Your lecture is there. Okay, very good arrangement. So it has now started.
Sir, with all your support and encouragement.
No, it will go very smooth.
Sir, thank you, sir.
Okay, thank you so much. Okay, bye.
Bye, sir. Professor Babu, sir, thank you very much.
Top left, bottom intermediate.
And then that mom, other same. Yes, sir. Session yes, mom. వచ్చేసి
Hello, Professor Reddy.
Sir, I'm here. Sir.
Okay, things are fine. It went off very well. Good.
Sir, thank you very much, sir.
Yeah, thank you. That's nice.
So we have tried to do whatever we can.
Yeah. It has come out very well. That's good. All the 4 lectures are very nice. Yeah.
And mostly we could complete as per the schedule.
Yeah. That is what is required. Otherwise, so afternoon, yeah, we have.
Afternoon, we have 4 lectures, sir.
Yeah.
Last speaker is not available, so out of 5, 4 only will come.
It's all right. So 3 o'clock is easy meeting, right?
3 o'clock, it is in other link, sir.
Yeah, I got that link. I have that.
I have instructed them to start the link at 2:30 p.m. Sir.
Okay.
So 3 o'clock, I will just come and say hello to everyone. And
yeah. Sure. No problem.
Okay, sir. Thank you very much.
Thank you.
Anil Joseph, sir, thank you.
I think, yeah.
Anil Joseph is there. Maybe
I would like to thank Professor Issmge for his presence. I hope he's not there, maybe.
Shin is there, sir. He is there.
Yeah, he's there, but he may not be.
Audio is muted, sir.
Okay, it's all right. We should thank him for its very nice lecture. And Professor Jimmy, Dr. Jimmy.
So afternoon session.
Yeah.
He is in charge, sir.
Okay, great, very nice. Okay, thank you, Professor Reddy. I will take you. So Anirudhan is there. Professor Anirudhan is there.
Sir, good afternoon, sir. First, I thank you very much for this pre-conference workshop. I am Selvam from Somesa.
Oh, thank you, sir. Thank you.
Thank you.
Thank you.
Yeah, I just want to, this is very useful for practicing engineers. So particularly for cover and erosion, all the lectures can be combined and published like conference proceedings. You are published.
Yeah, that we are bringing, sir. Actually, the speakers have prepared papers and they are submitting.
Yeah, okay.
Definitely will bring out proceedings.
Yeah, okay. Thank you very much. Thank you, sir.
Okay. Thank you.
कैसे मुझको मिल गई किस्मत के आए ना यकीन Hello, please exit the conference. The conference is now ended.
Sir, Dr. Jimmy Thomas, sir. Professor Sundar has joined, I think. Sir would like to have a trial.
Okay.
Hello.
Yeah.
Are you able to share the screen, sir?
Host has disabled the participant screen sharing.
Yes, we will. 1 minute. We will enable, sir. 1 minute.
Sir, we have done it, sir. We have done it. Sir.
Yeah, it is done. It is done, sir. You can do. You can do now, sir. Okay, sir. It has come.
It has come.
It has come, sir.
Yes, sir.
Sir, if you don't mind, you can on the camera, sir. Video, sir. Video camera.
You want to see my face?
Sir.
Okay.
Sir.
Yes, sir.
Okay. Yeah. Thank you, sir.
1 second. My fan is on.
Hello.
Hello.
Yeah, I'm from the office of Brigadier R.S. Rawal. Hello. Can you hear me? Hello.
Ma'am, you are audible. You speak.
I'm from the office of Brigadier R.S. Rawal, who is guest of honor tomorrow.
Okay, ma'am.
I just wanted to know how to join this meeting tomorrow, or is this right? Are we in right now?
Ma'am, you want to test a call, ma'am? Test a call.
Sorry, I didn't get you.
You want to test your screen sharing?
Yes. Yeah. What do we need to do tomorrow? What sir need to do tomorrow? How to operate this?
Sir.
Can you see us?
1 minute. Who is asking?
Yeah, I'm from the office of Brigadier R.S. Rawal.
Yeah. You just call me. You just call me on phone.
Sorry?
Hello.
Yeah.
So you just call me over my mobile.
What is your mobile number? What is your mobile number? Are you there?
Madam, the number, is it your phone number that is being displayed as a participant ID?
Okay, it is a meeting ID which I have entered. It is 972 4574 8502.
Okay. Madam, actually the workshop is going on in this link actually. By the end of today, we'll be finishing this. Then we can check for our presentations and all.
Okay. Actually, sir is guest of honor tomorrow. So when do we need to join? When does he need to join, and what we need to do tomorrow?
No, it is not the platform to ask all this. You just call me over my mobile.
You can call Sachin Reddy sir over his mobile so that he'll inform you the details.
Okay, just let us know the process, because tomorrow we need to do.
Yes, definitely we will let you know. But as of now, there is a workshop going on in this link. We'll let you know what to do. Thank you, ma'am. Sir, Vamshi.
Vamshi.
Yeah, Dr. Parsari sir, good afternoon.
Good afternoon to all of you, sir. Good afternoon.
Yeah, how are you?
Yeah, good, very good.
Okay, Dr. Thomas, how are you, sir?
Fine, sir. Good afternoon, sir.
After a long time we are seeing, no?
Yeah, yes, sir.
After
Yes.
Purankara days we are seeing now.
Yes.
Am I right?
We met in probably 1988.
Somewhere around that. After that, I don't know whether I've seen you in IGC conferences. That I don't remember. I think I should have seen you somewhere. Okay. Okay, sir. Welcome. We'll see you sometime.
Welcome.
Okay, sir. Dr. Patsari, sir, we will see.
You. Good to see you, sir.
Sir, should we wait for 2-3 minutes more, or should we start?
I think you can just wait a couple of minutes. If somebody is just having their lunch and come back, in 2 minutes you can start.
Sure, sir. Yeah, sure, sir.
Dr. Thomas sir, shall we start or wait for 5 more minutes? People are
yeah, 5 minutes.
5 minutes.
5 probably we can start. Yeah.
After 5 minutes, you can start, sir.
Sure.
Welcome, Dr. Parthasarthi sir. Thank you.
Thank you, Professor Satyanarayana Reddy.
Thank you, sir.
Sir, voice is not audible, sir.
Yeah, it's audible, clear.
Shall we start? Let's do 5. Good afternoon. I welcome all the participants to the second half of today's workshop, EC 213 workshop on cover and erosion. So we will be now starting technical session 3, where we have 2 speakers. So it is my pleasure to welcome Chairman Dr. C.R. Parthasarathy and the speakers, Professor V. Sundar and Mr. Albert Lim Lum Kong. So, Dr. C.R. Parthasarathy, founder and chairman and managing director of Sarathy Geotechnical Engineering Services Private Limited, will be chairing this technical session 3. It is my pleasure and privilege to introduce our chairman. Parthasarathy started his career as a geotechnical engineer in 1993 and is involved in numerous large-scale site investigation and engineering studies at various levels for both onshore and offshore projects. So he has rich experience in site characterization and deep foundation testing. In 2007, Dr. Parthasarathy founded the Sarathy Geotech Engineering and Services Private Limited with its registered office in Bangalore. The company provides geotechnical and testing services for both offshore and land constructions in India and abroad. He is a partner of Pile Dynamics USA, and he is instrumental in promoting quality testing of deep foundation in India and authorized trainer for high-strain dynamic pile testing. Dr. Parthasarathy is the Life Fellow of Indian Geotechnical Society, elected National Executive Committee of IGS for the 3rd consecutive term, and Chairman, IGS Bangalore Chapter. This brief introduction, I invite Dr. C.R. Parthasarathy to start technical session 3.
Thank you. Thank you, Dr. Jimmy Thomas, for a very elaborate introduction. At the outset, I thank the organizers of this workshop for giving me an opportunity to share one of the technical sessions. So today, post-lunch, in this session, we have 2 eminent speakers, Professor Vallam Sundar and Mr. Albert Lim. So first, I welcome Professor Vallam Sundar. Welcome you, sir, on behalf of the organizing committee, as well as the chair of this section, to this technical session. So before I hand over the chair session to Professor, I would like to introduce to the participant. Professor Vallam Sundar obtained his bachelor's degree in civil engineering from College of Engineering Gindi in Chennai in 1975, obtained his MTech and PhD and joined IIT Madras as a faculty in 1981. He retired in June 2018, having served as a professor in the Department of Ocean Engineering since 1996. So post-retirement, he rejoined as a professor emeritus at IIT Madras. So Professor Sundar has supervised 27 PhDs, 14 MS, 12 MTech theses, and he has about nearly 550 publications to his credit in various conferences and journals. And perhaps these publications are the highest by an Indian in the field of ocean engineering. So we are really proud of you, sir. A few of his publications has won the Best Paper Award in the international conferences, and more so, he has participated in hundreds of conferences worldwide and chaired many, many technical sessions. So he is the member of the editorial board of 10 international journals and has reviewed number of technical papers submitted to peer review the journals. He has been rated as an excellent teacher at IIT Madras. He has published 3 books and also courses that is available in the YouTube, which has become very, very handy for students for the distance learning. He has a number of awards to his credit as well, notably the National Design Award in Environmental Engineering 2008 from Institution of Engineers India for his notable contribution of solution to 4 decades old problem of coastal erosion along Raipuram. So recognizing his contribution in the field of coastal engineering, the International Association of Hydro-Environmental Engineering and Research elected him as the chair of the Asia Pacific Division in 2006. And he has long-term collaborations with several overseas universities in Europe, particularly in Germany and Norway. So he's serving as a member of expert committee for the Coastal Protection and Development Advisory Government of India for 3 terms, each of 3 years since 2010. His reports on the master plan for the 2 maritime states, Tamil Nadu and Kerala, in connection with tsunami mitigation measures remain as the basic document for planning and implementations. He has recently held the National Green Tribunal on an important decision on settling a dispute on coastal protection. Welcome you, sir, Professor Vallam Sundaram, and he will be delivering his technical talk on sustainable hard and soft measures for coastal protection. I'm sure with his decades of vast experience, he will mesmerize us in this post-lunch technical session. Over to you, Professor, for the commencement of the presentation.
Thank you, Professor Pathasarthi, for introducing me. At the outset, I would like to place on record my sincere thanks to the organizing committee for having given me an opportunity to share my experiences. So my topic will be on sustainable hard and soft measures for coastal air protection. Of late, these soft measures have become so popular, at least talk of the day. And let me try to give some examples for both hard and soft measures. Then I'll just present to you the performance characteristics of each of these, and then I'll try to finally wind up with the merits and demerits of hard and soft measures. And most of my lectures, this lecture doesn't have a single equation, so you can relax and be peaceful and happy because you don't have any mathematical equation. And it will be something like my experiences so far. Coastal hazards, as you can see in this slide, floods, storms, and earthquakes. But we are more interested in this, storms and floods. So here you see that what you see on the subscript is against each country showing its global rank. So this rank, I think we are not happy with this rank. This you leave it because it's more of nature. But this, although it is of nature, we can certainly do something about it. So this calls for better understanding or also prepare well for any kind of mitigation measure in the case of coastal hazards. These coastal hazards, except tsunami, all other coastal hazards are more or less giving us enough warnings for us to get prepared. Now, added to this dimension is the rise in sea level. The mean sea level rise on a global scale has been increasing by about 1.8 millimeter per year. Now, this out of a recent study, you see that it is almost about 1 millimeter. This is from NIO. So you can say that the sea level rise is to an extent of about 1 to 2 millimeter, 0.1 to 0.2 millimeter per year, meter per year. So now, next we'll move on to the causes for erosion. Now this is a video which clearly shows what kind of environment we are living with. India has such a long coastline, and most of the parts of the coastline has a lot of problems, and there is one such problem. So this is a nature, this is due to nature, and we need to safeguard our environment. So the natural factors are action of waves on the coast, storms, sudden outbursts, construction of dams, because if you have a lot of sediments along the shore, then these can serve as buffers and reduce the inundation level as well as the height, wave height. But if you start constructing dams, then this also would lead to some instability in the shoreline. That doesn't mean that you are not supposed to construct any dams. It needs careful planning. Then added to this already existing problem, we are talking about the sea level rise. There are artificial factors, human activities along the coast, construction of harbors or any other kind of development activities that will intercept the passage of sediments along the coast. The moment you allow things to take its own shape, then there is no problem. But if you try to meddle with it, sometimes you burn your fingers. A combination of these two factors are the one which has recently acted in Mahabalipuram, which I'm not going to discuss here because of want of time. So look at these two animations which are self-explanatory. For example, flat beach like that in Goa are excellent for relaxing, and that is why Goa beaches are very popular. And steep beaches are not popular, and we don't go to a location where the beach is steep, particularly for holidays. But then look at these two, animations. So here, quite dangerous in the case of maybe a tsunami, because it will simply travel, and the travel distance may be much, many times higher than in this case of a beach. Now let me touch upon some of the basic physics. See, when you go to a beach and stand here, look into the ocean, you will see most of the time you will get a feeling as if they're hitting you directly. It is coming normal to you. But when you drop a ball, you see how the ball is moving. Ball will be moving along the shore. So either it will be moving this way or this way, and this depends on the seasons, southwest monsoon and northeast monsoon. So in this way, if the waves are coming in this direction, probably during southwest monsoon, then there is a flow taking place, which is called as longshore currents, and these are induced by the ocean waves. Okay, if this inclination is longer, more, the obliqueness is more, then the current will be more. And this current is going to remove the particles all along the beach, and it will be transporting along the coast. And that means there is a continuous movement of sand along the shore. And for your information, the east coast of India has the world's longest, highest transport rate. So when that is the situation, when you add some kind of structures for different reasons, maybe this is for coastal protection, which I will come back later, or this is for making sure that the connection between the river and the ocean is not blocked, then you construct a pair of training walls. Either in this case, or there is another case where you have offshore detached breakwater. We'll see later. So you see what is happening is the movement of sand is arrested, and then you have a beach. This is a positive aspect, but then there is some erosion taking place on the other side. So this needs to be carefully done. And when you want to do that, when you want to erect this kind of structures for the coastal protection, what is in hand right now, most of structures are hard measures. They are constructed with natural rocks or concrete blocks. Now, of late, people are talking about geosynthetic products, which are termed as a set of, subset of your soft measures. So, having introduced the basic subject, then I will get into, at least I have emphasized or I highlighted the how the erosion is taking place. Now, there can be another form of erosion, that is particularly when on a regular basis. But when there is a storm, what happens is the storm breaks, and you have seen the earlier slide where it can have overtopping, and that will, when the return flow is taking place, the sand is removed from the beach, and that is how the erosion takes place when there is a storm. Now, to counteract all these problems, what are the options we have? One is called as hard engineering options. Here, essentially, gravity structures made of rubble stones or concrete is used. And this is an age-old practice which is still continuing. Then immediate results of erosion problems can be sought out, because the moment you think of this, it is quite, it's not so difficult to get the solution. You will get an immediate solution, but carefully it need to be done. If you put in a location where it is not supposed to be put, then you are likely to have adverse effects. So that is very important. And when you look at coastal protection works, so you see that hard engineering structures. So this is a beach where this is a coast which was continuously eroding, and they have these groins. This is called as groin field. So what will happen is when the sand is moving, the first one will stop and then you will see the beach, and the next one will stop, you will see. So alternate pockets will have some beach filled. Ultimately, maybe after a few years, maybe about 5 to 10 years, you will see that you will be able to win back the lost beach. That is the advantage of this groin field, or this groin field can be straight, or at certain locations you might have to have going for what is called as the T-groins, or if you don't have this kind of support, then you will have just offshore detached breakwaters, which can also do the same purpose as that field. The other aspect is the seawall, which is very, very common, and you would have seen, most of you would have seen these seawalls. The seawalls earlier, there was not, to be very honest with you, there are not much of technical, scientific calculations to arrive at the slope or weight of the stone. They used to simply, I am talking about early 60s or maybe late 50s. They used to dump, but later you had formulas and then started refining the cross section so that it can survive at least the perennial wave action or even the storm, occasional storms. So this is the training walls which serve as a connecting, which can permit the and the fresh water, and in several locations it is needed because there are some brackish water lakes, for example Chilika, which is a brackish water lake. If you don't have the continuous exchange of fresh water and seawater, brackish can become a freshwater lake, and you have other consequences on one thing. And then, for example, Pondicherry Harbor, you have a training wall so that vessels can and then move inside. So these are all these structures which I am showing you. These are all hard structures. That is, we use boulders, and that's why it is called. But when you look at the basic physics is it is stopping the movement of sand and arresting it from clogging in, and then it is promoting the free exchange of water. So what it means is the structure is same. Only the material, if you can change, and if it can survive the environmental conditions, then you can use any kind of material instead of the hard measures like your concrete or natural rocks. Then here you see that if you have a structure like this, these are all called reefs. These artificial reefs are submerged so that the energy can be dissipated even before it reaches the coast. So this is one kind of another kind of technology or scientific idea which we have and we have implemented. What I'll try to share with you is some of our experiences along our Indian coast. So to start with, this was one of the important projects which I don't forget to present in any forum, because this also got me the award, and this was a problem that was persisting for nearly 4 decades or 5 decades, in fact, 5 decades. So you have the Madras Chennai Harbor with a breakwater here. And initially what happened, when there was only one small structure jetting in, then we had the Marina Beach formed. When the sand is moving, and the moment you have a kind of an obstruction, it stops the sand freely moving. So what happens is it starts settling here, and then you have the beaches formed. So this is a positive aspect. We have the Marina Beach, which is the second longest beach in the world. And, but then there is another negative. This extends to blocking the river. And this river is connected all over the Chennai city, which still stinks even today. And that is one of the reasons why we have a lot of mosquitoes also. Now, coming back to the erosion, this area was completely getting eroded on a continuous basis. And we lost nearly about 400 meters width of the beach and for over a length of about 6 kilometers. So this is a loss which we need to take care. And also then we had another port coming here, which is called as the Ennur port. Now it is named as Kamaraj port. Now the distance between this and this is something like 20 kilometers. But then you need some kind of connectivity between these two ports along the road. And if the road itself is getting eroded, then what is that? The first choice is to make sure that this road is repaired. And that is how we try to look at the groins as first time we wanted to put the groins, and we had a lot of hurdles. Whenever we want to try something new, certainly all of you know that you might have to face a lot of hurdles. Not because they want to question you, but they want to be careful. So now you see that a road which is connecting this area was completely eroded. And you can see what is the status of this coast. What they did is they used different kinds of solutions for this, and without knowing how you can tame the waves and the sediments. We need to tame the waves. That just you cannot be greedy in coastal protection. So if you want to adopt, you have to think and plan. And then we gave this solution. And what we gave is, this is the harbor, Chennai harbor, and this is the Ennur harbor, satellite harbor. So initially we had 4 groins here and then 6 groins here. And then we said this is the most affected area. That was because you see that this area, you don't have much of problem with the road. So only this area was really very badly affected. So we gave this solution and immediately it was implemented. And also not just giving the solution through physical modeling as well as numerical modeling, which I'm not going to go into the details. Then after this, then we also were involved in the site supervision as well as also advising on the construction procedures. Then this was done, and then now you see, this is the area what to see is to believe. Now you see that an area where you would not be able to see the sand at all. Now you see this is the status, and this sand is still intact. There's no problem, except that when we started monitoring this area, this stretch of the coast, you see that you follow the dates here, and you see that this is the area of sand that was accumulated. And you just note here, see in this 2004 September, we had something like 8,000, which was about 50% of this vanished in January. So you know the reason. You must be knowing the reason because of the tsunami of 2004. So during the tsunami 2004, you had the removal of the beach sand from the shore, and then it was taken inside. But then that sandbar which was formed there again got redeposited, and this is what is called as, you have to sometimes wait and observe and then take a decision. You should not immediately jump into the conclusions. So we were very happy, and the status quo is maintained. The beach is intact and we don't have any problem. Now, after having exposed you to the groin field, I am not going to, I think I have something on seawall because this is not very serious. Only thing is you have to talk about the slopes, which I'll come back to that later. But then the other important structure or concept is having breakwaters. These are just trapezoidal sections put in layers. The lowest layer will be of smaller stones, and then as it comes outside to the surface, it will become bigger and bigger. The largest zone will be on will serve as the armor layer or the surface layer or the primary layer to take care of the wave forces acting on it. The design of such structures are no problem at all. It is quite straightforward. You can design. Only thing is implementation or planning of the spacing and the lengths of these breakwaters, and also looking at the status based on the status of the shoreline and also the past histories, etc. That is where you need a lot of scientific input, and that is what we are in a position to do. So the top one is somewhere in Spain, and the bottom one is somewhere in Denmark, where they have protected this coast. But then in our coast, this kind of a concept has not been tried yet, not much. There are some pilot projects which through which we have burnt our fingers, and in fact they have not used the rubble mound or the hard measures for this. They had used the geotubes. I'll come back to that later. So now the idea was, now when we looked at this, the cost implication comes into picture. This is a very effective solution for the coastal protection. But then we have some kind of another phenomena that can be beneficial to the society. Then probably we can think of the detached offshore breakwaters as one of the positive solution. So in this way, we try to look at this concept, and then what we try to think is to how can we include or combine the rise. That is, now people are talking about alternate sources of energy, and among which the ocean energy is one of the important concepts, and among which wave energy is also very promising. And so it is nothing. See, when the wave is entering, you have a chute through which the wave is oscillating, and this air is going to be oscillating, and that is going to pump or move the turbine, as you can see. So how can we include this in a rubble mound offshore breakwater? Now you see that this is a breakwater, this is another breakwater, this is a portion of another breakwater. So we had a number of oscillating water column devices here to understand the basic physics, how it performs. So now you see that the gap between the oscillating water column devices were varied, and then we found out that this is quite promising. And for your information, this is the first time it has been done around the globe, and this paper has been acknowledged worldwide. And then we have come up with some concrete conclusions with this. And now the only problem is we do have some problems with handling this rubble mound. So instead of this, we are looking at how we can have a precast kind of a structure with a built-in oscillating water column device. Such a kind of a device is a structure for coastal protection as well as energy conversion, can be very useful for, particularly for island. In the offing, probably will come up with, hope we are going to be successful. And now next you have the artificial reefs, which I have said. Florida is one of the places where they have used the reef balls and to a great extent, because what happens is it dissipates the energy even before it reaches the coast. And there are some kind of guidelines how to plan for this. And for example, this is somewhere in Puerto Rico where they have constructed here, and in order to save this age-old fort. So with this kind of an idea, what we thought is, so for our country, there is one artificial island here, which is called, an island which is called as One Island. This island, quite long island, was slowly getting eroded. And in fact, a part of the portion of the island got completely vanished. So what we wanted is, we didn't want to, it is rich in flora and fauna. So we cannot afford to bring in stones there. So the other option was to go in for some kind of artificial reefs. So now we have fabricated this kind of artificial reefs prior to going into the ocean. We try to verify this through numerical modeling as well as physical modeling only two-dimensional tests in the flume. And then we suggested that this kind of an array of artificial reefs, as you can see here, is placed as shown here alternatively, so that the wave energy can be absorbed and it's all submerged. So because of which you have a lot of marine life you can see here, and the I am happy to say that the island has come back to its almost original shape. This was about 4 years back, 4 or 5 years back, we did this work. And then we wanted to extend this work as a kind of a device which is like this. And we are able to, this is just a concept, is a part of a PhD work. Now, having introduced you old problem, and it is still stable. The seawalls have been redesigned. Somehow I forgot to explain that, but it was redesigned because the slope was instead of 1:2, we just have a flatter slope in order to reduce the weight. Or if you have a steeper slope, you have to have a heavier boulder. All these things are there because I don't want to discuss in detail. And then you have about we have recently done about 30 stretches of the coast, Kerala coast, along the Kerala coast for about I don't know, maybe about 45 to 50 kilometers, and there are still ongoing about 4 projects ongoing with something connected with this and other kind of concepts and towards the future. So if you want to check the Google Earth, go along the Kerala coast and you will see it for yourself. Now, towards the future coast, depletion of natural rock, particularly, in fact, Kerala is not allowing now. They are banning the natural rock. And for islands, it's going to be quite difficult to transport there. So then in that case, you are driven to kind of artificial armor blocks, like concrete blocks, not the natural rocks. And it is also the problem with this is the destruction of highways. You have the hard measures, you have the positive aspects, but then you have other problems like that lead distance may be more, but still, since you don't have any other concept, then you are only driven to natural rock, then you don't mind spending a lot of money on the lead distance. So, hence, and also the concrete blocks. You have some of these blocks on which we had to be paying a royalty earlier to France particularly. Now we have our own blocks which we have recently done for Krishnapatnam port, and it is intact and it is very good also. And now then we have the multi-purpose breakwater or reefs, which I have discussed. Multi-purpose breakwater is the offshore detached breakwater with wave energy converter. So very important. Also, it's also very important for us to look into the cheaper methods of coastal protection. Now let's look into the soft engineering options. One is the beach nourishment, take it from one location to and drop it in another location. Dune stabilization. This is very good on paper, but very difficult to maintain it in the field. And same case here, it is looking very nice, but maintaining is a problem. Coastal vegetation, this also is a problem. But we always talk about greenery. Okay, greenery, how difficult, how easy it is to manage in this kind of an environment. That is one important aspect we should have in mind. Geosynthetic tube, yes, this is eco-friendly, it's very nice, environmentally friendly. So, but then there are some ways and means of doing it. And we did try this, and what was the consequence? I'll try to share it. For example, narrow neck, which is in Gold Coast. This is one thing I request you to just, if you are interested, you can just put a narrow neck Gold Coast. You will know about the details of this project, how they have used synthetic products to win back the lost beach. Now, involvement in IIT, involvement of IITM in soft measures. So you should not think that IIT Madras is looking only at hard measures. No, that has to be removed from your mind. So we have done something on beach nourishment of Puducherry. I'll tell you that this we have done in Orissa, Gopalpur. Again, we had a lot of issues with this. Maintaining the dune is not so easy. Now, recently we have also completed one PhD work, and we have given design principles for having the plantation to be made all along the coast, which was really vulnerable tsunami ingress. So, but then this all takes a lot of time. You don't, you might have to wait for years now. So, coming to geosynthetic products. So here is the geosynthetic products where we have tried something for in Uppada, that is of north of Visakhapatnam. So where you see that we have prepared a layer which is called as the geotextile, and over which we have a geotube. There is a special way of filling the sand with inside the geotube. What geotube does is it retains the sand and allows the water to penetrate out. And then over this we have placed geo bags, that is just sandbags. Over that we have put what is called as gabions. So this combination of geosynthetic products gave us some kind of degree of confidence, because it has served for several years now. I think probably 5 to 6 years it has served, and it has withstood a number of storms also. And this is one such scenario taken, which is shown here. Now, the geotube, coming to geotube, suppose when you want to put the geotube as offshore breakwaters or an artificial beach, so you see that this is ineffective, because if you don't do it perfectly, then you are in for trouble. The whole thing is going. Not only this tube will go, it will also take away with it all the sand which is accumulated here. But a better way of doing it is completely submerged here and make sure that it is not exposed. When it is not exposed, that means there is a problem with the geosynthetic material. That is, if it is exposed to UV rays, then it becomes brittle after some time. So it is quite effective when it is submerged under water, and this is how it is also serving the purpose of winning the beach. But in our case, what is the problem? We have done similar kind of thing for Shankarpur, that is of West Bengal, wherein we had all these sandbags, all these geotubes. But you see what happens. So this has sustained the waves, but then the manhandling. So manhandling in the sense human intervention. They just to poke the geotube because it looks really funny. So they want to poke, and then once it is poked, and when you have some rain or something like that, the whole sand, whatever has been. So we move on to artificial beach nourishment. That is in Pondicherry. So you say along the east coast of India. So this is north, and this is south. So this is north. So the sand is moving along the north, and that is why you have Chennai Harbor breakwaters and you have the Marina Beach. Same way, south of Chennai, you have the Pondicherry Beach, Pondicherry breakwater. And in fact, this was also done by IIT Madras. And once this was erected, then we know that it's going to happen. This is going to happen. But this is no man's land. So no man's land, not no man's land, it's not inhabited. So what happens is this beach is not serving any purpose. So what we can do is use this beach, nourish this area which was getting eroded. And this is what was done sometime in early 2000s, I think, 2001, I think. So we pumped some of this sand, and there is an underwater tunnel here. And through that tunnel, it was bypass. This bypassing was excellent. It gave very fruitful results, as you can see here. This is to see how it served. And this was in early 2002. And then again here. But what is the problem here? It served. It helped. But the problem here is during the monsoon, you have the power cut. The motor fails. The pumping is not possible. Then what happens? The motor is designed for a particular capacity. So after the monsoon, the capacity, the quantity to be handled increases dramatically. And the pump is not able to cater to the requirement. So that is how this project was stalled, but it was not. So when you look at cheap materials, there are several cheap materials like coir bags, concrete blocks, which is run through a chain, and these are all used by CWPRS. Have done a lot of work in this area, and we have not been involved in this kind of work. And so I'm just projecting all these things. Recently in Kerala, they have started using the coconut fiber as a revetment for this one. So this needs to be examined how it's going to serve. Now, next we are in the planning stage for a soft measure near Bengal, West Bengal. So Sagar Island is somewhere here. And we are planning to have the geotubes, as you can see here, and have a mattress here, container and mattress, have a proper toe protection here so that the scour can be avoided. And we have gone in for a submerged breakwater, submerged reef, and this is still pending. We have submitted the report and we are waiting for the okay. So here, if you look at the soft measures, it's mixed. Towards the future cost, sustainability of geosynthetic products, particularly the emerging type exposed to sunlight, is a big question mark. And in fact, its life, wherever they have done, it remains to be seen, because I have not come across products which are lasting more than 5 to 10 years. Whereas for this boulders are remaining there intact. The only thing is you might have to do some kind of periodic rehabilitation. Execution and maintenance of such project. So the products needs further investigation. It needs skilled labor, simple technology needed for filling the geotube. So this is very important, because I had an opportunity to visit, spend some time in Mexico. Mexico, the 2 geotubes which you saw is from Mexico. So it is almost like a child's play for them. In one day they fill the tube, and the next day they lay the tube. Everything is finished within one or 2 days maximum. But in our case, it doesn't happen that way. So this is one area which needs a lot of attention, skilled labor and technology. Then cheaper protection measures like its sustainability have to be assessed. It will work because the principle is same. The basic physics is not much of different. Only thing is it's sustainable. All these software measures, all the soft measures are bound to work. But its sustainability is the only question mark which we have to have in mind. Then plantation, it has been proved to be very effective, particularly after the tsunami. I'm sure many of you would have seen the articles saying that a lot of area which was which had the plantation, these plantations are serving as soldiers against the tsunami in Greece. So that is the kind of experience we have. So a lot more need to be done in the plantation. So conclusions, if you look at, so hard and soft measures. I have explained you our experience with hard and soft measures. Now aesthetic, it's not appealing. Yes, we have to accept that it is not accepting, but it is serving its purpose. It is appealing, but we don't have enough evidence that it is serving its purpose. Then provided it is submerged, maybe it is working. Because once a typical example is, I had an experience in Cochin. CWPS has laid a geotube, which is a submerged geotube. Technically, everything was good, but due to the whole the weak soil, it has completely gone down. So it is not serving its purpose of preventing the sediments from clogging the approach to the Cochin port. So then restoration immediately effective. I need to just put some boulders. But here it is not. Once it is punctured, the geotube is punctured. Although we had, in the case of Shankarpur, we took all kinds of precautionary measures. We had a UV stabilizer, we had extra sand, everything, but still it did not work. And capital cost may be slightly higher for installing slurry pumps. Geosynthetic materials are expensive there. Here again, geosynthetic, there are mushroom of industries having geosynthetic materials. The quality of material needs careful assessment. The environmental impact, huge. Of course, this leaves a huge print, because when you talk about trapezoidal section, the base width is going to be high, more, and it's going to leave a larger footprint, whereas that footprint is completely much less compared to in the case of a soft measure. Implementation, very cheap, very speedy, easier, and unskilled labor also is enough. Good, only good supervisor is needed, but mostly skilled, unskilled labor is good enough. This is quite time consuming, and it has to be very carefully done. The low water level, high water level, all those things have to be taken care. And in case where there is a large tidal ranges, then you have other problems. Then design criteria, you have a number of solutions. I mean, manuals, shore protection manual, and other things. Here we do have one book that was published by Pilaris, which who also we had the opportunity of having Pilaris with our geosynthetic workshop held in IIT Madras, and we had a lot of knowledge shared between us, and but still there are lot of things to be done under geosynthetic division. The design life maybe 30 to 100 years. This is my wild guess. But then 30 years definitely on the minimum, definitely for sure. 100 years is a guess. And then it's not defined. In software, soft measure, it's not defined yet. Unless some of the experts sitting in the crowd may please clarify me if there are anything. So thanks for your kind attention, and I look forward to your interaction. Thank you.
Thank you. Thank you. Thank you, Professor. If there is any questions, maybe one or two questions we can take before we go to the next technical session. Could you please post some questions? Somebody have?
I just would like to say that all these things, whatever I have discussed, is also available in the YouTube under my name. So you can just look at coastal engineering, Sundar, you will get all this information.
I think there's no question, Professor. I think one of them have really appreciated your presentation. In fact, thank you very much, and very nice presentation. So now with this, I call upon the next speaker for this session, Mr. Albert Lim. Hi, welcome Albert Lim on behalf of the organizing committee and the chair of this session. Welcome you, sir. Before I hand over the session to you, I wanted to introduce the speaker to the audience. Mr. Albert Lim is a professional engineer and is currently the regional manager for 10K Geosynthetics, Malaysia. He is responsible for marketing and development of geosynthetics in water and environmental application in the Asia Pacific region. So in his academic background, he has a Bachelor of Science in 1988 from University of Mississippi, USA, and Master of Science degree in 1990 from the University of Mississippi, USA as well. So to his professional experience credit, he was a technical manager at Polyfelt Asia in Malaysia since 1997 to 2011, wherein he was responsible for providing technical support on various geosynthetics or geotechnical application, that is the stabilization of extreme soft soil, land reclamation, over soft soil, slope failure remediation, wall slope design, etc. Implementation of research and development projects with National University of Singapore. And since 2012, he is associated with 10K Geosynthetics Asia SD and BHD in Malaysia. Until now, as a regional manager responsible for commercial sales of hydraulic and marine business in Asia Pacific region. So he's going to deliver his talk on the topic geotextile tube for coastal protection and land reclamation. Welcome you, Mr. Albert Lim. Over to you, sir, if you can kindly share the screen with the presentation. Okay. I think there are a few questions. Maybe we can take those questions at the end of the session. Yeah, go to the presentation. Over to you.
Okay, good afternoon, ladies and gentlemen. A very good afternoon. So this afternoon, I will do a sharing on the use of the geotube containment system for shoreline protection and land reclamation. This is the content. I will give a very brief intro on the use of geotube containment system for shoreline protection and land reclamation. And from there, we will go through projects in Vietnam, which is the Lac Huyen Bridge and also the Deep Sea projects. And I will also talk about the long-term property of the geotube containment unit subject to weathering. I mean, Professor Sundar has brought up a very, so-called question on how durable is a tube after 5 to 10 years. Yeah, and with this, and this is an accumulation of the tubes It's after 5 years we cut the fabric and we test it. So I'll be very happy to share on the properties of the tubes after 5-year exposure that we actually do the simulation. And last but not least is the Mauritius project in Malaysia and also Muni project in Vietnam. Okay, I mean for geotextile tube, right? I mean, in terms of the fabrics, there are different type of fabrics that you use for different application. Yeah, what happens is that they say, oh, there's a rupture of the tubes, there's a problem of a weathering. The main reason why this occurs is because, I mean, the wrong type of fabric has been used for the wrong application. This is what I'm trying to say. So if you look from here, this is a sand color fabrics we use for shoreline. This is the black color one. And for permanent protection, yeah, where you got high vandalism and also, I mean, high wave pounding action and also high UV, I mean, condition, we will use composite fabrics. Yeah, this fabric allow entrapment of sand. Yeah, so when you got entrapment of sand, it will solve the vandalism problem. It will solve the UV degradation problem. Yeah, so what I'm trying to say is that there's different fabrics that you use for the geotube design for different application. Yeah, each application you have to design, I mean, for the property of the fabric to be used. Okay, geotube you can form on land, you can form in water. The maximum inflated height is 2.5 meters that you can pump, and normally you will fill the tube with sand. Why sand? Because if you fill with marine clay, you will get consolidation with time, is it? And also it's very difficult for the water to drain out. So what we normally fill the tube, we fill with sand, yeah, and sand got self-compaction. And what we are trying to say is that with time, right, the shape will not change with time. Okay, the length of the tube normally is 50.5 meter length, and when this is the inner part, you will fill in. Then from there, it will drain all the way through. The water will drain out, the sand will be trapped in the tube, and the last inner part we leave it open. Intermediate inner part we seal it. The distance between the inner part is about 5 meters, around 10 meters center to center. Okay, so how you actually fill the tube depend on the size of the project. If the size of the project is very big and there's a sand available, I mean from the sea, it can be direct from the cutter suction dredger. Yeah, that can be one way, or you can use a steel tank. This is the most common method used in Asia. I mean, in areas like Vietnam, Indonesia, and Malaysia, we use this method. It's a steel tank, and inside the steel tank, we have a sand slurry pump, about 190 meter cube an hour. So what happens is that you will pump water into the steel tank, you fill sand inside there, and from there, this sand slurry mix is pumped into the tube. Where are geotube been used? You will use it for shoreline protection to protect your building front over here. As a breakwater, as what Professor Sundar just now has shared, very effective. You use it as a breakwater to break the energy. As a groin structure, this is shared by Professor Shin this morning for the groin structure. And also as a jetty. I mean, in country like we use a lot in country like Philippines and also in Indonesia, where they have many islands and where they have to construct the jetty. You see, so as rock is not widely available, we use the tube to form the core. Yeah, to form the core. Yeah, and from there you put the rocks over it. So in terms of usage of rock, I mean, you actually use less quantity. And also we use it as a containment dike. Yeah, these are containment dike for land reclamation and also for bridge construction, especially coffer dam, as shared by Professor Shin this morning. I mean the Issmge Grand Bridge. Yeah, we can also use a geotube to form the containment dike. And these are submerged breakwater. These are submerged breakwater that we can use the tube. So once the wave pounding action goes over, it slows down the energy and it allows sedimentation of sand. Yeah, submerged breakwater. These are all the tubes. Okay, so the first project that I will use a woven tube. Yeah, a woven tube, because I highlight earlier there's different products, different fabrics for different application. Here I'm going to use a woven tube, and the requirement, and this is the woven tube, and the requirement by the customer is that it has to undergo UV exposure 5 years without cover. Yeah, no rock cover, no sand cover, no soil cover. That was the requirement by the owner. 5 years exposure, the tube should not degrade. Under weathering condition in Vietnam, northern Vietnam. I mean, it's very close to India. I mean, in terms of the this UV exposure is very close. So what we have done is that we have used a 200 kilonewton product. This one, 200 kilonewtons, and the elongation has to be very low. Why it has to be very low? Because when you pump the tube, you don't want the tube to change in shape. Yeah, so you use less sand, because when you pump right, straight away you get a height. If your elongation is very high, the tube will actually go sideways because it has to expand before it reaches the ultimate tensile strength. And the other thing is that you don't want the structure to change shape with time, is it? I mean, because of creep. So you use a product that has a low elongation and also a very high seam strength. During pumping, you do not want the tube to rupture, and high abrasion and high UV resistance, because the tube will be subjected to wave pounding action, and also this sand pounding is a very high abrasion and very high UV. Yeah, and that's the reason why in this project the client said 5 years no cover, the tube should be there. Okay, this project we call it the Lac Vuillan Bridge. Is funded by JICA, Japanese loan. Yeah, it's in high form. So what they've done is that they want to construct a deep sea port. This is the deep sea port over here. It involves a bridge construction about 15.6 kilometer length of bridge construction. Yeah, and out of this 15.6 kilometer length, 5.4 kilometer is this crossing in the sea. It's a sea crossing, 5.4 kilometers, right, in the sea crossing. And the main difficulty is that the soil is marine clay. It's around in the region about 7.5 to 15 kPa marine clay. And if you use the normal, method construction, it's too soft for construction equipment. And if you do the conventional rocks, when you dump rocks, right, the rock will actually, sinks into this deep marine clay, easily more than 7 to 8 meters deep. Yeah, and barges most of the time will be grounded because of it's in the tidal flat. Most of the time the water is about around 1 to 1.5 meter. In the deeper section. So due to the tidal flat and also the soft soil, yeah, the client had actually changed the methodology to use geotube because it saves time, saves cost, and also the carbon footprint compared to rock option. Okay, so if you look from here, this is total is 3.9 kilometers, this crossing. Okay, so out of here, around I put that way, it's around 1.5 kilometers is constructed using the offshore construction is around here. This is using the offshore construction, and this is using the land construction. Yeah. So what the client have actually done is that they actually use 2.9 kilometers using the land construction using a geotube to form the containment dike. And this is the offshore construction. They do not use the geotube because this is the deeper section. Yeah. A schematic layout. This is how it is. Total height is 4.5 kilometers. Sorry, 4.5 meter height. The total height of the tube. So they actually have formed a coffer dam. 3 tubes on the left and 3 tubes on the right. And between the tube, you fill with sand. Yeah. And from there, they construct the superstructure. All in all, in total, about 27 kilometers of tube was supplied to this project. 27 kilometers of tube. So if you see from here, the tube had to be left exposed for 5 years because this bridge construction, right? It takes in the region of 3 to 5 years. So during the construction, right, the tube should not degrade. If it degrade, the coffer dam will collapse. Yeah. So it actually left exposed. This is the installation of the tube during the low tide. This is the first tube that's been done. So once that's been done, right, we will actually fill the area with sand, the area between the tube with sand. Then from there, the second tube is up already. Then from there, you can see the structure is going towards into the sea. Then once that has been done, you have the confident up. Then the heavy machinery will go up to do the pier structure. You can see from here, the structure has to be there for 5 years. They should not degrade. So then from there, they construct the superstructure already. Yeah, you can see from here, all the way up into the sea. Then from there, they do the deck. This is the deck. This is after construction. Yeah, for the bridge, this is 5 years already. The pier is up, the deck is up, and you can see that the tube, right, it does not degrade, it's still there. Yeah. This is that this photo is taken in the 2019. So you can see from here, these are the geotubes over here. This is the bridge structure. Okay, so from the Lac Huyam Bridge, Deep Sea 2. Deep Sea 2 is adjacent to this Lac Huyam Bridge. This is the bridge structure. This is the bridge structure over here. So from there, the client has changed the design using conventional armor rocks to geotube. This is the bridge structure using geotube. Then from there, they do the land reclamation here using geotubes. Yeah, this is the conventional design that the client has actually adopted during the initial phase, is using rocks. But when they saw the geotube for the Lac Huyam Bridge, they changed the design. This is the design that they had changed. You got a scour mattress, then you got a tube over here. This is 2 meters high over here. Then from there, this is above the water level, which is a sand mattress. This is inside the land side. So we have 2 tubes. This tube is just to prevent the overtopping due to typhoon. Yeah. So you can see from here, this is phase 1 done in 2014 over here using geotubes. This is phase 2 done in 2017 using geotubes over here. So the geotubes are used as a containment dike to contain the hydraulic fuel that's inside there, and the geotube will be less exposed. So you need a minimum lifespan of 5 years. That's a requirement by the owner. Yeah, you can see from here. These are the geotubes. Yeah, over here and over here. Yeah, the construction was very difficult because we actually had to construct in the soft bearing clay around 7.5 to 10, around 15 kPa. So we have to use a bamboo raft because it's a soft bearing clay, and bamboo are very high in tensile strength, and it allows the manpower to step on top. So once with the bamboo raft, we will lay a high strength PET reinforcement, a high strength basal reinforcement, because the soil is very soft. The high strength basal reinforcement is about 800 kilonewton per meter. Yeah, and with that, then we only put a tube on top. This is the installation of the high strength PET basal reinforcement over the area. Then from there, we install the tube over the high strength basal reinforcement. So you can see from here on the left and on the right, yeah, I'm going to construct the dike. The basal reinforcement is over here across. Yeah. So we have 2 tubes at the bottom. This is the scour protection, and this is above the water level. We have the sand mattress. Yeah. Above the water level, this is also filled with the thickness is about 180 mm thick. We will actually fill with sand slurry. Yeah, you can see the bridge, right? This is the bridge structure. This is using geotube, the bridge structure, and this is the land reclamation for deep sea. It's adjacent to the deep sea. This is a Lac Huyam Bridge. So this is the scour, the protection. This is the geotube. This is taken in 2017. That is a sand mattress. You can see in 2019, right? 2 years, the tube is still intact, and this is the scour apron vegetation start to grow. Yeah, 2017, you can see that it start to grow. The tube is still intact. Over here, it start to grow. Okay, 2017, this is phase 1. 2019, this is phase 2. Similar, 2017, phase 1 is in geotube, and this is phase 2 in 2019. Okay. So to answer to the question that how durable is a geotube, so what we had done is that after 5 years, I went to the project site, I cut the fabrics on the Lac Huyam Bridge. This is the brick structure. We do sampling 1, 2, 3, 4, 5 samplings. So what we had done is that this is a sampling. Sample 1, 2 is here, it's at the back, 3, 4, and 5. Yeah. So the sample 1, sample 2, sample 3, sample 4, sample 5. Yeah, these are the sampling, the area where we will actually take the sample. Yeah. This is Dr. Chiu Song Ho for National University of Singapore. Dr. Chiu Song Ho over here. And this is myself. So if you see from here, we mark the fabrics. Yeah. This is at the seam. This is at the joint of the tube. We cut the fabrics. This and we mark this is the what direction, the machine direction. Yeah, you can see from here. Because when you feel the sand, right, you're using a pump, 190 meter cube an hour, it's very, very dense. So if you can see that even after 5 years that you cut, right, it does not collapse the sand down there because it's very densified. So I will cut the fabrics, this at the seam. Yeah, over here. Then this one, I will cut sample 2, this away from the seam. This one with no seam. Then from there, I will cut the sample at the top also. Because the UV exposure, that's, I mean, at the side and at the top is different. I mean, from the top, right, it's much more severe. So we also cut the fabrics at the top. Yeah, you can see, we cut. And this sample 4 that we cut is near the edge, sample 4 that we cut. Yeah, you see, we cut sample 4. And this sample 5 is on the side, sample 5. Yeah. So if you look at the material, even after you actually cut, I mean the fabrics, but right under tension, right, the tear should actually propagate because this is still under tension. But because of the high strength fabrics and of the special weaving, the material does not propagate. Okay. This is the summary result. The tensile strength after 5-year exposure in the machine direction or in the what direction is 57%. Yeah, retained. Sorry, it's 57 kilonewton. Yeah, after retained. Sorry, 57%. I got it. 57% retained after 5 years. And in the cross machine direction is 73%. The tensile strength retained. And for the CBR, right, it's more than 70%. So what we are trying to say is that the fabric itself is a special make. We actually special make for the customer because the customer requested 5 years. It still must be there. So what we have done is that we cut the fabrics of the tube after 5-year exposure because they reach a 5-year exposure and that's the requirement, and they allow us to actually to cut the fabric for testing. So it still retains 50% tensile strength after 5 years. Okay, so if you need more than 5 years, because depend on the application, as I highlighted earlier, each fabric is designed based on application. So you need more than 5 years, right? In that case, you can actually design the fabrics to actually trap the sand and also be more robust, that vandalism, so that people cannot actually spike it. It becomes more difficult to spike. So in this case, we have a fabrics that allow the sand to be entrapped on the surface of the fiber or on the surface of the fabrics, like this type or this type. So when sand gets entrapped on the fabrics, right, it actually protect the fabric from UV. It also make vandalism more difficult, and it make also like fire. Let's say someone throw a cigarette box, right? It make it more difficult to burn because it entrap the sand particles. Okay, and this type of material normally we use it for high-end beach resort. Yeah, beach resort, because in beach resort, if you come up from the beach, right, you don't want to see black color. You want to see sand color, something that match with the, with the surrounding. So you want a sand color. Okay. So this photo is took in 2010. This photo over here. So in 2017, this is taken in 2017. Heavy erosion over here. A lot of erosion took in 2017. Yeah. Heavily eroded. And these are the results. So the customers do not want to have a heart injury over here because the tourist has to go down. So in that case, initially they use bags. They use this, this bag is also very familiar in India. They use this, I call it sugar bags. They use sugar bag for the protection. But we know that sugar bags, these are low end. it does not have a high UV resistance and it will degrade. Yeah, it will just degrade with time. And if you are paying in this resort, I mean, one night cost easily about 300 USD, you will not want to stay in this resort because you pay so much and you don't want to see all these bags start to degrade. So what we have done is that we actually propose a design. This is for immediate measure that they actually propose. A tube in the front there and a scour protection. For the permanent design, we will construct a submerged breakwater over here. So this is for immediate protection. A tube with the scour protection down there. Permanent, we will have a submerged breakwater over here. Yeah. So we actually fuse the bags. This bag is also it's a coarse fiber bag. It allows entrapment of sand on the back surface over here. Yeah. So we install the scour protection using the bags, and from there above it we put the jaw tubes, and we start to do the pumping of the tubes. Yeah, this after completion already. These are the scour protection. These are the tubes over here. So because each fabric site is designed for a particular function, particular application. In this case, they are worried about vandalism. They also want the tube to match with the sand color. You don't want black color, and the tube has to be there for more than 10 years. So that's the reason why we go for coarse fiber to allow entrapment of sand particles on the fabrics and also a high UV, high vandalism resistance. Yeah. Upon completion, this one, and this is up. You can see from here. This is the aerial view of the tubes. This is the scour protection bags, and this is this is took in after 3 years. I mean, it allows algae to grow to form the UV protection. And with this type of soft engineering, right, tourists can actually go over the tube and go for a swim. So it's not. I mean, it does not actually. If you use rocks, the rocks will cut the legs. Yeah, so the tourists can't actually go down. So with this, we use soft engineering to to form the shoreline protection for this resort. This took in 2019. Okay, this is another project we done in Langkawi again. I mean, it's in the same area. This is the resort. This is a very common profile that we see if you go to the beach. You go there, then you see there's a sudden drop. So if you don't do anything, when the monsoon comes again, this will actually recede inside if the monsoon comes again. So how to solve this is either you actually put rocks over here. I mean, you have to do immediate protection before you actually do your submerged breakwater. So for immediate protection, either you put rocks or you can use a jaw tube for immediate protection. And this is what we have done. We actually, install a layer of jaw tubes in the front for immediate protection. And from there, we cover with a sand, with a sand top layer. And for permanent protection, they will actually design the submerged breakwater for permanent protection. Okay. And from there, we go to Vietnam. This is Mui Ni project in Vietnam, Mui Ni. This is Mui Ni is about 3 hours from Ho Chi Minh. This is it's a resort area. They have very beautiful beach, and most of the tourists they are from Europe. Yeah. So this is in 2010. This is in 2017. Yeah. The beach actually recede all the way inside more than 60 meters. Yeah. And we got a Coco Beach Resort, and this is Issmge and Bang Zep Resort. So what they've done is that they actually have to protect their beach. Yeah. Because if you read the newspaper, because in Vietnam they're subjected to typhoon. So every time the typhoon strikes, right, it will actually recede. I mean, they will lose their beachfront every time when the typhoon strikes. So what they've done is that because when they design your ground structure, it will actually influence the structure. Adjacent to it. So these 3 resorts they combine to do a so-called a macro design. So we have groins that's made of jaw tubes, and for immediate protection, we also have jaw tube over here. This is for immediate protection. These are the jaw tube. These are for the groins to allow sedimentation over here. Yeah. This is the groin that goes out into the seafront. These are woven sand color tubes. Woven sand color tubes. They go into the sand. The seafront. Yeah, during pumping. Yeah, you can see from here the groin. This forms the immediate protection. They do the backfill. So with the groin, as Professor Sundar has shared, it allows the sedimentation of sand in between. Yeah, you can see from there. So the sand will start to deposit in the front. So I will just show a video clip on how we do the geotube pumping. Okay. This geotube installation was carried out for the Lac Huyam Bridge. Yeah. The fabric floats in water because it's made of polypropylene. Polypropylene has a much higher UV resistance compared to polyester. Most of the UV degradation happens because the material is the wrong type, it's a polyester. Yeah. Polyester, normally after 2 years, it will start to break down and the degradation can be as high as 50% polyester. So these are PP, high UV resistance. Yeah. Because you can see from this area, these are soft marine clay, yeah, about 7.5 to 15 kPa. So what we have done is that we use an amphibious excavator to unroll the tube out. And the length of the tube is 50.5 meter length of the tube. The tube height for this project is about 1.8 meter. So after you install, then we will pump using a sand slurry, 190 meter cube per hour sand pump. As for Professor Sundar highlighted, why it takes so long sometimes for project in India, because they use the wrong, they use the pump that's so-called, the capacity is not enough. So normally we use 190 meter cube an hour. So again, what you need is only a steel tank. Yeah. Inside the steel tank, you have a pump, 190 meter cube an hour, and you just pump water inside there and infill the steel tank with sand. So this sand slurry will be pumped into the tube. So in a day, the customer, they can pump about 100 meter in a day, in 1 day. So that what I'm trying to say is that as long as you get the pump correct, which is 190 meter cube an hour, you should be able to pump the tube. Very fast and correctly. Yeah, this is the basal reinforcement over here, 800 kilonewtons, because the dike is constructed on soft soil, so you need a 800 kilonewton basal reinforcement to prevent the slip circle from cutting through. From there, we install layer number 2. Layer number 2. The tube comes with a guide rope for you to actually unroll it out, and it actually roll onto the steel bar for easy unrolling and installation at the site. Okay, then after the once been done, you actually input sand again into the steel tank. Yeah, then you pump again. The fabric has a very high water permeability and very small opening size. Water will drain out and it will trap the sand particles. Uh, 190 meter cube per hour sand pump. You just pump inside, water drains out, it traps your sand in the tubes. Third layer, this layer number 3. Yeah. So you can see that when we did the copper dam construction, we had to construct on very steep slope. This is close to about more than 45 degrees. Yeah, this is layer number 3. We have to use a pole to tie the tube because the tube is very close to the edge. And when you do the pumping, we don't want the tube to move. Because if the tube moves, it might overturn down. So we drive the pole, and from there we tie the tube to the pole. You can see from here, this is a very, very steep structure. Yeah, you tie to the wooden pole to secure and position, and then once that is done, we will pump again. Yeah, pumping in progress. Yeah, fully secure. And infill the sand into the steel tank, and from there you just pump. So from here you can see that the geotube, right, you do not require many workers or many laborers. You only need a pump, excavator, and a steel tank plus water. Third layer done in place. So you can see that's very steep, right? It's close to about 45 degrees. But normally we install a tube, right? We would not install more than 45 degrees. But because this is the copper dam, they want to construct it very, very steep. So with this, I would like to conclude and to make a remarks that geotube are designed using different fabrics for different application. If your requirements, right, need, I mean the UV exposure more than 5 years, more than 10 years, right, it can be correctly designed using the right type of fabrics. Yeah. Okay. So I thank everyone for your attention.
Thank you, Albert Lim.
Okay.
I think there are some 2-3 questions are there. I will read out the questions. I think was to Professor Sundar. So there's a question from Alok Ranjan that is it possible to use a composite with thermocol as a soft measure to protect the slopes? This is a question to Professor Vallam Sundar.
Could be tried. But it depends on how, if it is going to be degradable, then it becomes a question mark. Any material which is light and it can have some kind of other kind of features, it can be tried. But thermocol for what? You want to, are you talking about thermocol on the surface or for coastal protection?
For the protection, coastal protection.
Coastal protection, because thermocol, they used to talk about preventing evaporation in reservoirs. But coastal protection, I don't think I have really come across. But what they do is they use a combination, for example, hard and soft measure combination they use. He was just mentioning, no, the second speaker, I think Albert Lim. He was mentioning about the geotube. So what we have done is we have thought of having the geotube as core layer, because in order to escape the UV rays, and over it have the rocks. That is one way, so that at least you can save a little bit of rocks and then use the geotube. That kind of thing, a combination is possible.
Okay.
Also, yeah.
I hope this has answered the participant who has asked this question. I think there is another question from same participant. Can we think of preparing any other composite material for slope protection?
I think there are other experts who can state about this, talk about this. that he's talking about slope protection. Slope protection, other materials, mostly I have only like this, or maybe I need to think. Cannot really come out with a, I think probably others may be in a position to help me out.
Oh, okay. So the next question is to Mr. Lim from Smita Patil. What is the blue sheet that is used in between the layers of the geotube? It is slide number 35 in the video.
I mean the participants, they are very sharp. They actually notice the blue sheet.
Yeah.
Yes.
Okay, I mean, not many people notice it. I appreciate it. What happened is that you've got the first tube, then you backfill with sand behind. So when you put the second tube on top, the second tube will be sitting on the sand. So when you pump, the water will drain at the bottom of the tube. So the blue sheet is a plastic sheet to prevent under scouring under the tube.
Thank you for answering that. There's one more question from Dr. Premlata. Can you share the experience with the use of geosynthetic tube in beach where the wave currents are very, very high?
Okay, so I mean, what we are trying to say is a tube, normally we will use it to form the core. To dissipate it, the wave energy, you still need your primary and the secondary armor rocks.
I think Professor has a question to.
Can I
Yes.
ask directly?
Yes, please go ahead, sir. Please go ahead, sir.
Mr. Albert, I just want to ask you one question. Do you have any kind of UV stabilizers for the tropical countries? Special kind of UV stabilizers, particularly for
We have, and that's the reason why, Professor Sundar. That's the reason why for that. I mean, normally for tubes, right? If it's not properly designed, it will start to break down. I mean, around 1.5 to 2 years, it will start to break down, and that's the reason why we highlighted. I mean, each fabric are specially designed for the application, so that, for instance, the Professor Sundar, if you say, okay, Albert, I need 5 years. So in that case, we will use special UV dosing for for the fabrics. Yeah, and that's the reason why for the Vietnam project, the client, before we actually do the project, the client already put it down onto the table. It has to stand for 5 years, and because if it start to break down for 5 years, the coffer dam will be affected and the bridge will be affected, and that's the reason why we do special fabrics. So the answer is yes. Let's say, for instance, for India, if you tell me, okay, I need this number of years, then we can actually design the fabric to meet that requirement.
That is the crux of the problem. Totally.
Yeah.
That is the biggest challenge.
Yeah, because what we are facing is that we don't want the products to have a bad name. They say, oh, the geotube, it can't be used, it degrades. I mean, it degrades, it starts to break down. So that the problem is that, I mean, it's the wrong fabric for the wrong, requirement. I put that way, and that's the reason why I put out earlier. PET fabrics are, I come across in the region. I mean, even in India or in Vietnam, right? It will start to break in 1.5 years, and the strength loss can be as high as 50% in 1.5 years. PET. Okay,
Thank you, Lim.
Okay.
To sum up this session, Professor Vallam Sundaram has very nicely and very simply brought out what are the causes of erosion, the stabilization problems, the solutions like the hard engineering options, the soft engineering options. He also presented a very interesting case study on the coastal engineering problems in North Chennai port, wherein he actually got an award for that as well. The Van Island artificial reef solutions, and also on the soft engineering solutions, the dune stabilization, coastal vegetations, and the geotubes were very well brought out by Professor. And Albert Lim did talk about the geotubes, its applications both on land, in water, presented very nicely successful case studies in Vietnam for the bridge project and the deep sea port, and a couple of other case studies in Malaysia. And he emphasized that the geotube could be one of the soft solutions for coastal protection. So it was very interesting presentation from both of you. Thank you very much, sir, Professor Sundaram and Albert Lim, for a very nice presentation. So with this, I conclude this session, and I will hand over the session back to the organizing committee. Over to you, Dr. Jimmy Thomas. Thank you, sir. Thanks for this opportunity to share this.
Thank you. Thank you. Thank you.
Thank you.
Thank you very much. First of all, I would like to thank the eminent speakers, Professor E. Sundar and Mr. Albert Lim, for sharing their experience and expertise with all of us delegates. It was both like wonderful lectures covering various aspects of shore protection, applications of both hard and soft technologies. We also thank our chairman, Dr. Parthasarathi, for conducting the session, and I think it was finished well in time so that we can start the next session in time. So thank you very much. Once again, I thank everybody for this wonderful technical session.
Yeah. Thank you. Thank you, sir.
Thank you. Thank you. Thank you.
Now we can go to the next technical session 4. I'm happy to welcome Dr. Anil Joseph, who is going to chair this session. And here we will have 2 lectures, one by Mr. Paulo Di Pietro, and the second by none other than Professor C.N.V. Satyanarayana Reddy, who is the heart and soul of this workshop. Now it's my pleasure to introduce Dr. Anil Joseph, our chairman for this session, who is a close friend of mine. Dr. Anil Joseph did his engineering from NIT Surat, and he got his PhD from NIT Calicut, and he also has another PhD from Open International University. He's the director of Geostructurals Private Limited, a leading foundation and structural consultancy firm in Kochi. So he has done a large number of work in Kerala, India, and even abroad. And like most of us are either in geotechnical or structural, but Dr. Anil Joseph is equally competent in both fields, both structural engineering and geotechnical engineering. He's a National Executive Committee member of the Indian Geotechnical Society, and he's also involved in many other professional societies, including Institution of Engineers, where he's an officer bearer. He also takes a lot of activities, including social service also, and other activities also. And recently, he was elected as one of the top 10 Diamond Hall of Fame New Age Icon Changemakers 2020. So with this brief introduction, I have great pleasure in inviting Dr. Anil Joseph to start technical session 4. Over to you, Dr. Anil Joseph. Hello, Dr. Anil.
నానబెట్టిన తర్వాత డీప్ ఫ్రై చేయాలా డైరెక్ట్ కదా కొంచెం లైట్.
Dr. Anil Joseph. Dr. Anil, we are not able to hear you.
I am connecting from another system.
Dr. Anil has some connection problems. He'll be joining in a minute, actually.
So go to next slide.
Yeah, sorry for the technical glitch. Is it audible now?
Yeah, it is audible.
Okay. Yeah. First of all, thank you, Jimmy sir, for the introduction, and congratulations to getting elected into the National Executive Committee. And it is a great pleasure for me to chair this session on this ISSMG TC 213 workshop on score and erosion. I would like to congratulate the organizers, particularly Satyanarayana Reddy, for taking great pain in organizing the event. And today we have two sessions in this technical session 4. And the first one is erosion control solution with case studies. The speaker is Mr. Paolo Di Petro, DT Senior Specialist, Corporate Technical Division, Technical Education and Know-how Manager, McCaffrey Geosynthetics, Italy. So, and the second topic will be on issues related to erosion and its effect on stability of structures in Visakhapatnam by none other than the man of the show, Professor CNV Satyanarayana Reddy, Department of Civil Engineering, Andhra University College of Engineering, Visakhapatnam. So I will introduce the first speaker now, and Paolo Di Petro is currently Senior Technical Education and Know-how Manager at Office McCaffrey Corporate Headquarters in Bologna, Italy. With a degree in Civil Hydraulic Engineering earned in Italy in 1984 and over 30 years as professional in design and construction of geotechnical and hydraulic engineering works. Paolo's experience stated as project design engineer at the lead of a technical engineering team, supervising and coordinating studies from feasibility to final design, performing cost analysis, and overseeing construction sites. Having served for 4 years in the USA as a technical director for the North American operation, and later for another 4-year term as technical head of the German operation group headquartered in Berlin, his responsibilities include research, development, and innovation of new steel wire and geosynthetic systems as well. Since 2001, Paolo holds frequent seminars and workshops to design engineers, contractors, and state officials in geotechnical, soil retaining structures, slope stabilization, river and erosion control works, and best management policies and practices of soil bioengineering systems. He is also an active contributor to the development of international standard ASTM, EN, DIN, and author of several papers on international conferences. So it's a great privilege for me to welcome Paolo Di Petro, the Senior Specialist Corporate Technical Division, McCaffrey, to deliver this lecture on this session on score and erosion. Over to you, sir.
Thank you, sir. So, sir, I will join once again at 4:45, sir.
Yes, sure.
Okay, thank you, sir.
So, Professor Babu, how do we take forward introduction and then followed by this?
Hello. Can you hear me?
Yes, sir. Yes, sir. We can hear you.
Okay, good. So let me put on the presentation. So good afternoon, everyone. This work is an overview of some basic principles to take into consideration when designing river engineering structures. I'm going to start with a brief background on basic principles of modern river engineering, and I will then briefly classify typical erosion phenomena based on experience and observation. Then I will show an overview of main applications in use for erosion control in river environments along with their functions. And I will then discuss recent research studies and new design approach for the stability of erosion protection systems. And lastly, I will show some real-life project cases with their peculiarities and their challenges. In the history of river engineering structures for erosion control, the first ancestor of the modern gabion dates back almost 130 years ago, when a riverbank restoration along a river, Reno, crossing a small town, took place. The small town is today part of the suburban area of Bologna in Italy. You can see here a little bit the location. This early application was built in 1894 to repair the riverbanks due to a breach caused by a major flood. The structure is the first example of how engineering combines the use of natural materials, the stones, confined inside a cage to reduce their size and the overall volume. The simple idea revealed to be successful over the time. The good performance of this application and the many more built in the following years led to further improve this idea through an industrialization of the technology by manufacturing standard geometries with a box shape, standardizing size, quality, shape to allow them to be connected together. These pictures show gabion applications in the early days. At the beginning of last century, the manufacturer introduced the double twisting process of the mesh to provide an improved strength and to allow an engineered use in hydraulic and geotechnical applications. Gabion applications start becoming attractive as engineered systems to control erosion due to their ability to combine the strength, the flexibility, and the natural pleasing outlook at the same time. The picture below on the left shows gabions used to protect the pier in a harbor in the early 60s. The increasing interest for these natural systems led us to invest in research programs aimed at developing design criteria to provide engineering methods to design them against the effect of hydraulics and the hydraulic and geotechnical instability, analyzing performance. Among their best features, the environmental friendliness and the ability to integrate with surrounding environment becomes an attractive subject of research in the 90s. The picture below on the right shows the old site in Italy after more than a century, where the first gabions were used. A few more gabions were added on top of the old ones to raise the bank in the 60s. Nature has fully taken over, and gabions and old and new are blended with the environment. But I would like to mention some basic principles when designing river works. The first postulate we learn from experience is that the hydraulics is not an exact science. When we design structures in river works, we make our choices on current knowledge, but also on know-how and on best management practices, assuming that natural events like rainfall, flooding, storms, to assume in our design will be based on statistical data. This will require caution, a cautious approach, and in most cases to perform a risk analysis, analyzing scenarios beyond the design data assumed. So a modern and correct approach to river engineering requires to recognize two main types of requirements. The hydraulic requirements, meaning the base of technical knowledge, including evaluating the stability of a solution both from geotechnical and hydraulic point of view, using correct and sound engineering practices, using design methods based on risk assessment and not on fixed numbers, considering how erosion will affect the surrounding environment. So in other words, use an integrated river management approach. But also, and most importantly, the environmental requirements, meaning consider the river as a living environment. That requires us to understand the rules, like the river is a dynamic environment. It's necessary to consider that it will change over the time. In applying river engineering principles, minimize changes in the morphology and nature of the watercourse. In applying protection measures with proven ability to recover and to reestablish the natural conditions. That is, using sustainable systems. And finally, to provide solutions aimed at balancing the ecosystems. River engineering requires to start from location, characteristics of a watercourse, depending if we are in the mountains or at the foothills or in the valley, close to the river outlet. The three regions will be characterized by different climates, different soils, different morphology. In mountainous regions, watercourses will be characterized by steep gradients. Normally, we consider 5 to 10 in the normal practice, 10% in the normal practice. With deep erosion, frequently characterized by an abundant and coarse bedload. Structures used to prevent erosion in these regions are grade control weirs, for example, sometimes combined with secondary longitudinal bank protection. On the mid-slopes, gradients become moderate, so we could consider 1 to 5% as a reasonable standard range. And river sections start widening, forming a low-flow section, a tholweg, and a berm on the lateral sides, which will overflow during the high floods only. In dry times, sometimes forming a small island or rapids in short reaches. Typical structures may still be gabion weirs with a wider crest, combined with bank protections alongside, and small groins to facilitate the sedimentation on curved reaches. Valley regions are the last segment of our river, where the watershed has collected most part of the rainfall volume. Rivers are typically characterized by low gradients, less than 1%, low velocities, less than 3 meters per second, and large discharges, more than 1,000 cubic meters per second. Definitely in larger rivers, we're talking about the tenths of thousands of cubic meters per second, and by a tendency to meander. Intervention in this region will be primarily to stabilize the river banks on bends or straight reaches and to favor sedimentations in sections where meandering tends to progress. The problem of floods in natural watercourses may require solutions like to intervene on the banks, so a bank protection, to build a new embankment, a dike. Alternatively, when space allows, an encroachment area where water may temporarily flow into may be created, so a detention basin. We have seen that in the mountains, we may alternatively consider to reduce the gradient, so a gradient reduction. In other cases, a cross-section reprofiling may also be an option. In case of a bank protection required, the top of the slope may be sometimes raised when little space is available on the sides, or otherwise a section may be widened to convey a larger amount of discharge within the river section. All this shall not forget the possibility to encounter site limitations like the archaeological landscape restrictions or other environmental issues. As previously mentioned, depending on the site, location, geometry of the site, climate, etc., the engineer shall choose the most suitable technology, varying from a large, massive retaining structure, or a hard armor, or a soft lining system, or even simply by using natural self-sustaining soil bioengineering practices to help fast and natural recovery. Understanding rules means to understand how erosion generates. We could start from the type of problem, then see what is the case, the cause, and where is it generated, and finally, which effect results from such type of problem. We could have drainage resulting in surface runoff, typically occurring natural or artificial slopes. And finally, generating erosion due to lack of vegetation, soil instability. Another type of problem is seepage, resulting in reduced soil strength. Where? In embankments and slopes. Another problem is scour, formation of scour holes at the toe of riverbanks critical for bridge abutments, generating progressive instability. Finally, the wet and dry cycles or temperature variations, resulting in the formation of cracks in cohesive slopes, resulting in progressive debris. Erosion protection systems in rivers can be grouped either depending on their direction to the stream, lengthwise or crosswise, meaning along or across the riverbank, to prevent instability, or by conveying the flow as a drainage media. Sometimes they can be intermediate between longitudinal and transversal to the stream to control the meandering by favoring sedimentation. In the first category, we can consider bank protections and bridge abutments. In the second category, we can group river crossings like culvert head walls, as well as guide bunds, more typical of some larger rivers, or bridge piers. In the third category, we can group channelized streams or reaches where the rivers are canalized due to the space constraints typical of the watercourses crossing urban areas. And in the fourth category, we may refer to the groins to maintain the flow within a given path. Along the banks, rivers generate instability by eroding the toe and creating a failure surface. The solutions in this category may require mass gravity walls or linings, depending on the angle of slope. When infrastructures cross rivers, we shall ensure that the bridge has a stable foundation. We can see examples of progressive erosion underneath the bridge due to the lack of protection. On the right side, examples on how the main structure can be protected. Another example of lack of protection in a culvert structure. Here, the main contributing factor is the progressive erosion is the rigid apron, unable to follow the soil contour. The correct design shall consider flexible systems able to manage the transition zone between concrete, rigid, and soil, loose and erodible. Special applications are guide bunds, frequently used in the Indian region. Guide bunds are structures that divert the water to flow in the central zone of the river to avoid river meandering across the large floodplain with risks for all piers to have excessive scour due to the low flow season, during the low flow season. Pier foundations are highly erodible riverbeds in highly erodible riverbeds. They can be subject to instability as piles are progressively exposed to the flow. These situations are still quite critical as we have rigid supporting elements, the piles, in contact with the loose erodible soil. And adequate protection with flexible structures to manage this transition, avoiding abrupt changes will also be needed. Drainage channels like channelized streams collect and convey the water to a safe zone. Protection measures in these courses guarantee that the flow is safely brought to the delivery network. In large floodplains, normally the groundwater flow as well as the secondary channel may affect the flow in the main channel section sometimes, forcing changes in its path. Considering that floodplains or areas adjacent to the main channel are often used for agricultural purposes in the dry season, gravity walls or revetment may be used to contain the flow inside the desired section. Often in wide river sections, typically in alluvial plains, where meandering can be dangerous as it could progressively scour close to the infrastructures, groins may be used to favor sedimentation in other reaches at the bed. Lateral spillways. They are used to provide a controlled water release, diverting the water flow in the river from the river during the flood, or redirecting the water back into the river after the peak flood. Spillways release water to prevent damage to the levee embankment Except during the high water event, the water does not flow over the spillway. So spillways can be constructed with the crest lower than the top of the embankment. The protection is usually made by concrete, stones, rocks, or gabions. Overflow spillways with significant hydraulic head will require properly shaped crest, an energy dissipator downstream, and a protected release channel. Gabions and matrices are flexible and permeable structures frequently used in river engineering works, as we have seen. It is in 1984 that gabions and matrices become an engineered system after the first experimental study done by Colorado State University. Back in 1984, there were no rules about erosion protection systems. The mattress stability was based on the principle that the confined rock should not move. The proliferation, actually, in the hydraulics of open channels, an important change over the years has been the creation of standard. The proliferation, as I was saying, of several types of erosion systems required engineers to provide a guidance for their selections to guarantee an effective protection against the erosion. In the United States, the most reference standard defining performance limits for all erosion protection systems in open channels is ASTM D6460. Applicable to most types of erosion protection systems, from the heavy duty to the lighter wetments, this standard defines the stability for aligning either when no collapse or when limited erosion underneath occurs. In order to reevaluate the conditions of failure in line with an ASTM for the new McAfee mattress, Colorado State University recently completed a research study performing a new test campaign. The research was developed in 4 steps. Task 1, preliminary, was aimed at analyzing the effect of the flow on the wire mesh and the time only. So this was performed running the flow on an empty mattress. The scope was to see resistance to the flow the wire mesh alone provide. The task 2A combined, always preliminary, were made filling matrices with rock of different gradings and uniformity. Here the combined presence of different partitions and stones allowed to test the velocity dissipation through the mattress layer. Task 4 was made on a larger flume, simulating the real flow regimes of an open channel. Based on results of the preliminary investigations, the best performing combinations of partition and stones were chosen. The tests were performed in line with the requirements of ASTM, which defines failure either by a recurrence of a mechanical rupture or by reaching excessive erosion under the mattress. The development of all 3 project phases required a thorough analysis of the various aspects. All in all, the research was completed in almost 3 years, requiring important financial investments, but also in terms of time and resources. On the other hand, the results brought up to light quite a valuable outcome, as overall the effectiveness of the best performing mattress resulted into a 73% reduction in thickness of a bank protection compared to a conventional riprap lining. The new research at Colorado State University allows to introduce a correlation with other factors not considered in the past, allowing to optimize limit performance on the new mattress, ultimately leading to the definition of the new approach applicable to the new generation of McAfee mattresses, the Rhino Mattress Plus with the X ties. The Rhino Mattress Plus with the X tie has basically 3 main improvements compared to the standard Rivet mattress. One is the pleating of the mesh, making partitions much more robust with the double mesh. Second is the innovative and much more durable new polymer coating, making wire mesh more resistant to the abrasion and the sediments carried by the water. A higher UV resistance to the high temperatures, as well as a much lower embrittlement temperature to the cold climates. And finally, the X-tie, a patented anchoring tool to firmly and securely connect the lid to the bottom of the mattress. We learned that the benefit of a double diaphragm partition the rock size smaller and more uniform, and above all, the presence of a tightening connection between base and lid greatly boost the performance both against rock movement and against erosion. By interpolation, we could introduce partial factors in the Shields formula to include these contributions. Here, we can see the formula here. In summary, comparing past and present in our design approach, we could say that the attractive force theory allows to define equivalent Shields coefficient to apply to mattress protection. This method, still in use for riprap, is focused on the limits of the lining's mechanical stability, condition of no movement of the stone. The new standard ASTM introduced a new way of looking at the performance of an anti-erosion system. The mechanical stability, always, combined with the controlled or limited erosion underneath, which is the main purpose of it. This chart shows a summary of where we can observe the relevant improvements of the allowable shear stress in relation to the thickness of the protection when we combine mechanical stability and the anti-erosive function. The light blue color bars show results of standard mattresses with single diaphragms based on the tractive force tested in 1984. The blue middle bars show the increase in shear strength by using a double pleated diaphragm only and the most suitable grading for the film. And finally, the dark blue bars show the ultimate and most relevant increase in shear strength when adding the X ties to the unit. So overall, we have say an over 50% increase in performance. These results today have been implemented in the new Macro Studio, a user-friendly software to assist designers in the selection of most appropriate solutions for riverbank protection. To enable designers to view different scenarios, the software provides multiple choices, pulling out from a database shear resistance values for other common anti-erosion systems as well, allowing also a choice to model a channel section only with natural materials like bare soils or vegetation from light to dense. When choosing a Rhino Mattress Plus, the software will require the relevant parameters to use, like the grading for the rock fill, the thickness, and the assumed roughness. Based on these variables, a database will provide the equivalent allowable shear resistance for that mattress configuration. Macro Studio is a simple tool with a user-friendly interface, able to model open channels of any shape, from simple trapezoidal to double trapezoidal, or virtually changing geometry, checking multiple discharges, or profiling slopes, partly with natural vegetation and mattresses or gabions, is very simple to do. Results allow the designer to quickly make a decision considering various scenarios and best performing configurations. Sorry, I have to plug in. Okay. We provide regular training online sessions on Macro Studio for people interested in using this tool. Let us now move to the last part of this presentation, a brief overview of 5 interesting case studies in the Indian territory. The first one is the Mahanadi project. The location of this project is in the eastern side of India, in the Orissa state, near the town of Paradip, south of Kolkata, where the Mahanadi River flows into the ocean. After the cyclone of 1999, both rivers Devi and Mahanadi suffered from severe erosion. The effects of the tidal waves, combined with water velocities of 2 to 3 meters per second, dislodged the existing protection works. The project received financial aids by the World Bank. The riverbanks needed to be reconstructed using the available fill. The 2-to-1 slope was stabilized by dumping loose rocks, riprap, on top of which a lining protection of 0.5 meter gabions was installed. A large part of the protection had to be installed underwater, and that was one of the biggest engineering challenges. Gabions had to be pre-filled and launched by crane down to the riverbed to a depth of 15 to 18 meters, so quite a challenge, cost effectiveness was one of the successful project's outcomes. The second project is the Valmiki project. This location is on the northeastern side of India, very close to the border with Nepal in the Bihar state. The Bihar Water Resources was looking for protections on the left bank just upstream of the Gandak River barrage in Valmiki Nagar. The Gandak River in this section has a discharge in the range of 24,000 cubic meters during the monsoons, resulting in severe erosion on the left bank and damaging the gates of the Gandak barrage. So approximately 1,080 meters length of the bank had to be reconstructed and protected. The retaining structures was designed for a seismic zone of 5 as per the Indian standard. The retaining structure required to be flexible, permeable, and able to withstand poor water pressures and protect against scour. So in order to meet these requirements, the solutions was divided into 3 parts, in 3 sections. The reinforced soil retaining wall with a permeable gabion fascia, the slope stabilization on the upper bank with a synthetic erosion control geomat reinforced with a double twisted mesh, and finally the scour protection with a mattress apron and a gabion key. And this solution was chosen because of the high permeability and flexibility and the environmental friendliness. You can see here some details of the structure. The soil reinforced structure was used combining geogrids, high-strength geogrids, and steel wire mesh, a soil reinforced system with the gabion fascia. The third project is the Golpaganji project. This is approximately 100 miles south of the Valmiki Nagar along the Gandak River near the city of Golpaganji. Another project which required an intervention of erosion protection. Here, during the construction of a bridge across the Gandak River, due to a sudden increase in discharge, the river started eroding the bank at the toe of the guide bund and downstream and at the downstream end. And riverbank protection measures required, in this case, urgent protection works, using the available sand and least amount of stones, scarcely available in the area nearby. To meet this requirement, cylindrical gabions lined with the geotextile and filled with locally available soil were proposed. Here you can see a picture during the installation of these units. Gabions were factory assembled and supplied in a folded form. Construction required opening and holding gabions to allow fast filling using special arrangement designed to this purpose. The protection was was completed and say in a very short time, and it was extremely successful. The fourth project is quite a challenging project. This is the Budge Budge project. It's because it's about is quite an unusual effect, the tidal bore. The location is in the suburban area of Kolkata in the southwestern side in West Bengal. The Cheviot Group has a factory located along the river Hooghly. The river is in this section in its estuary zone, and it is subject to heavy tidal bore phenomena, which cause intense turbulence and hydraulic jumps. Here you can see a couple of pictures of, say, during it was approximately 6 meters in height, and the slope at a 2:1. The thickness of the system was analyzed and considered to be approximately 3 meters. Geotextile bags and sack gabions filled with sand were adopted to fill the embankment core. Here, this part. The geotextile bags were made of woven polyester geotextile material. Sack gabions lined with geotextile were filled with the dry sand and laid in position. In order to ensure solid and firm function to the gabions used at the toe protection, an additional high-strength geogrid reinforcement was wrapped around the units. The two lower images show the protection on the embankment before and after the installation of the upper gabion layer to cover everything. Last project to mention is the Delhi Noida at the Yamuna project, the Yamuna River project. The location is south of Delhi in the suburban area. In 1999, the Delhi administration proposed a road bridge across the Yamuna River downstream the existing interstate bus terminus bridge for the mass rapid transport system about 2 kilometers upstream of the existing Okla barrage. Due to the presence of the new structure, it was anticipated that velocity would be high and the bridge piers needed a protection. The river works were designed for a discharge of 15,000 cubic meters per second. The maximum velocity is around 3.3 meters per second. The original design consisted in a massive slope protection with a 1 meter thick gabions, stones, with a cost estimate of about 275 million Indian rupees, around 6.1 million USD. The alternative proposal considered was to use a single layer of 0.5 meter gabions. And here the interesting point, because this resulted in a volume reductions of about 50% as compared to the original solution, resulting into an overall saving of nearly 130 million Indian rupees, accounting 2.8 million US dollars approximately. So quite a considerable saving. So in conclusion, in this presentation, we have seen important points, I guess. Number one is erosion is a result of a natural environmental change. We shall understand the rules to develop sustainable solutions. Number two, river works require solutions suitable to integrate with the surrounding environment, minimizing disturbance with the ecosystem. Point number three is a very important point, is an achievement of these days, of modern times. Erosion control systems shall be tested in accordance to a common standard procedure. Thanks to the new development currently in the ASTM standard allows to do so. And this is the first guideline for most systems. Also, for new rhinometers show an effectiveness by going in accordance to this ASTM of over 50% compared to conventional riprap. And when I mention 50%, I'm referring to the total cost of ownership. So that includes construction, maintenance, and everything. So during the lifetime of a structure. And the number of projects built around the world, we have seen a few examples in India, prove the effectiveness of these erosion control systems, as well as their environmental friendliness, of course. Well, this concludes my presentation. Thank you for your attention. And of course, I am more than available here to answer your questions.
Yeah, thank you, Mr. Paolo Di Pietro, for that wonderful presentation. Very informative, covering the entire aspects right from the history of river protection, basic principles for designing river works, function of applications of different river protection, research and new design approach to river engineering, and 5 interesting case studies, all from India, right from the Mahanadi River Project, Gandak Bargage on the left bank at Valangiri, bridge protection along Gandak River, bridge protection along Ganges, and the Delhi Noida Yamuna River project, where substantial cost saving was achieved by changing the design. And the important aspect of testing systems using ASTM D64060 to be standardized. So there are a few questions from the audience which has already come in. We will just go through those questions.
Sure.
From Temura Rahul has asked this question: can the current protection methods help in the prevention of soil from the effects of heavy flood, as the heavy floods that occurred recently in the northern and northern eastern states in India caused many regions to be submerged underwater?
Okay. I'm sorry, I didn't quite catch where. I'm sorry, because I have to see now. What can you repeat the question one more time,
Yeah.
please?
Can the current protection methods help in prevention of soil from the effects of heavy floods, as the heavy floods that occurred recently in the northern and northeastern states in many regions to submerge underwater?
Yes.
So that was the question. The methodology can it be
Absolutely.
adopted when there is heavy floods, especially in north and northeastern states?
Yes, absolutely. Thank you for the question. Yes, the procedure here that we are putting in place, and I was fortunate to be also one of the members in developing a STM D6460, allows exactly to apply to any erosion system the effect of a flooding, basically, because we have all the abilities during the testing procedure, and ASTM allows that to define different slopes. So we can even design for a spillway generating the right amount of allowable shear stress, which is, let's say, simulating the realistic scenarios. So yes, my answer is absolutely.
Thank you very much. Any more questions from the audience? Yeah. So there is one question from Alok Ranjan that you have referred a river near Gopalganj in Bihar. Are the soil conditions different from whatever you encountered in Valmiki Nagar? So the question is, you have referred a river near Gopalganj in Bihar. Are the soil conditions different from whatever you encountered in Valmiki Nagar?
Yes, I think you can also see it a little bit. Maybe the pictures were not large enough to see a little bit the difference. But in the Golpaganchi site, we had to deal with, say, quite a big challenge, the scarce availability of rocks. And so that was, in practice, the challenge of that requires us, instead of having a lighter system with matrices or gabions, depending on design, but we had to go on a 3-meter thick embankment, which required, of course, a little bit more substantial volumes, but we were able, by using geotextiles lined inside a cylindrical gabion, to create the solid core of the embankment.
Okay, so I think it's clear. Now there is one more question from Smith Patel. Is it necessary to take seismic zone-wise design based on the seismic condition? Whether we have to accommodate the changes in design is the question from Smith Patel.
Yes, seismic is an important factor, because it may generate also soil liquefaction in certain instances. Not always, but of course it has to be considered based on the geometry of the site. If we're speaking of a retaining structure, definitely is a must. Is one of the conditions that would lead the design to a certain type of solution and reinforce, or say we have a massive structure, we need to do, let's say, in line with the requirements. If it is for a slope, depends on the type of soil and on the sloping angle to decide whether seismic can or cannot or shall not be necessary to consider.
Yeah, there is one additional question from Anand Hulagabali. The question is that gabion walls or sand-filled geotextile bags, which will be more stable and economical?
Typically, I would go for gabions in a box shape, let's say in box-like shape, because this gives for the above the water construction the possibility to connect the units together. Cylindrical gabions normally are used for the underwater applications in any type and shape, because they are easy to install. Even though I must say that after, and you have seen some of the interesting and most challenging projects. There was the first one that I show in Hanadi, where by the use of a suitable crane and skilled labor, we are able to lift units in a box in a typical shape of a gabion box. So this means that when you're placing the units in underwater, you can also achieve quite a uniform surface on the ground, and this obviously benefits the anti-scour function.
Okay, we got the point. Now from Shankar Ganesh, there is a question: if suppose the embankment upon soft soil as well as in the heavy rainfall area, for this case, is there a possibility of slope surface erosion and slope deformation also? Which will be a preferable solution?
So deformation or what is the
slope surface erosion or slope deformation also? What is the preferable solution? Embankment on soft soil, when heavy rainfall is happening, there is a possibility of slope surface erosion as well as slope deformation. So which will be a solution in this particular case?
Well, it is generally difficult to give an answer that would fit all points, because this would very much depend on the site conditions. The approach we use is generally to understand the level of deformation that we have to achieve, and depending on this, we might combine the use of geosynthetics and steel wire mesh together. There are several solutions that we could use for that purpose. The use of high-strength geogrids combined with the permeable and flexible units in steel wire mesh. So this could be, if I'm trying now to follow a potential project. Now, this could be an option. Yes.
Thank you very much. As we are running short of time, the next speaker is already in. Otherwise, it's a very interactive session, very informative session. And thank you, Paolo Di Petro, for that wonderful session. Now, let me call upon the Satyanarayana Reddy to deliver his talk. And his topic will be issues related to erosion and its effect on stability of structures in Visakhapatnam.
Thank you again.
Yeah, it's my pleasure to introduce Satyanarayana Reddy. And Dr. CNV Satyanarayana Reddy is a professor of civil engineering at College of Engineering, Andhra University, Visakhapatnam, and has 28 years of teaching, research, and consultancy experience. His expertise and research interests are in the area of reinforced soils, ground improvement, landfills, soil retention in excavations, deep foundation, and forensic geotechnical engineering. He obtained BTech degree securing first rank from Nagarjuna University, MTech in geotechnical engineering from IIT Madras, ME structures from Andhra University, and PhD from NIT Warangal. So a multi-dimensional consultant. He is an academician. He is into geotechnical consultancy as well as into structural consultancy. He has guided 8 PhD scholars and 92 MTech dissertations so far, and the number keeps on going to increase. And I know in the next 2 decades, it's going to reach a much greater height. He also has got more than 110 publications in various national and international journals and seminar and conference proceedings. And he's a wonderful organizer and has organized more than 30 seminars, workshop, and training program. He served as director of Andhra University Development Center during the period 2013 to 17. He is a recipient of Engineer of the Year 2006 award from Government of Andhra Pradesh and the Institution of Engineers India, AP State Center. And Dr. Sarvapakula Radhakrishnan, Best Academician Award 2014 from Andhra University. So an academician as well as a practicing professional. He handled research projects funded by Department of Science and Technology, New Delhi, and University Grants Commission. He is an established consultant to various local, state, and central government engineering organizations. In addition to this, he is a reviewer for Indian Geotechnical Journal, Institution of Engineers India, Journal of Civil Engineering, ASCE Journal of Materials, International Journal of Pavement Research and Transportation, and International Journal of Earth Sciences and Engineering. He is a Life Fellow of Indian Geotechnical Society, Institution of Engineers India, and is a life member of Indian Roads Congress, Indian Concrete Institute, Indian Society for Technical Education, and the list goes on. He is nominated IGS member in International Committee, Technical Committee TC213 on score and erosion, of international member in H4 Committee on Embankment, Ground Improvement and Drainage Committee of Indian Road Congress IRC for the term 2018-20. And he's serving as the chairman of IGS Visakhapatnam chapter and is a National Executive Committee member of the Indian Geotechnical Society. And most importantly, he's the pillar of the IGC 2020. And I wish him all the best. He has done a wonderful job. Now the show next 3 days has to go on. All the best, Satyanarayana Reddy and team, for this presentation, and as well as the next 3 days where we will be all ears and listening to you people. Unfortunately, due to this pandemic COVID, we are not able to come down to Visakhapatnam to hear you straight from there. But through this online platform, we will be listening to you. All the best, and over to you.
Thank you, sir, for your elaborate introduction and your good words. So actually, we all would have loved to host you all here for IGC 2020 and for this pre-conference workshop. But COVID has prevented from physical interaction. But still, whatever best possible we are doing with all your assistance and help. So I'll go into my presentation. So whatever presentation I'm going to make is based on my consulting works, right? So mostly related to stability of structures and stability of slopes in deep excavation. And towards the end, I will touch upon the beach erosion problem recently experienced in Visakhapatnam. So in my presentation, I am going to deal with the effect of erosion of foundation soil in hill slopes on stability of structures with a case study. And the second topic of my presentation will be related to the effect of erosion of soil in deep excavation. This also I am dealing with the help of a case study. And third one is the beach erosion problem, which Visakhapatnam has been experiencing from 2014 to 16. This problem was more. After that, this problem has receded. I'll tell you why it has why the problem has receded. So first, I'll go into my first part of my lecture, that is the effect of erosion of foundation soil in hill slopes on stability of structure. So in the year 2010, 16th December, that is the day on which IGC 2010 was started in Mumbai, venue being IIT. So in the early hours of 16th December, I got a call that one of the retaining wall of an apartment present in hill slope has collapsed. So can you make a visit and assess the situation, right? That was the scene. So I'm going to show you the picture of the failure of retaining wall, RC retaining wall, RC cantilever retaining wall, present on the rear side of an apartment located in Visakhapatnam in Maripalam area. So name of the apartment I'm hiding, right? So it belongs to Maripalam area. So actually, the residents of that apartment came to me in 2008 with observation that cracks are developed in certain parts of the apartment, and also saying that at the junction of retaining walls on rear side and abutting two adjacent sides, right, corner portion, cracks were there, and they asked me to make a visit and give suggestions. So during the visit, it is observed that cracks were present in different areas of the apartment. Fortunately, no serious structural cracks were observed, but clearly there is indication that the material in the basement is having some movement. and retaining walls on north and south side. So here front side is west, rear side is east, north and south are adjacent sides, right? So on north and south sides, retaining walls are built of RR masonry. On the rear side, that is east side, since the apartment was in hill slope, so from front to back there is an elevation difference of about 4.5 meters, and that's why on east side they have constructed a RCC retaining wall of about 5.5 meter height, right? So the height of backfill retained on east side was 5.5 meter. So same is mentioned from front from east side wall to from west side to east side, right, retaining wall, right? The backfill height was varying from 0 to 18.6. So as a result, north and south side RR walls, right, have varying length, varying height from 0 to 18 feet 6 inches. That is about 5.5 meters. Okay, so it is observed that RCC retaining wall, cantilever retaining wall, got separated with development of tracks. Right, there is separation with respect to the RR retaining walls, and when I have gone to the other side of the building, where there was the presence of a road at lower elevation, when I looked at the retaining wall foundation part, I could see that there is insufficient foundation soil beyond the toe of the wall. Okay, so the foundation soil of retaining wall on other side of backfill, right, was observed to be very steep. That is due to excavation of soil from the slope by the neighboring people, and also due to erosion of soil from heavy rains. Some gullies are also seen, and the soil present beyond the toe of the retaining wall, right, was with a steeper slope. And also the soil that has slided due to erosion from heavy rains that has accumulated, that accumulation has been also observed. And we have carried out stability analysis, whether anything wrong with proportioning of retaining walls and all. So coming to RR retaining walls adopted on north and south sides, the dimensions were inadequate, particularly when it was reaching to the east part, since height was varying from 0 to 5.5 meter. So some inefficiency of sections have been noticed. Coming to RCC retaining wall, cantilever retaining wall on each side, it was structurally sound. It was properly designed, even taking a level load of about 10 kN per minute. Then, based on the analysis, we have told that due to inadequate sections of RR retaining walls on north and south sides, they are yielding outward because of infill that is placed. And also, RCC retaining wall, RCC cantilever retaining wall is also yielding outward due to presence of insufficient soil cover. Right, so that's why the residents, this is a state. So we never expect that failure will happen in the projects which we visit. So that's why at that time I did not take a photo. So the soil cover, right, beyond on toe side of RCC cantilever was like that, almost below the base of the footing. So then immediately I suggested them to dump soil, particularly gravelly soil, because on north and south sides, the sites are empty, right? They are vacant. So that's why I have suggested to place some materials so as to reduce the effective height of backfill and to stabilize the existing RR masonry walls. They could do that with contribution from neighbors also. But coming to each side, whatever suggestion I gave to go for a soil nail wall for foundation soil below the cantilever retaining wall, or at least there was a provision for some roadway by the municipal authorities, but the road was not formed. So since there is no road laid and there is provision, simply I have suggested at least you bring some morum and prepare a berm-like thing to support the foundation soil of RCC cantilever retaining wall with the safe slope maintaining 1.5 horizontal to 1 vertical with stone pitching on the slope to prevent the erosion. So they negotiated with the builder, asked them to get it done. And they bargained, they negotiated with even site owner who was at the site at a lower elevation behind this apartment. So that particular person did not agree. He simply told, I may construct a structure or I may dispose. I don't want to spend like that. So they delayed. They delayed the things and nothing was done with respect to RCC cantilever wall. And also, weep walls are provided, but they are not properly finished. Some of them are not clearly discharging water, right? Some cloggings are seen. And we have advised them to at least keep the weep holes clear so that drainage will be better. So nothing is done for 2 years. Meanwhile, also 2 rainy seasons were there and some more erosion took place. And finally, the retaining wall foundation soil having supported for 2 years in the worst possible condition, it failed by overturning. Simply the underlying soil did not mobilize the required support, and thereby the retaining wall failed by overturning. You can see here the entire RCC cantilever retaining wall, has undergone overturning due to lateral thrust from the backfill, of about 5.5 meters. So no structural crack, nothing has happened, So abutting on the compound wall of adjacent apartment was in contact with this wall. The moment when this RCC cantilever retaining wall overturned, the neighboring old compound wall, which was of RR construction, that has also collapsed, and that fell onto another apartment that was under construction. So you can see this right side, yellow colored one is the affected apartment. So actually this apartment rear side, compound wall has collapsed, and this has resulted in collapse of abutting retaining wall that fell onto this apartment under construction. And you see the extent of damage that occurred. You see the extent of damage that occurred to the apartment under construction at lower elevation. So even some of the columns got crushed, slabs broken. So if such damage, serious damage has occurred, no builder would like to restore it, So finally that builder has to finally demolish everything. Since during that period, 2010 period, there was real estate boom. So we could manage because there was a rise in price of land, and we could completely demolish the structure, and he disposed of the site without much loss. But the ignorance of the owners of this apartment has resulted in a significant damage to the other builder who has constructed apartment at lower elevation. So you can see here. So here actually the tie beams that are present, due to the sudden rush of fill material, and due to collapse of the retaining wall, even they have developed cracks, So that is covered, and later on, immediately cement grouting has been done to further stop this, and all the residents were asked to vacate the apartment till the treatment is done to backfill material, and again fresh retaining wall is constructed on pile foundation. So initially they thought for spending some money on going for a soil nail wall to strengthen the foundation material. initially, even before that, they could have kept a watch on what is happening beyond their compound wall. They could have objected when people are excavating and there is erosion, got some soil and dumped it there. That they have not done. And finally, they had to spend more for constructing a retaining wall supported on pile foundation. Okay, so anyway, so after the incident, again, the local authorities have asked us to investigate, and we have done the borehole investigation. Based on this data only, fresh retaining wall support and pile foundation was given. Going by this data, since it is a hill slope, there is presence of clay gravel in top 7 meter depth, and underlying that there is soft disintegrated rock followed by soft rock. So in such a failure scenario, we cannot go for again conventional RCC type kinds of retaining wall, because you cannot excavate, you cannot dare to excavate and lay a foundation. It will affect the stability of the apartment as well. So luckily the apartment was foundations were laid right in natural hill slope material, maintaining a minimum depth of 2 meters below. So that's why structure stability is not affected, except that due to large lateral rush of backfill due to overturning failure of retaining wall, tie beams and plinth beams have shown up some cracks, and building walls have experienced some minor cracks. Except for that, apartment was stable. So the bearing capacity analysis has been done just for academic purpose by modeling the failure zones in AutoCAD and the effect of loss of soil cover above the base of foundation. If soil is lost due to erosion, how the bearing capacity changes, and in next case, if entire soil present to the right of or toe side of your right cantilever base slab, if it is completely lost due to erosion, how bearing capacity changes in dry state and saturated state, that has been analyzed using basic bearing capacity theory. These are the properties of hill slope material. Being gravelly soil, it has a good angle of intersection with cohesion of 1.2. It is right classified as GC. Gravel is 66%. Soil is very good, right? So these are the failure zones. So taking surcharge load of 10 kN per meter square. So we have determined the base pressures. Toe pressure, maximum toe pressure was determined to be 20.8. So in the normal condition, when there is no loss of soil beyond the toe of retaining wall, right? In dry condition, SBC was very high. In saturated state, it is 34.1, still much higher than the maximum base pressure. When you consider the loss of surcharge, that is right, the soil present above the level of base of footing, right? If that is lost, so there is a drop in bearing capacity, safe bearing capacity in dry state from 59 ton per meter square to 41 ton per meter square. In saturated condition, it has dropped down to 25.1. So when there is loss of surcharge as well as foundation soil, right, beyond the toe edge of footing, the bearing capacity, you can see it has decreased, right, like anything, right? Even in dry state, it is marginally, right, close to the maximum base pressure, and in saturated condition, it is much less. So that is the reason why the wall has failed by rotation, right? That is due to improper ground support. So you can see reduction bearing capacity, right? So loss of soil above the base level of foundation beyond toe in saturated state and dry state, right? The losses are only up to 30%, whereas if soil is lost right below the base of foundation, right, with respect to vertical plane considered, right, through the toe, the loss is significant, almost 60% loss of right bearing capacity. Okay, so that's why it is important to protect the foundation soil of right retaining walls or even foundations which are close to the walls. Any instability to the retaining wall will affect the stability of foundation soil also. if depth of foundation is less. So that's why one should take care and should keep a watch beyond the retaining wall, right? If neighbors are affecting the soil by excavation or due to heavy rains, if some soil is getting eroded, they need to take care. It is always better to protect the slope by maintaining vegetation or if not do stone pitching, whatever it is. So in Vizag, we have many hill slope settlements. Not only that, some developed colonies, right, posh areas, right, are developed along hill slopes. So that's why problems of collapse of retaining walls has become more common these days. So in cities like Visakhapatnam, so one should be very careful, right? So because gravelly soil, their fines will be less, and if the plasticity of soil is less, in saturated condition, easily the soil will disintegrate, right? So that's why protection of material slopes is important. Otherwise, under compression, gravelly soils are very good. They will have a very high bearing capacity, right? So next topic which I am going to present you is with regard to caving in of soil that happened in a deep excavation made in a soil predominantly consisted of sand. In Visakhapatnam, most of the area in our university area, right, surrounding university, up to RK Beach, right, the soils prevailing are silty sands are, right, fine sands are present. So coming to clay silty sands. So looking at sand or fine sand, we'll think that they are poisonless and we'll be careful. So coming to clay silty sand, because of the clay binder, as long as it is dry, you feel that it is standing in excavation. But if it rains and if it gets saturated, right, the material will disintegrate and it will try to flow with water. So one of the builder in the center of the city, right, I should not reveal the name and all. It is it happened very near to our Andhra University, within a distance of 1 kilometer. These days, as you know, most of the builders, right, and commercial complex owners, right, so they are going to create cellar or sub-cellar floors, right, particularly for meeting the demand of right parking space. So particularly when such provision is there, when excavations are made, they need to take proper right soil retention measures. Otherwise, it will result in sliding of soil from the excavated faces, and it will affect the stability of neighboring structures, and also the workers who are working, they will be also affecting. Sometimes they will lose their lives also. Okay. So coming to clay soils, excavations are not serious because the Koju strength is enough, and you can comfortably excavate up to about right 5 to 6 meters without any difficulty, without going for any special retention right techniques. So as I said, the clay, silty clay sands and silty sand, right, are unreliable because they give a feeling that they can stand vertical in dry state, but they destabilize when they get saturated due to rain or due to subsurface flow. So this is the photo of a picture wherein a commercial complex owner has excavated soil to a depth of about 20 feet, 6 meters, and for construction of basement wall. Again, that soil was standing because of little poison that is present in soil, and relatively it was dry. So I warned them because I was going through that road, and sometimes some soil sliding took place, and he used to call me. I advised him, you should go for soil nailing technique. Don't take risk. If it rains, you will land in trouble. So sometimes in some parts he has got soil nailing done, And again, he asked that applicator, no, you go, it is enough, it is standing and managed. So finally, the side where the maximum height was there, he has made excavation without doing soil nailing for full length, just he has done for limited length. And since underground drainage, right, structures have appeared, and he said since they are coming, why they are obstructing, so not necessarily standing. Like that, he requested that agency, and he continued excavation. And finally, foundation trenches were made for laying foundation for the basement wall. And people were working, bar benders were working in the early hours. Overnight, there was also rain, and during the early hours, there was caving in of a large mass of clay, silty sand material in saturated state, and buried 4 people, and they lost their lives. 4 migrant workers, right, were buried. This happened in the month of September in 2014. And the soil sliding, right, has resulted in loss of soil. This site was abutting a road, right? So the soil from the shoulder portion of the road extended to the site was also affected, and underground pipelines and sewage lines got visible. And it is noticed that right, there is large amount of seepage, right, coming from them. So we don't know whether the seepage was present prior to the failure or during sliding of the mass, right, they got damaged. But continuous, right, seepage was noticed. So as I said, the builder has attempted to carry out soil nailing on this south side, where the road shoulder material sliding and all that. There, soil nailing was partially done, right? As the UCD system, right, is encountered, they have stopped doing nailing and continued excavation up to -6 meter level. And there, further they have excavated by about right 1.5 meter to lay the foundations for the basement wall. So that time the incident happened. So that's why, based on this incident, later on, subsequently, what is to be done, he has done it. Initially, he has thought for expenditure of about 10 to 15 lakhs, and finally, he has to pay for compensation to the right workers whose right lives are lost, with compensation and again stabilizing the soil, right, that has caved in, right. That need to be retained, everything was done. And finally, he had to spend about 45 to 50 lakhs for further right carrying out his work. So that's why whenever you are making excavations in clay silty sands, where a little clay binding is there, without proper soil retention technique, don't attempt to do this. If overnight if there is some heavy rain, it is going to seriously affect the stability of soil, and it will affect the person who are working there. So I'm coming to my third part of my presentation, beach erosion problem that is faced in Visakhapatnam. This started in January 2014, and 2014 October was right well remembered by people of Isaac, because Hudud happened, right? Much prior to that, this beach erosion issue started. We have Kursura Submarine Museum. So the beach adjacent to that got eroded. The soils, the sea surge, right, happened by about 30 to 40 meter for a length of about 300 to 400 meter, and waves started touching the soil fill, right, supporting the footpath. So along our beach, we have a beautiful beach, and we have right road, beach road, right, in a vicinity of about 40 meter distance, right, 40 to 40 meter distance from sea. So when sea surge took place, the waves were touching the soil field, supporting the footpath, right? And as a result, since the soil present there was silty sand, due to hitting of sea waves, the material right got eroded, and the footpaths and all started right, collapsing. And there was also propagation of moisture due to capillary action, and right, even in the edge regions, pavements also experienced some distress. Immediately, the local authorities, ODA, right, and the GVMC commissioner, and they came to us, and immediately they wanted to take some measures to stop further right, failure of the existing beach road and abutting right, footpaths and all. So this is a case you can see here, right? Sea waves coming and hitting sea sand, right? Silty sand, silty saturated, and right. The moment it gets saturated, it will easily slide out. So earlier we used to have a very beautiful beach at that time, right? People used to enjoy, and in many movies, right, people can see how beautiful that was. Now, fortunately, again that beach has come back, right? I'll tell you what is the reason behind it. So immediately, in whatever projects, some boulders are there, right? Some boulders and gravelly soils are there, right? GVMC commissioner got them brought to beach, and they started dumping so as to reduce impact of waves on right, silty sand and stopping the right further damage. Though it is not proper way, they try to do on war footing basis. You can see here how the structures abutting right, the sea got affected. Now the present state, if you see, right, again we have beach, right, about 20 to 30 meter, right, that beach has come back. So since morning you are listening to many speakers, right, on beach erosion. So some of the major causes for beach erosion, if you look at, whenever deep dredging activities happen at ports for increased draft, right, it will cause beach erosion in neighboring area, right? So we have a port here, Visakhapatnam Port Trust, and also one more port, private port, Gangavaram Port, right? So always dredging, deep dredging happens, right, for increased drift. So that is right, one possible cause for beach erosion. And whenever new harbors, right, are constructed, right, that can also cause right, beach erosion due to changes in right, wave currents and all. And similarly, construction of sediment, right, trapping upland banking, right, may result in erosion. And sometimes construction of jetties and groins, anything you can, any structure you construct into sea, right, will create problem, right? So the energy of waves will be transferred to the neighboring region. They will be obstructing there, and I'll show. So groins, though in some places they use as remedy for beach erosion, you might have seen one groin after the other. Like that, they will be going on placing groins, and the entire beauty of beach will be lost. Right? You can see even in India also, in some places like Chennai, you can see groin. No doubt, erosion of groins will create beach, but the erosion right, location will go on shifted. So coming to erosion control options, you can go for filter type structures to protect the beach abutting roads and structures, gabion structures. You can use geotube walls for protecting right, the roads and other infrastructure abutting beach if at all sea surge is happening, and as well groins, right, as the earlier speakers pointed out. These are the options. Just I go one after the other in filter type structure. So the existing ground, particularly if you take our previous Visakhapatnam case itself, existing ground is some silty sand. So what we should do is we should place some good right backfill material, right, like gravelly soil, and finish it to proper shape, and over that place the right bedding stones, and right in between backfill and bedding stones, you place right a filter like thing like geotextile, nano and geotextile, and above that place armor stones. If waves comes and hit, the energy will be absorbed by armor stones, right? And a little amount of water, whatever that will be seeping through the bedding stones, through geotextile filter, can enter into backfill. But when water goes back, it cannot take soil fines. So that's why the existing ground and backfill material will be stable, right? So filter type construction will have usage of right a geotextile fabric, above that some bedding stones, or that large sized stones, right, armor stones, right back. So you need to protect the toe. So armor stone will be dumped right beyond the toe for required length for stability. So this model morning Professor Madhav was also discussing. For bank protection, we'll go for right. We'll go for uses of right laying a geotextile after finishing the right slope to two horizontal to one vertical. Over that place a geotextile nano, and over that you can place right a gabion mattress. In between mattress and right geotextile, you can place sandbag layer also. That will take care of right the structure, the bank which are protecting. But there can be erosion of soil, right, on the bed of beyond the toe of your right bank. So for that, we will be using PP, right, rope gabion mattress, right, since it will be always in touch with contact with seawater, right. So in order to avoid issues of corrosion and all, we generally go for right PP rope, right, gabion mattress. Right. So this will check the erosion of material here. So this model will work well. The other option is even for control of erosion, right, beyond the toe of existing ground, we can use right a gabion mattress, and the retaining structure itself can be formed with gabions. And on the back of the gabions, we will place a filter cloth in the form of nano and geotextile, and you can place a back. Right, so all these things will protect your right back. So in Visakhapatnam also, at least if authorities take up such right structures, even if such happens for some reasons, right, the footpath and associated road, right, where people sit in the evenings and enjoy, right, they will not be affected. So gabions, no need to right deliberate more, because already morning since morning you have been doing it. Coming to geotube walls, right, geotextile tube walls, right, that is what Professor Issmge was specifically mentioning, right. These work well in many countries. These are being used to create the lost or eroded beaches. So geotube walls can be used either to protect, you can use them for protection of banks, or when you use them as submerged units under the sea waves, they will create the eroded beach also. Imagine if you place a stack of geotubes, right, in sea. So when sea waves cross this stack of geotube walls, the incoming waves will bring along with them the sediment, right, fine sand particles will bring in. So when it tries to go back, only water will be able to seep through the geotubes, because it will be mostly sand. Whatever sand they are bringing, that will be getting deposited behind this geotube wall. So over a period of time, there will be accumulation of sand, right, behind the geotube walls, and like that there will be creation of this. If you use geotube walls along the bank, right, they will absorb the energy of hitting waves, and protect right the bank from being eroded. So these will work well. Only thing is, while designing, you need to take the hydrodynamic forces into account. Otherwise, during cyclones, if at all a cyclone hits that particular area, you might have read right in literature and recent cyclones, you might have heard that even geotubes got right washed out onto the tanks, onto the shore, right, during cyclones. So if they are not properly designed, the impact of heavy winds and right whatever large waves with high energy created during cyclones, right, they may displace even gabion cliffs. So it happened in Kakinada, right, Kakinada area. So people, some people refer that it is a failure. I don't say it as a failure. We should properly design sufficient weight, sufficient right design should go in to make it proper. So just like human beings, people with flexible nature will be able to survive in all kinds of situations. That's why for resisting the impact of dynamic action of sea waves also, whatever measure you take, it should have sufficient flexibility. Any rigid thing you are going to construct into sea, that will make right sea more aggressive and right erosion issues will come in. Right, among various options, geotube wall is more flexible. It is capable of absorbing more energy. That's why it is the most invariably used, right, in different countries. In fact, for Vizag, also we suggested, even Professor Madhav was also supporting this idea. So they were negotiating and all. So nothing has been done. There were some proposals finalized by government, but till now, no right protection measure is taken. But it is on cards. Since they are covered, I am skipping. Actually, what was happening is in Visakhapatnam, beach nourishment was regularly done. Right? Even now it is being done. For some reasons, because of reduction in sand traps, for some reasons, port authorities could not do nourishment properly. And if nourishment regularly happening is not done also, it will result in loss of right loss of right beaches. So beach erosion can happen that. So even when this problem appeared, I was hinting that if we take up right beach nourishment by pumping dredged sand, this issue may be resolved like that. And for some reason that they were telling that there was a reduction in amounts of traps, and they were not able to do it as what they were doing earlier. But some reason in 2016, IFR, International Fleet Review happened. I know that my time is over, I'll conclude. International Fleet Review happened in Visakhapatnam, and for that, authorities have given top priority, and a lot of right sand has been pumped, and the last beach was created almost, and from that time onwards, regular nourishment is being done, and that is the reason why no serious beach erosion people are facing now, and people are enjoying the beach now. So anywhere, whatever nourishment programs are there, they have to be continued. Otherwise, they will bring in unnecessarily issues, new issues of erosion and all. If even with that, that is not happening, if there are some changes occurring in right sea course and all, then we need to really address the issue. Right, so with the usage of groins, longshore drift and all, how the sediment transport occurs. This was explained by Professor Sundar. Right. So only thing is, if you put groins, the sediment material will be trapped by them, and it will get deposited. And on drift side, there will be deposition of sand, and over a period of time, you will see that last beach is right again and again. But the thing is, the area next to it will show the signs of again erosion. You will go on extending growing after the growing, right? So that's why in many countries they are not going. Not only it will affect the aesthetic, it is not permanent solution. Okay. So based on my observation with regard to Isaac, I feel regular beach nourishment will also check the beach erosion. And always it is better to have seawalls, permanent seawalls, to protect the banks and protect the structures, right? Like roads or whatever resorts that are there. And never allow anyone to construct anything into sea, right? Any production we make into sea will aggravate the sea and in the neighboring area erosion effect will notice. Okay, anyway, I summarized right everything and concluded at the end of each topic. I think I'll close with this. So I thank Dr. Anil Joseph for introducing me and giving me the chance to give a lecture in this session. Thank you, sir.
Thank you.
If any questions are there, I'll be.
Yeah, thank you, Satyanarayana Reddy. It was a very wonderful session, and I congratulate you. Despite your hectic schedule, you are able to manage this session also. So hats off to you for finding the time for that. A very interesting session where we had that retaining wall collapse, which was explained well in detail with what is the engineering behind that, and a very important point which you have pointed out, that no action was taken by the resident for 2 years. Most of our problem happens because the people who are affected will sleep over it, and no maintenance is a big issue which is there. We believe that once it is constructed, it is there for every time. No regular maintenance is not there. That is one issue which you have highlighted. And second is the instability of soil for excavation in basement. Yeah, you have pointed out, despite the warning, they were not careful and 4 lives were lost. So that's a big tragedy that could have been avoided if a proper engineering would have been there. And coming to the third session, which beach erosion in Vishak, where you have wonderfully covered the entire systems, what can be adopted and how practically it can be used. It is very useful. The session was very useful for all the participants, and we'll go for the question and answer session. Now there is one question from Seda Shirin Biju. So she has asked that what are the methods that can be adopted to reduce deep excavation erosion problems?
Yeah. Deep excavation erosion problems to the side of excavation, you can plan some drains, divert the surface runoff. Don't allow water to enter into the excavation. But actually, if soil is susceptible to sliding, right, you should not dare to excavate without proper supporting system, right? Even with that also, it is always better to divert the surface runoff and seepage water. It is better if you cover the surface of soil, everything, right, your excavation with some impervious sheets, right, plastic sheets, and divert the flow away from the excavation.
Understood. Thank you very much. So that's one suggestion. And what exactly was how you done after that collapse and 4 people died? How that solution was brought in? What was the solution for that particular case?
Regarding that soil sliding side, sir?
Yes. Yeah.
Actually, that person was asked to consolidate the soil that has caved in. Since it was silty sand, right? It was compacted in the settled state. After that, even some cement grouting was also done, and only after that, that person was allowed to cut it with the proper retention using nailing also.
Soil nailing, okay.
Because we don't know how much loose the soil has, because the entire thing has moved. At least the soil adjacent to the area of construction, right, was stabilized, and again it was retained temporarily with grouted nailing system, and with that we could complete. You could have done it. You could have done it earlier. Unnecessarily, you had to grout the soil that has caved in also.
Understood.
Because you cannot remove the entire volume. That is difficult task.
Yeah. So
removing that will cause neighboring soil also to slide.
Understood. So it was a very valuable lesson, which has to be a carry-home package where you have to be very careful regarding when you are going for deep excavation, and the importance of ground improvement and soil stabilization along with soil nailing was adopted to solve the problem. So thank you very much, sir, for that. And any more questions from the audience? If you want, you can unmute and ask the questions. So the practicality of geotube, are you using geotube in Vizag to prevent the soil beach erosion?
Actually, it was considered, sir, actually. The earlier government involved some international experts also, and they have also given the same solution to go for geotubes. But somehow, due to budget and constraints and all, they delayed, and luckily they have been doing this beach nourishment. Dead sand they are pumping annually, and that is taking care of the present beach condition. Whatever beach that is lost, that is since 2016 they were doing it. Earlier also they were doing it. We used to see in between some period that nourishment program was missing, and that has brought in this one.
Thank you, Professor Satyanarayana Reddy, for that wonderful session, and it was a very informative talk. So this session 4 was very interesting, where we have Paolo Di Petros talking about the geosynthetic applications, and Satyanarayana Reddy sharing with us the case studies with what are the practical solutions also. So very interesting session. I would like to thank the organizers for giving me the opportunity to chair this session, and I would like to hand it over now to the session coordinator, Jimmy, my close friend, Jimmy Thomas, for the further proceedings.
Thank you, Dr. Anil. And again, we had a wonderful session. The 4th session also was equally good. We had 2 very interesting lectures by Mr. Paolo Di Pietro and our own Professor Satyanarayana Reddy. On behalf of the organizing committee and on behalf of all the participants, I thank both Mr. Paolo Di Pietro and Professor Satyanarayana Reddy for sharing your expertise and your experiences with us. Thank you very much, sir. I thank Dr. Anil Joseph, who conducted the session in so lively manner, and he has also summarized all the in a so nice way. So that's all. Once again, I thank you. I thank both the speakers. I thank the chairman, and I thank all the delegates for their very active participation. Now I request Professor Satyanarayana Reddy to lead the validation session. Over to you, sir.
Thank you, sir. Thank you, sir, for effectively organizing the session. So from organizing committee, I have one announcement. The feedback form, right, has been shared. So kindly fill up the feedback form. So I hope all of you might have enjoyed all the 8 lectures that are delivered today. And we hope that on behalf of Issmge, IGS and Andhra University, we hope that certainly you might have gained considerable knowledge in the area of in the areas of scour and erosion. At least some ideas will come into your mind if you look at any erosion or scour issue. So as members of TC 213, myself and Dr. Jimmy Thomas, so we coordinated with International Society for Soil Mechanics and Geotechnical Engineering, and our chairman, Professor Issmge has approved this program, and because of his support, we could organize this important event. On my behalf and on my co-coordinator, Dr. Jimmy Thomas, I thank our President, Professor G.L. Shukumar Babu, Secretary J.T. Shahu, and and the session chairman for today's program, starting from Professor G.L. Shivkumar Babu, then Professor G.V. Ramana, Dr. Parthasarathi, and Dr. Anil Joseph for sparing their valuable time and for accepting our request to be here and chair the sessions and organizing the lectures in the sessions. So I take this opportunity to thank all the keynote lecturers, our Vice Chancellor, Professor P.V.J.D. Prasad Reddy, our Principal College of Engineering, Professor P. Srinivas Rao, Head of the Department of Civil Engineering, Professor P.V. Praveen, for all the support and help required for organization of this event. Sir, Dr. Jimmy Thomas, sir, shall we allow any one or two participants to speak and express their experience?
Definitely, sir. That'll be very nice.
So I request one or two participants to give their response. You can unmute your audio and speak. I think sir, Dr. Balakumar sir is here. Sir Balakumar sir.
Yes, sir. Good evening. Tell me, sir.
Good evening, sir.
Yeah.
So I'm happy that you are here since morning and listening to all the lectures.
Yeah. 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 So if you really ask my opinion, it was really wonderful issues. So I didn't want to say that, but then there are one or two lectures which was really thought-provoking. One was on the laterally loaded pile by our Professor G. Han. And obviously your lecture was really interesting and thrilling, particularly if you had covered the sequence of construction. That was my last question which I typed, but I couldn't post it. See, there must have been some sort of a sequence of construction between the retaining wall and the main structure and things like that. Probably that also could have been one of the reasons. That's what I was feeling. And apart from that, a lot of works have been done on this geotubes and then erosion and other things. But frankly speaking, I never knew that there is so much of topics are available in erosion and erosion prevention. So obviously, this particular program was highly educative and very interesting program, and all the 8 lectures were thought-provoking. There is no dispute about it. Perhaps some of the younger students who are attending, they must get a clue for their further research work. Those who have not selected their topics, they can definitely do from today's lecture. That's quite possible. So it's very interesting, and one definite admirable thing is Professor Satyanarayan Reddy, you have done an excellent job in organizing this on such a big conference on an online mode so fast. That has to be appreciated. It is really excellent work which you have been doing, and there is no second opinion on that. So anyway, it was very interesting sessions, and all the program also will be, I hope it will be very interesting. Thank you. Thanks a lot for calling me, sir. Thank you.
Sir, thank you very much, sir, for your valuable feedback and good wishes. Thank you, sir.
Thanks a lot.
So any more participant would like to respond?
Good afternoon, sir. This is Vivekanand Matpati calling from Muscat, Oman.
Can you talk a little bit louder?
1 second, sir. Maybe sound is less. No,
maybe your audio is low.
No, it is there, sir. It is full.
Yeah.
So I am calling from Muscat, Oman. So it was a quite wonderful session, and all 8 chapters were very nice, and it was well presented. And as Balu sir telling, it is definitely a good lessons for the students and upcoming people who are doing their higher like research or something. And especially presently, I am involved in construction of dike in the Khazain Economic City in Oman. So we have a similar technique. It is being used like geotextile based with the Gabion with a wire mesh. We are building a big dike. A dike means it is kind of, you can say, the earthen barrage for the diverting the flood water, so that that economic city should not submerge in future. So the whatever some of the topics what we have seen, the sectional details and cross sections, it was quite similar what we are using here, and definitely it was very user friendly and wonderful session, sir. Thank you for your kind efforts putting in this and combining that to online session for whole our world. I think people are joined this one. So it is that achievement goes to you, sir. That credit goes to you, sir. Thank you very much. Thank you.
Thank you. Thank you very much, sir, for your valuable feedback and good words. So the entire program will be available on YouTube, sir. So those who could not attend also, to your colleagues and all, you can share the link so that during their free time they can listen to all the lectures of this international workshop.
Thank you, sir. Thank you. Definitely, sir. Definitely.
So kindly ensure that the feedback forms are submitted before leaving. It is with respect to the participants.
Thank you, sir. Sir, I am Ramakrishna from Visakhapatnam.
Sir.
And I attended, this whole workshop from morning to evening. Thanks to all Andhra University team and all presenters who are presented the sessions from all over the world. Like, any engineer or any student, maximum they can attend one session of this type in a day. And you conducted so much knowledge in one day, we had interacted with all these people, eminent people from everywhere with so short time. This is really great, sir. And I attended many seminars of AU, and this is one of the best seminar I attended. Thank you very much, sir.
Thank you, sir. Thank you, sir, for your good words and feedback. So next 3 days also try to attend the sessions of prestigious Indian Geotechnical Conference 2020. It has 26 invited lectures. I hope we have registered, sir, for IGC 2020, Ramakrishna, sir.
Sir, I have not registered yet. Is it possible to register
Yeah,
now?
you can do that, sir. You can do that.
Okay. Yeah, I'll do that, sir. Thank you very much, sir.
Okay, sir. Okay, sir. Thank you. Sir Thomas, sir, do you have anything to say? You say a few things and conclude.
It was already like a wonderful day, like one full day on cover and erosion. This topic is actually very important for us. Actually, it threatens both the life and livelihood of people, especially like in Kerala. Like every day, I can read in newspapers. Like people, houses are being threatened. Like everywhere there is a problem. Let's say, like people are desperately searching for solutions. Like we have been. Actually, in Kerala, like we have a saying in Malayalam, like because we have a long coast, so this problem has been going for many years, many decades. And the traditional solution has been to put stones, like we say dump stones. Like in Malayalam, we have a phrase like kadalil kalliduka, which means like dumping stone in the sea. Other meaning is something, anything which is effort is going to be wasted in meaning. That means the technique, after sometimes the stones go away, like again doesn't succeed. So it is time we have to find new solutions. Like fortunately, a lot of technologies are available. Like so, but then the problem, like we know, like structural engineering, like it is more predictable. Materials are well behaved, boundary conditions are well known, so we are able to predict with confidence. When it comes to soils, it's more challenging. But here we have, like actually what we have is like soil water structure interaction. So very challenging problem. Like the theories are very difficult. boundary conditions are not known. Like if you protect a stretch, the stretches beyond may be affected. Like so many uncertainties are there. So it's a very challenging problem, probably like very interesting areas to work, both for both researchers as well as practicing engineers. So I think we have covered most of the important areas like riverbank protection. There was bridge cover problems we have covered, coastal erosion, like probably only one area which was not probably rainfall induced erosion, which is also an equal problem. But again, it's a much simpler problem. We have solutions also like
erosion of soil in slopes.
Yeah.
Surface runoff. Indirectly, that is not.
So I think we had excellent speakers, like was presented very well. Like, it was organized everything. When timing was perfect. So actually, I congratulate Satyanarayana Reddy, who is the heart and soul, who put so much effort into his workshop, making it a great success. Thank you, sir.
Thank you very much, sir.
All the delegates.
Thank you very much for your wonderful support. We'll conclude, sir.
Yes, sir.
Okay, I thank all the participants for effectively participating in the sessions and for your interaction. We look forward, for your active participation in IGC 2020 as well. We hope that you will enjoy all the invited lectures and presentations by the others, and others got some encouragement in the sense that Springer has announced some prizes for the sessions. So their presentations will be also evaluated based on their presentation as well as content, technical content in the submitted paper. Session wise, I have sent mails also. Prizes will be given. So once again, on behalf of Issmge, IGS, and Andhra University, on my behalf and my co-coordinator behalf, I thank you all for taking interest and attending this international workshop, through all the lectures, from first lecture to last lecture. Thank you all. Okay, sir.
Thank you.
Okay, sir.
Thank you very much.
Thank you. Thank you all, sir.
Thanks a lot.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you.
So good night, Dr. Satyanarayana Reddy. Good night, sir.
Good night, sir. Thank you, sir.
We'll see you tomorrow at morning.
Sir, morning 9 o'clock we'll meet, sir.
9 o'clock we will meet.
Sir, thank you, sir.
But excellent job, sir. There is no dispute about it. I'm not talking for just for the praise sake, but it is out of my heart. It is coming. Beautiful job which has been done. There is no dispute about it. This program is very, very interesting.
Thank you very much.
Right?
Thank you, sir.
Thank you. Thank you, sir. So we can leave.
You can leave,
I can leave now. Thank you.
Okay.
Madam, how are you? Vandana, madam.
हाँ वो देखा ना मैंने घर वालों को हाँ दिया है हाँ ज्यादा बन गए अच्छा अच्छा अदरक डाला है।
Hello. We request you to please leave the session after submitting your feedback form. Thank you for your support.
Hello. Feedback form is in the email ID. Excuse me, sir.
Sir, you will receive the feedback form through your email, sir. So you can just give that feedback form in your email, sir. You will receive the link in the email.
Okay, sir. Thank you.
Yeah, you're welcome, sir.